Chapter 3, Section 2, Large Molecules, Their Physicochemical Properties and Their Architectural and Functional Significance in Living Matter. Much of the work of preparing this SCTion was cloned while the author was a member of the staff of the University of Toronto. Warm acknowledgement is due to the secretaries of the Banting and Best Department of Medical Research for their generous help. The 4 succeeding chapters deal with some properties of large molecules. We have refrained from classifying large molecules or even defining them in any precise manner, preferring to illustrate their manifold behavior nature in fibers, in interfaces and membranes, in condensed masses, and in the dispersed state. This discussion we have prefaced with a short account of the forces operating in material systems, an appreciation of which is essential to a clear comprehension of the properties of kaolides and the inherent vagueness of the classical definition of molecules when applied willy-nilly to systems in which the discontinuities are so ill-defined that a molecular boundary cannot be fixed, or, if arbitrarily fixed for one set of conditions and with one set of criteria, is so displaced in an altered environment that a molecule may lose its original identity without, however, having undergone any change that would, in simpler circumstances, be called chemical. While recognizing this indefiniteness, it is nevertheless expedient to preserve the term, without being committed to any definition that would demand either the strict preservation of molecular identity through a series of physical manipulations, or the identical similarity of all molecular units formed in a given process under set conditions. The size of a macromolecule so limits the inevitability of its interactions that even in gross measurements we sometimes have to deal with statistical assemblies of non-identical particles, while the changes occurring in the microscopic volumes of the living cell must often be so dependent upon fluctuations as to appear quite irregular and irreproducible, to be sure. These deviations from statistical behavior will not enter greatly into the discussion which follows, for the study of macromolecules in biology is still at the preliminary stage, in which we try to define the repeating units in the fine structure of tissues, but it is well to recognize their critical significance to the future development of analytical biology. Introduction. The disintegration of a mass of tissue, or indeed of any colloidal system, into its component atoms demands an increasing expenditure of energy as the subdivision proceeds. It is, of course, a simple matter to degrade the elaborate structure by mechanical deformation, to remove a certain small number of atomic ions and small molecules by diffusion, and to segregate particles of different size and density by applying a gravitational field. Even these preliminary measures can have such spectacular effects upon the properties of the system, as striking in their way as the resolution of common salt into an inflammable metal and a corrosive gas, that it is tempting to regard any biological system as a single giant molecule, or rather a time series of giant molecules, continually changing in their detailed organization, but preserving a subtle integrity that can be ruptured by forces customarily believed incapable of producing chemical change. It can indeed be argued that an uncertainty principle applies in biology, operating in such a manner as to ensure that the process of observation invariably changes the nature of the property observed. Although we do not wish to subscribe to this view, or to enter into any of the sterile arguments that it has provoked, it is useful to insist on the essential unity and indivisibility of the forces responsible for the unstable organization of living systems and those involved in the formation of stable chemical compounds. The succeeding discussion will perhaps serve to indicate roughly some reasons for the extreme quantitative variation in the fundamentally similar forces causing cohesion and repulsion of atoms. At a certain early stage of disintegration, protoplasm yields particles of colloidal dimensions which satisfy many of the conventional chemical criteria of molecular individuality. To some degree, these, or their unstable derivatives, were present as aggregates in the undisturbed tissue and could be shown to be present by their effect on various physical disturbances too weak to alter materially the unique properties of the tissue. To some degree also, they were present in molecularly dispersed form, interacting kinetically with molecules of the continuous phase and other solute molecules, but to a first approximation, at least, showing physical identity with their derivatives extracted from the tissue and redispersed. In addition to a certain tendency to show uniformity of size and elementary composition, a tendency that can be exaggerated by various fractionation procedures. The protein molecules to which we especially refer have sufficiently well-defined chemical and physicochemical properties for the gross features of their structure to be elucidated by the methods of organic chemistry, even though chemical synthesis has not yet been achieved. This means that, however extreme the lability of the association occurring in lipoproteins, nucleoproteins, and so forth, in the living cell, and however weak those linkages which are broken in denaturation, the protein molecule does represent a fairly sharp dividing line between the irreversible changes which can be brought about in protoplasm by weak mechanical forces and those requiring the more energetic operation of chemical agencies and high temperatures. We can thus contemplate in protoplasm and the various dead structures created by its organizing activity or its degeneration the operation of the whole range of forces answerable for the orientation and cohesion of molecules and their component atoms. The extreme mechanical manifestations of this cohesion are seen in the fluid or jadastic nature of single cells, the softness and high compressibility of protein crystals, the hardness of bone, the lateral weakness and high longitudinal tensile strength of animal and vegetable fibers, the extreme brittleness and low compressibility of sodium chloride crystals, and the volatility combined with great chemical stability of the molecules of oxygen or carbon dioxide. The same contrast extends in large degree to other properties such as optical anisotropy, X-ray diffraction, light absorption, electric conductivity, dipole moment, and so forth. For a first description of interatomic and intermolecular forces, however, we shall attempt to find simpler illustrations in order to emphasize the qualitative differences in behavior that can result from quantitative differences in atomic constitution. 2. The interaction of atoms. The early theory of the directed valence bond resulted in a distinction between primary or chemical and secondary or residual bonds, which is still in use, although the original idea of fixed valence has to some extent required modification. The distinction arose not only from the difference of stability between primary and secondary binding, but also from the complete mystery surrounding the nature of the forces involved in the formation of the valence bond. Thus, the secondary forces were regarded as forces of cohesion, physical rather than chemical in character. The electronic theories of valence postulated the physical nature of chemical forces and led to theories interpreting both primary and secondary bonds in terms of the mutual potential energies of atomic nuclei and their associated electrons. The essential features of the nuclear atom and the theoretical foundations thus provided for a general theory of valence have become widely known, the lack of clarity which exists by contrast. Among physiologists, concertining the more general aspects of intermolecular action may justify the inclusion here of a short discussion of the subject. The positions of the electrons within an atom or a molecule are continually changing. Average positions can, however, be assigned so that the potential at a remote point X due to an atom can be calculated as that due to an assembly of point charges, and expressed as a series of terms in representing a field strength varying, according to Coulomb's law, as ER-ter. It is 0 for a neutral atom, for an atom with a spherically symmetrical time average of charge distribution. The higher terms are also 0, so that there is no external field. An atomic ion, such as Nag or Cl, will have a Coulomb term, but no higher terms, since it has the symmetrical electron configuration of the inert gases. More complex neutral molecules, or ions in general, give rise to potentials varying as 1R, 1Re, etc. The term in LR contains the sum of Clyde-Girardets. Elementary charge X, distance from center, and can thus be regarded as representing the field of a dipole. Similarly, the term in L-large refers to a quadrupole moment, which may be important when the effective dipole is small. Second particle, less than the geotential phi AD of the first at the remote joint X. It is found that an ion in any of the types of field enumerated above experiences a force of translation, while a neutral molecule with an electric moment does so only if TLNG field is non-uniform. The characteristics of the various forces of interaction are summarized in Table 5, rows 1, 2, 3. In addition, dipoles and higher poles experience a torque. This makes certain orientations more probable than others, so that in the field of an ion, the electric axis tends to point toward the ion, W dually. In the field of another dipole, the electric axes tend to become parallel. Such effects will in general be opposed of dipole molecules will occur only in very powerful fields. Interacting particles proportional to 2, ion permanent dipole, 3A permanent dipole, transient induced dipole. Transient EICJ denote ionic charge, Ju, denote dipole moment. It denotes polarizability. R denotes distance between centers. When the two interacting systems of charges interpenetrate, it can be seen qualitatively that at first, as the electrons of the first atom come into the field of the nucleus of the second, there will be a considerable attractive force. With further penetration, powerful repulsive forces must come into play, since the effective fields will be those between the two nuclei and between pairs of electrons. The calculated cohesion at the equilibrium point is, however, far too weak to account for the strength of primary chemical binding. Even when the mutual displacement or polarization of the electrons is taken into account, classical electrostatics fails to explain the primary bond. But the polarization effect does exist in some types of residual force, and therefore merits further mention. Even spherically symmetrical atoms or molecules are iolarized in an external field, and the forces between the inducing particle and the induced dipole are summarized in rows 4 and 5 of Table 5. To complete the enumeration of residual forces, it must be added that even spherically symmetrical atoms with a zero average field show instantaneous asymmetry, and therefore give rise to a fluctuating field. The transitive fields of interacting particles induce transient electric moments and give rise to the permanent dispersion forces of attraction specified in the last row of the close approach and Chernykh action of atoms, require quantum mechanical treatment. And it is sufficient to say here that under certain clearly defined conditions during the interpenetration of atoms, there occurs a concentration of outer shell electrons in the internuclear region, amounting, in effect, to the electron sharing postulated in the early electronic TLNX mesovalence. Further interpenetration is limited by re-impulsive forces arising from the interaction of the interclosed shells with operation of the Pauli principle and by electrostatic repulsion between nuclei. All forces of interaction, from the Ye dispersion to the covalent, may be generalized in the form where F is force, R is distance, and A, M, and P are constants. Whatever the type of interaction, there will always be a certain equilibrium distance of separation, ρ, at which the force is zero and the Ye potential energy minimal. With increasing distance, the force of attraction will rise and then decrease. There is therefore a tendency for all particles to associate vibrating by virtue of thermal energy about the point of minimal potential energy. Varying degrees responsible for this effect and are sometimes known as van der Waals forces. Their respective contributions are shown in Table 6, which also shows how it depends upon dipole moment and B upon molecular volume. When the moment is sufficiently high, as in water, the rupture energy is of the order of magnitude of the Kleiner-Mol energy, resulting in condensation to the liquid state, in which bonds between pairs of molecules have a longer life, but are not strong enough to give rise to a structure with any mechanical stability. Contribution to lattice energy in column 1 is the exponential value of the van der Waals constant. V is the molecular volume of the substance in the liquid state. The table has been compiled from data given by Slater, Introduction to Lyrical Physics, P. 408, Mark Physical Chemistry of High Polymeric C. Stems, P. 95. Evans, Introduction to Crystal Chemistry, P. Dubai, Polar Molecules, P40, and Smith, Dielectric Constant and Molecular Structure, PL92, 3. Homopolar or covalent linkages with an energy of the order of magnitude 100 kil G are well known to be governed by the rule that the number of such linkages between one atom and others is limited by the number of additional electrons needed to complete the inert gas configuration. A necessary consequence is that monovalent atoms can form only binary homopolar associations, which must then depend upon secondary forces for higher order aggregation. The mechanical properties of such compounds can depend only upon these secondary forces, and the rupture energy of the homopolar bond can only be measured indirectly. Substances in which two or more types of binding are present are said to be heterozernic. Homopolar associations of bivalent atoms are also heterozernic, since they may form homopolar chains or rings, but cannot have homopolar binding in 3 dimensions. Homopolar homodesmic compounds are confined to tetravalent atoms, such as carbon, which in diamond forms a homopolar structure of indefinite extension in 3 dimensions, with consequent loss of molecular individuality. The majority of carbon compounds are, however, heterodesmic, since the 3-dimensional linkage is usually interrupted sooner or later by atoms of lower valence. 2 further consequences of exchange interaction or electron sharing are important, namely, the existence in homopolar compounds of characteristic bond angles and interatomic distances, TQ. The semi-empirical theories of Pauling and Slater stress the importance of the state of quantization of the electrons participating in homopolar binding in determining the bond angle. Electrons in p states tend to form linkages perpendicular to one another, and this pronounced orientation, with a well-marked resistance to deformation, imposes a limitation upon the possible modes of packing of homopolar molecules. This is responsible for many of the facts of stereochemistry and morphology. Repulsive forces between substituent atoms usually cause deformation of the 90 degrees valence angle. For this needs considerably less energy than does linear extension in the direction of strongest binding, about 1 kcal mol for 10 degrees compared with low 2 kcal for an extension of 0.1, 0.3 A. This is seen, for example, in the water molecule with an angle of 104 degrees 31 in the pyramidal structure of ammonia. In the pyramidal structure of ammonia, where the bond angles arc all 106 degrees, in the well-known but approximate tetrahedral distribution of valence bonds around the saturated carbon atom. And again in the series C4 cyclocherosity, which show progressive increase in the CL distance corresponding to increasing distortion of the tetrahedral configuration of CC4. Double and triple bindings between carbon atoms, which may be regarded as extreme instances of distortion of bond angle, involve also some decrease in interatomic distance, which in typical cases may be given as 155, 134, and 1.9 A for single, double, and triple bonds respectively. In different compounds, it is, however, possible to find a series of intermediate values for the carbon-carbon distance and for the corresponding dissociation energies. The position of double bonds in a conjugated system has ambiguity, arising from the fact that each atom contains a single electron with unneutralized spin from the point of view of wave mechanics. There is difficulty in assigning these to a series of localized double bonds with spins uniquely paired. Rather, is it necessary to assume each electron to move in the field of nuclear framework, being allotted to a polycentric orbital embracing all the carbon atoms which are conjugated together, in conformity with the Pauli principle? Such a resonance system has lower energy than would be anticipated from a conventional formula, with localized double bonds, while all the CC bond lengths are equal and slightly longer than a pure double bond. An alternative to the theory of mobile electrons is to attribute the resonance effect to tautomerization among various possible canonical structures of conventional type. Both theories have been applied to the benzene and naphthalene molecules, and both have been used semi-empirically with some success in the calculation of energies and bond lengths in resonating structures. Apart from this peculiarity of conjugated systems, the repulsion between electrons concentrated in the internuclear region in a pure double bond leads to an electron distribution with twofold axial symmetry, so that there are two bond orientations of minimum energy at 180 degrees to each other, corresponding to the stable cis and trans isomers of organic chemistry. A second consequence of this restriction, conferred by the double bond, is the anisotropy of J-polarizability of organic molecules. Containing this linkage, a property which indeed extends to the single linkage in molecules with unsymmetrically occupied carbon bonds, the polarizability is usually considered localized between atoms in the region of high electron cloud density, and is described in terms of the three axes of a polarization ellipsoid dot in conjugated systems. The polarization ellipsoid, instead of coinciding with each bond, is of considerable length. Since the electrons concerned in polarization phenomena are those which form the virtual oscillators responsible for dispersion interaction, this increase in length and decreased frequency is of importance in the calculation of van der Waals forces, and will be referred to later for linkage between ions, the heteropolar bond. Electron sharing represents only one method by which pairs of atoms can attain the inert gas configuration. A donor atom with a small number of outer electrons can do so by ionization, while an acceptor atom with a nearly completed outer shell can take up these electrons and become a negative ion. Such a reaction will result in an assembly of ions in which every ion of one sign is surrounded by an atmosphere of the opposite sign, the precise geometrical arrangement being determined by the repulsive forces, which also define the ionic radii. Such a structure is homodesmic and devoid of molecularly distinct units. Other ionic structures are, however, possible, in which agents of several types participate with different interionic bond strengths. The very sharp localization of ions in the typical ionic lattice, EJMS, has been demonstrated by X-ray analysis. Sly outstanding physical properties are to be expected from this predominantly Coulomb binding: low compressibility, hardness, high rupture energy, low thermal expansion, and characteristic lattice vibration frequency. Low electrical conductivity in the solid state gives way to ionic conduction on fusion. These properties have been accounted for theoretically with varying degrees of refinement by addition of the potentile energies of interaction of pairs of point charges over the entire lattice, 5 to 8. Partial ionic and ioniopolar bonds, origin of dipole moments. It can be imagined, however, that in some cases the electrostatic interaction of ions will cause deformation, so that the charge-free interionic region will tend to become occupied by electrons attracted away from the negative ion. Since the atoms still tend to preserve their inert gas configurations, we may expect this process to be accomplished in suitable cases by electron sharing, and not by the formation of an assembly of unbound neutral atoms. This will result in a decrease of dipole moment of each ion pair and in a closer approach of the nuclei, since the shared electrons take up less room than the corresponding unshared air. On the other hand, it may be imagined that the shared electrons in an homopolar bond can confer polarity upon the molecule by being more closely attached to one atom than to the other. We shall not defend this description of the mixed covalent and ionic character of bonds. It is sufficient to mention that it has proved fruitful in the systematizing of a considerable body of chemical information. Pauling's semi-empirical method is to enumerate all the reasonable ionic and covalent structures of a compound that are possible without actual atomic rearrangement, and by certain quantitative arguments based upon a comparison between the observed bond distances, bond energies, dipole moments, and any other relevant quantities and those calculated for the several separate structures, to arrive at an estimate of their respective contributions to the measured values. The energies of various purely homopolar bonds should be interrelated, arithmetic mean of the energies C and 2 at 2. The energies for various single bonds between unlike atoms calculated from thermochemical data do not in fact obey this rule if we assume that bonds between like atoms are completely homopolar. It is reasonable to attribute the discrepancy in the case of other bonds to their partial ionic character. If we denote by this extra ionic resonance energy, it is found empirically that value of additive in the sense that a series of values T can be assigned to the elements if X set arbitrarily at 2.5 for carbon, such that the difference Za, XBY, or XE for any two atoms, A and 6, is proportional to the value of Ea for a single bond between those atoms. Pauling calls X the electronegativity of an element, the electronegativity scale defined in the above manner being closely similar to that of classical electrochemistry. The values of ATX for single bonds correspond, very roughly, with a proportionality factor 10% to their dipole moments, the latter being regarded as components of a vector defining the observed, and derived by analysis of this quantity with the aid of observed bond angles and interatomic distances. An alternative relationship given by Pauling may be written in the form where P is the fractional ionic character of the bond, denoting the ratio of the observed dipole moment of the bond to the moment calculated from the observed interatomic distance and the valence of the ions. Tedious relationship was based on a calibration with the hydrogen halides, and it is of some value in assessing the relative importance of various resonating structures. Such considerations give, for instance, the following proportions of the four structures of water. The bond CO is of some interest in biology. This, in various aldehydes and ketones, has a moment around 2.8, that ESU, instead of character of 47%, or about twice that of the single bond CO. Triple bonds, however, as in the alkyl cyanides, have much higher ionic character than would be expected from this rule, a fact that must be attributed to mobile electrons in the triple bond. Bonds, increasing in importance with the difference in electronegativity of the bonded atoms, provides for the occurrence of a series of secondary interactions of electrostatic character. These would be expected a priori to resemble the interaction of dipoles in some cases. In others, through the operation of steric factors hindering orientation. The interaction of ions with the subject has been reviewed up to 1939 in Rest. Or 1, to which reference should be made for points of historical interest and for qualification of some of the statements made in this section. A further question of nomenclature, with reference to the distinction between hydrogen and hydroxyl, or long and short hydrogen bonds, is discussed by J. D. Bernal and H. D. Mugaborprockroy. Soki 151A, 384, 1935, J. D. Bernal, T.R. Faraday, Soc 36, 922, 1940, A.R. Arbolodi, Protsagriad 473, 417, 19. Faraday, Soc 36, 886, 1940, better describe the situation. In the latter case, a bond energy much smaller than that of a purely ionic system would be expected, because of the partial covalent character of the primary bonds. At the same time, the system might be stabilized by resonance between two covalent structures. Such a covalent contribution involving directed bonds will impose a geometrical restriction upon the electrostatic arrangement. The energy of the latter, considered alone, should depend upon the electronegativities of the atoms or groups X and Y, and upon their ionic radii and that of the ion AA. The special importance of the hydrogen bond, in which AEI is a hydrogen ion, is due largely to the minute size of the proton, and the strength of hydrogen bonds depends in a very rough way upon the electronegativity of X and Y, upon their size, and upon the number of hydrogen bonds in which they participate. The small size of a proton is likewise responsible for the further aequiliarity that hydrogen can rarely associate with more than two anionic groups. These usually form a linear sequence, H, so that the close approach of further X groups is prevented by the electrostatic repulsion of those already bound to hydrogen. Exceptions to this rule are found in the case of glycine and alanine crystals, which may contain bifurcated hydrogen bonds given these facts. the twofold coordination of protons, the symmetrical electrostatic field of the anionic groups, and the directional character of the covalent bond. The possible modes of molecular association through hydrogen bonds can be seen to have great variety. Consider, for example, the compounds Cy-NH3 or T2FH. The conditions here are reminiscent of the relative importance of resonant covalent contributions and electrostatic effects has been much discussed. R.H. Gillette and A. Sherman, J.M. Shuck 68, 1936. Give quantum mechanical calculations for carboxylic acids which do not agree closely with experimental results. On the other hand, purely electrostatic models have been used with some success by Molwyn Hughes, J. Chem, Suk P. 1243, 1938, M. Davies, T.R. Faraday, Soc 36, 333, 1940, E. Bauer and M. Megat J. Fizz, Rad 9, 319, 1938, R.F.J.D. Bernal, T.R., those governing formation of luomodesmic or heterosmic covalent or ionic structures. The covalent binding of the first three molecules predisposes to a tetrahedral configuration. This is complete in CIIH4. In NHS, it can be completed by sharing one additional proton from a neighboring molecule, so that the substance might be expected to associate to form chains and rings, but never to give a three-dimensional structure. The same is true of F8, in which the tetrahedral configuration can obviously be at most rudimentary, so that new protons will tend to take a position or eye diametrically opposite the first name one. The tetrahedral arrangement is already implied in the V-shaped H-OH chain, and the presence of only 2 hydrogen atoms per molecule makes it possible to complete the configuration by attachment of 2 further water molecules through their H atoms. In this way, a self-perpetuating three-dimensional structure can be formed, and this is largely responsible for the striking physical differences of water from other neon-like substances. Many similar examples are to be found among organic compounds, where the presence of hydrogen bonds is often detected by the intercontact methods of X-ray and electron diffraction. These methods are not, however, readily applicable to complex molecules in which the detailed atomic configuration is unknown. Argument by analogy doubtless has some value. The known structures of glycine and dicotoperazine crystals certainly suggest that cohesion must occur in dry proteins and polypeptides by formation of intermolecular hydrogen bridges involving the ketoamino linkage and amino linkage and amino and carboxyl side chains. At present, other methods must be applied, also largely by analogy or by questionable simplification. Nevertheless, we shall mention briefly 2 methods which have given information in simple systems, and the extent to which they have found application to macromolecules. Hydrogen bond formation between different molecular species has been extensively studied by measurement of solubilities and of heats of mixing, especially in connection with bonds involving TH groups. In general, abnormal solubility or high heat of mixing is attributed to intermolecular association of some kind, and attempts are made to identify the atoms. The importance of hydrogen bridging in proteins is discussed by W.T. Asbury, T.R.G.F. Zellhofer, M1, Opley, and C.S. Marvel. Soki, 1337, 1938, M.J. Copley, G.F. Zellhofer, and C.S. Marvel, Ibid, 61, 3550, 1939, M.J. Copley, C.S. Marvel, and E. Ginsburg, Ibid, 61, 3161, 1939, M.J. Copley, G.F. Zellhofer, and C.S. Marvell, Ibid, 62, 227, 1940, M.J. Copley, Ginsburg, Zellhofer, and C.S. Marvel, Ibid, 68, 254, 1941, C.S. Marvel, M.J. Copley, and E. Ginsburg, Ibid, 63, 3109, 3203, 1940, C.S. Marvel, F.C. Dietz, and M.J. Copley, Ibid, 62, 2273, S. Marvel, J. Harkema, and M.J. Copley, Ibid, 63, 10-9-1941, C.S. Marvel and J. Harkema, Ibid, 63, 2221, 1941. involved by the method of elimination familiar in organic chemistry. The results are often complicated by homomolecular association in one or other of the two components, so that the observable solubility or heat of reaction is actually a resultant of several processes which may be difficult to disentangle. It is obvious that in label systems of unknown constitution, the methods are not likely to be very useful. From a brief study of the solubilities of polyesters, polyketones, and polymeric halogenated hydrocarbons, it has been concluded that hydrogen bonding is only one of several unknown factors determining the observed relationships. Polyvinyl chloride, CH2-EduNCl, which should form hydrogen bonds, has about the same low solubility in chloroform. Tetrachloroethane, carbon tetrachloride, and tetrachloroethylene, the polyesters and polyketones, on the other hand, show the expected behavior, being far more soluble in C3L. The second method to which we refer is that of infrared spectroscopy in the wavelength region around the absorption band. For example, in oil equals TH, etc., is usually spread out and EUL is placed to a lower frequency when the hydrogen is subjected to some additional force. Perturbation of the 12 bond, which can thus be measured spectroscopically, is usually attributed to molecular association through hydrogen bonds. This conclusion has been well substantiated in certain cases, but the inner jar rotation of the observed HL bands is less definite in the case of large molecules. Features in the complicated spectra of celluloses and gelatin G have been explained tively. Crystalline sucrose shows several first overtone bands at 1.5 to ILG attributed to valence vibration, stretching, and valence vibration combined with distortion, bending of perturbed and unperturbed O groups. These can be identified in modified form in the spectrum of dried Ramey fiber, the unperturbed components being practically absent. In studies on dry proteins, certain bands have been ascribed to double hydrogen bonds producing 8-membered rings between parallel ketoamino linkages. And intensity changes have been observed on absorption of moisture. The detailed interpretation of these results, however, requires much further work. This may indeed be said of all methods of investigating hydrogen bonds in complicated systems. The lability of the bond contributes at once to the difficulties attending its investigation and to its extreme importance, so that a linkage, which can be said to be more significant for physiology than any other single structural feature, can also be described as no more than an attractive possibility in protein structure. 7. Van der Waals and other secondary forces. Molecular association is often observed in cases where formation of hydrogen bonds is unlikely. Calculations based on the heats of sublimation of organic compounds give values of the molar cohesion of various groups, ranging from 1 kcal dinyl for the methylene group to 7.25 for hydroxyl and 10.2 for ketornito. The higher values refer to polar groups, including those which can take part in hydrogen bridges. Well-marked association in the absence of the latter usually involves dipole-dipole interaction, or the interaction of permanent and induced dipoles. With stabilizing contributions from dispersion forces, it is clear from the format's ET Table 5 that under favorable conditions, Cly-Former effects, die-ending on the square of the permanent moment, will greatly exceed the latter, and will, moreover, cause mutual orientation of a very specific kind, depending on the Sha-E of the inducing dipole, and on the local distribution and anisotropy of polarizability of the induced dipole. These relations have been interestingly worked out in the case of associations between the lamellar molecules of naphthalene, anthracene, and phenanthrene with various nitrobenzenes, in absence of de moment. As with cohesion between DL2 or CH3 groups, only dispersion effects can be involved. The magnitude of these is difficult to estimate, but there is little doubt of their importance. It is perhaps a good thing at this point to review the subject of van der Waals forces more or less historically. This will lead to a clear statement of the conditions to which the well-tested equations are limited. and even without detailed information will enable us to view critically some of the more reckless references that have been made to van der Waals forces in condensed systems. The fundamental observation is that of the imperfect nature of all real gases, including even the inert gases at very low temperatures. Theoretical and empirical equations have been devised which account for this fact with varying degrees of success, those of van der Waals and Dieterichi, and the semi-empirical power series of Kemmerling and Dies, lying the most familiar. Experimental data are still most frequently expressed in terms of the van der Waals constants A and 6, and it is generally agreed that these correspond respectively to intermolecular forces of attraction and repulsion. The A term of van der Waals' equation was originally deduced by assuming n forces of attraction extending over many molecular diameters, but it was later shown, by statistical analysis of collision frequencies, that the same result can be obtained with short-range forces. The mechanism of the van der Waals attraction probably varies. Giesem-John showed that the temperature variation of A could be well represented in some cases by equations expressing the interaction of rigid quadrupoles. Giving an intermolecular force inversely proportional to Debye introduced a temperature-independent term in R to account for the fact that van der Waals forces do not vanish at high Lemairetures by assuming an induction effect. Neither the Kiesoi nor the Debye effects are, however, applicable to spherically symmetrical molecules, and it is in these cases that dispersion, the detailed calculations, have been made only for hydrogen and helium. But approximate generalized equations for nonpolar gases have been given. It is agreed that the force between the molecules of such substances at large distances can be represented by a function that varies as the inverse seventh power of the distance. Some idea of the Kidget of agreement that can be obtained is given by the data in Table 6, columns 1, 2, and 3. While the relative importance of the three components of residual force in several cases can be seen from column 6 to IGA for the larger molecules, the agreement between experiment and theory is poor. And even for the inert gases, it is not yet certain that there is not an error by a factor of 2 ℏ nevertheless. The formulae have been applied to larger molecules and even to bodies of colloidal dimensions by integrating or summing the reciprocal energies of every pair of atoms in the interacting bodies. The principle invoked here is that the attraction between two atoms is independent of the georesonance of a third. Thus, given the dispersion formula, the question is merely a mathematical one. Such manipulations have given forces varying as where r is the shortest distance of separation. For two spheres in contact, 2πdga, or a sphere in an infinite plane surface, as r for an atom near a plane surface, and as for two plane surfaces, and it has been claimed that formulae obtained in this way justify the assumed tangent obtained. Interparticle attractive forces of sufficient range and intensity to account for the formation of Kosevacs and thixotropic gels. Harnackeren also attempts to show that the forces of attraction between two similar particles are unaffected by the presence of an intervening fluid medium, provided H. Coleman and M. Willstetter Naturwissenschaften 2952-1932. H. Freundlich Clea molecules of this are not oriented. But his arguments are formal ones, and no attempt is made to justify them on physical grounds. Although van der Waals forces are probably not, as a rule, important, e.g. the structure of Schusch's district systems. They do, to a large extent, determine the molecular volume of liquids, Table 6, and in absence of dipole or ionic forces, they are responsible for the cohesion of molecular crystals. The form being determined largely by the Chi-E of the homopolar units, and ALU properties by the strength of intermolecular binding. In particular, the intermolecular distances in molecular crystals and nonpolar liquids usually have the large value 3 to 5a. And the existentius of such spacings is taken to indicate the residual nature of the bind. The crystals are soft, convex resible, have high coefficients of thermal expansion and low heats of sublimation. The simple dispersion formula have been used to calculate the tensile strength of a number of synthetic resins, with results at least one order of magnitude larger than those observed. This has been attributed to the chain resonance of structural faults. Lockerstellin in the materials, dot an estimatia of the tensile strength of cellulose fibers, on the other hand, made by assuming this to be conopposed of the force necessary to tear loose certain van der Waals linkages, and that needed to cause the Streck-Clued molecules to slide over one another, has given results of the same order of magnitude as those observed. This probably gives cause for astonishment. In another case studied by de Boer, he approximate formula gives unexpected agreement with experimental data, namely, in the calculation of the sublimation energy of benzene. One imagines the agreement to be fortuitous, since mole with non-localized electrons probably require special theoretical treatment, while the practice of postulating distributed centers of van der Waals attraction in order to facilitate calculation has been criticized by London. London has, at the same time, drawn attention to the possibility of long-range van der Waals, forces of considerable biological importance between molecules containing regions of conductivity, such as those produced by conjugated double bonds. He makes a start by considering the dispersion forces between elongated molecules of this kind. In these, the virtual oscillators are of low frequency and arc comparable in length to the length of the chain. Their extent is taken into account by separating each into two suitably situated regions of positive and negative density, and the results of the calculation are expressed in terms of the positions of R or Howe Wink, elasticity, plasticity, and structure of matter. Cambridge, 1937, K. H. Meyer and H. Mark, Der Aufbau der hochpolymeren organischen Naturstoffe. These, monopoles in the interacting molecules and the energy of the quantum jump, believed from spectroscopic data to be associated with interatomic charge transfer. At intermolecular distances, very small com, paired with the oscillator length for molecules with similar monopolies in juxtaposition, the attractive force varies as 1 rd. The force on a small spherical molecule near a long oscillator varies as g-r. It is suggested that the existence of such long-range forces operating at widely separated points of attraction along a conjugated chain may account for the elasticity of rubber in contrast to the brittle long-chain paraffins in which short-range one-row forces act between separate atoms. We open this section with a reference to molecular association result in Chen from orientation and induction effects. It should be added that the dispersion effect, to which we have at least by implication attributed part of the lateral cohesion of chain molecules in fibrous structures, and the molecular binding of homopolar molecules in crystals, can also under other circumstances play an important part in restricting the random motion of molecules, and therefore in promoting their morphological organization. Calculations of de Boer, although open to criticism, suggest that in liquid benzene, there may be a tendency to formation of unstable dimers consisting of benzene rings lying in parallel planes about 3.5 apart. This tendency is opposed by thermal motion and by a polarization anisotropy, which would favor another configuration, but there is evidence that the parallel orientation does occur. This is not, however, the configuration adopted in benzene crystals. Intramolecular dispersion forces can similarly give certain configurations a higher probability than others, leading in the case of chain molecules to an average chain length different from that which would be anticipated on the basis of unrestricted rotation about single bonds. Such preferred orientations have been discussed in the case of polystyrene, Chi6H5, where the orienting effect of benzene rings would be expected to play a part. These effects are better understood in small molecules, and even in ethane, studies of heat capacity and vibrational spectra indicate that a potential barrier of 3,000 kmol restricts internal rotation in which the 6CH bonds, projected on a plane perpendicular to the CC axis, are staggered at angles of 60 degrees to one another. In ethylene halides, where dipole forces come into play. Electron diffraction studies show that rotation is considerably impeded in favor of the transisomer. In substituted benzenes, it appears that polar groups impede one another's rotation about single bonds whenever they approach to within about 3/8 long-range forth in mononuclear systems. Quantitative arguments have obviated any need for the assumption of long-range van der Waals forces in explaining the stability of hydrophobic systems. Other biological phenomena have been mentioned, however, which seem at first sight to require some mechanism for the transmission of stimuli to remote points. The best-known case is that of photosynthesis, in which it seems to be necessary. In order to explain the observed diffractional quantum efficiency for a large assembly FAF chlorophyll, molecules in the interior of the chloroplast to absorb for light quantisimultaneously and then to transmit the electronegative excitation energy from one molecule to the next by some sort of resonance effect until it reaches a point on the surface occupied by an adsorbed O2 molecule. Other cases have been mentioned in a recent article by St. Georgi, who seems to suggest that common energy levels associated with the presence of non-localized electrons may be responsible for the transmission of chemical stimuli in genes, muscle fibers, and even through an entire organism. London, whose treatment of long-range monopole forces has already been referred to, has expressed an opinion in this connection that is worth quoting. There can be, however, some doubt as to whether at p(n) cent we are able to survey all consequences of quantum mechanics to such an extent that we could, with certainty, preclude the existence of specifically macromolecular forces which could not be built up by the well-known elementary atomic or molecular forces, but would rather depend on properties of the molecule as a whole. It might be of interest to establish in full generality the conditions under which, in the interior of molecules, such regions of electric conductivity may occur as we have recognized to be responsible for the presence of these characteristic long-range forces. It might well be that still other phenomena and mechanisms are connected with this peculiar kind of intramolecular charge transfer. It is a long step from this to the conducting assemblies of macromolecules suggested by Sedgwick and by Weiss, and still further to the conception of the cell as a whole, or as a single giant molecule as we facetiously spoke of it at the opening of this chapter. Hertzberg, G., Atomic Spectra and Atomic Structure, Prentice Hall, New York, 1937. Molecular Spectra and Molecular Structure, Prentice Hall, New York, 1939, 139. Introduction. The label organization of protoplasm is closely bound up with its colloidal nature. Many experimenters in the past, recognizing the complexity of colloidal systems and finding ample experimental evidence for the belief that reproducible properties can hardly be expected of random aggregates of dissimilar molecules, described colloids and the peculiar forms and reactions of protoplasm very much as a naturalist describes variations among species, as something amenable to meticulous description, but beyond fly reach of CP-generative experimental study. If invited to account for the extraordinary uniformity and reproducibility of, let us say, sea urchin eggs in terms of the extremely variable aggregates of which they are supposed to be composale, they would appeal to some external force, a vital principus or analechy which would impose form and vital fun upon lifeless matter, much as a potter molds his clay, instead of thus confusing increasing complexity with increasing lack of organization. It is probably better to discern in the specificity of colloidal systems the emergence of new qualities which depend for their very existence upon an intrinsic tendency of matter to become oriented both in the geometrical or morphological sense and in the sense of a correlated localization of energy transfers, except perhaps in the experimental study of biological specificity. This view has received no stronger support than in the discovery that the colloidal CT components of living matter can by the mildest methods be resolved into colloidal substances which yet have all the earmarks of chemical individuals. In a majority of cases, they can be molecularly dispersed, and there is an increasing body of chemical and physical evidence that serves to identify these well-defined particles with some of the most highly specific components of protoplasm. It is the purpose of this chapter to review briefly the properties of such homogeneous colloidal substances, without due articular reference to their origin, The common characteristic of immediate interest is their colloidal nature, which implies large molecular size and therefore the use of special methods of study. Important substances of this class are obtained synthetically, and since 65 references in Chapter 7, frequent reference is made to T. Svedberg and K.O. Pedersen and others. The Ultracentrifuge Oxford, 1940, and Advances in Colloid Science, Volume T, edited by E.O. Craner, Inner Science Publishers, Inc., New York, 1942. Solute of these have properties that stand in interesting opposition to many of biological origin they will be referred to. Partial size and shape are the most elementary properties to be discussed. The progress made possible of non-polar, polar, and charged groups will be mentioned, and convergence of physical and chemical evidence to provide a more or less consistent general conception of macromolecules will complete our discussion of these substances, as they probably exist in very dilute solutions. It will then be possible, again, with the utmost brevity and heat completeness, to indicate with a special emphasis upon the behavior of biological fluids and their derivatives, some of the interactions that occur in polydisc earth solutions to it. The delineation of size and shape of large molecules in dilute solution. The determination of inocular size and shape can seldom be accomplished by use of a single experimental method. Moreover, application of a single method usually involves additional measurements often regarded as accessory in nature, but actually as important and frequently as difficult as the machine determination. The results obtained terms by the application of theoretical equations and TSCYD are invariably AI proximate, impose a new uncertainty upon ply errors of measurement. The methods available are of two kinds. By their newtons, one measures either a thermodynamic equilibrium or a velocity. Ply former have the important advantage that, involving as they do, the establishment of an equilibrium between opposing tendencies regulated by the same dynamic quantities, they finally give a measure only of the number of articles present, irrespective of their size and shape. The classical thermodynamic method is, of course, that of osmotic unpressure cryoscopy, being too untrustworthy and vapor pressure determinations usually too inaccurate, in which a mechanical barrier opposes diffusion of the colloidal solute. Scrupulously applied, it is still probably the most accurate, although by no means the most fashionable method for determining the number of particles. It must be recognized that for a colloidal electrolyte, the observed osmotic pressure arises only in part from the colloidal ions, and in part from the unequal distribution of diffusible ions. The relation to the molecular weight is given by a combination of Van Hoff's law and Dalton's law of partial pressures. A, the osmotic coefficient, a function of P, salt concentration, and degree of interaction of colloidal ions in their shape, CMX. The ratio of concentration to molecular weight. Thus, if C refers to dry suslance, Mi is the corresponding molecular weight. The actual molecular weight in solution may be entirely different as a result of solvation. The measurement of osmotic pressure gives the core CT value of Cm, while the correct determination of the molecular weight depends upon a knowledge of solvation. This is, of course, still true when NP and pi have been eliminated, as is customarily done by extrapolation to zero colloid concentration. The same limitations naturally apply to the sedimentation equilibrium method, in which the osmotic membrane is replaced by a gravitational force. There is the added complication that, since the gravitational field is not uniform, it is necessary to measure a concentration gradient. The molecular weight is then given by the acceleration, where C2. Cx are relative concentrations at distances from the center of rotation. O is angular velo. ETV is the partial specific volume of the colloidal solute, d phi L, as Dr. DG, where V is volume and G is mass of solute, while P is the density of the solution. JF2I refers to the unhydrated substance, ml determined by equation. 6 at high dilution should be comparative to the value found by osmotic pressure determinations. The dynamic methods have in common their dependence upon an imposed translational or rotational movement of the particles, or both in opposition to their Brownian movement. All the equations employed must therefore contain terms expressing frictional RE assistance to motion, and these must necessarily be functions of the shock and flexibility, and often also the size of the part. In other words, if the reference substance is the anhydrous solute, it is always necessary to take into account the degree of solvation and the shape of the resulting solvated particle. In general, it is not possible to calculate both these quantities, and until recently it has been customary to express results in terms of an apparent shape factor calculated for a hypothetical unsolvated particle. As far as possible, we shall avoid placing too much weight upon results obtained in this way. Cf. R.E. Powell and H.P. Airing, frictional, and thermodynamic properties of large. The dynamic methods further divide themselves according to the nature of the property measured. In measurement of sedimentation rate, diffusion constant, and viscosity, we deal with properties directly related to the mechanical interaction between solute and solvent, so that all interpretations of these quantities in terms of the properties of the solute must contain some function of a friction coefficient, which gives the frictional force opposing translational motion of a solute molecule as you go, where v is the rate of movement. For the motion of a splutical molecule, Stokes' law gives the frictional coefficient O as where T is viscosity, R radius of the molecule, and Avogadro's number 6.06 Gh10, and molecular weight V partial specific volume. If each article is not spherical, is some other function of Shaw-E. The functions for both elongated agide flat ellipsoids of Revolution, rolls and disks, in random configuration, have been derived theoretically in the form where O is the frictional coefficient of a sphere volume and A, H are the axes of the ellipsoid. Jog these equations are applicable to measurements in which orientation of the solute molecule does not occur. In the second group of dynamic methods, namely, the measurement of dielectric dispersion and streaming double refraction, the effects observed depend similarly upon a frictional coefficient, in this case representing the force opposing rotation, and defined by Fa, where A is angular velocity. For rotation of a spherical molecule, while for an ellipsoid of revolution, any mode of rotation can be expressed as the resultant of components of rotation of each axis about the other, each with its own frictional coefficient, Fa and F. It is convenient in practice to replace the friction coefficient by a closely related quantity, the time required for a system of oriented molecules to regain a certain degree of random distribution when the orienting force is relaxed. This is known as the relaxation time, and for a spherical molecule is given by where K is Boltzmann's constant, 1.372 Joule. Deg 0 for ellipsoids of revolution. The values of TA and RT have been expressed in terms of the axial ratios by equations analogous to 8, where again T refers to the equivalent sphere and can be calculated from equation 10. We can now consider more explicitly the various experimental methods. The instrument that has probably contributed most to the physical knowledge of large molecules is the ultracentrifuge, the use of which in determining sedimentation equilibria has already been referred to. Before such equilibrium is attained, the rate of sedimentation during centrifuging can be determined and expressed as a sedimentation constant 9, defined as the rate of movement of the substances dx in a field of centrifugal force. Equating centrifugal and frictional forces gives the expressions where the symbols have the meanings previously assigned to them. The suffix 12 referring to the actual solvent-solute complex comprising the colloidal kinetic unit in solution. And 1 to the unsolvated molecules, it is easy to show that approximately. Hence the use of Ti and Mi, obtained by some other method, in conjunction with the experimental value of S, will give the correct value I2 for the frictional coefficient of the solvated molecule. The calculation of a shape factor by use of equation 8 is, however, not possible unless we know OI2UA, the frictional coefficient, for a spherical molecule of molecular weight μ2. If W is the number of grams of solvent bound to 1 gram anhydrous substance, it may easily be shown that for a very dilute, where the fraction 2001 is the value usually, and erroneously given as the frictional ratio, dearly, we must have some independent way of finding IV, the hydration, if the correction factor G is to be applied. The molecular weight, Mi, is often obtained from the sedimentation constant by inserting in equation 12 a value of 12 calculated from the diffusion constant D. The information gained from viscosity Nick assurance, even at great dilution, is far more uncertain. It has been shown repeatedly that elongated particles form more viscous solutions to ion spherical ones. But the precise relationship between viscosity and shape is still uncertain. Many of the equations that have been suggested arc of the form where Rj and Rho are viscosities of solution and solid respectively. D is partial specific volume. C is concentration in G loose centimeter, and K is a function of particle shape. The practical determination of K is best done by extrapolation, since in many cases deviations from the simple Chi proportionality of equation 16 occur at quite low concentrations. Accordingly, we may define for spherical particles K is equal to 0.025. Add for ellipsoids of revolution. A theoretical expression for K obtained by Simon has Eud with H, some succi S. In application to proteins, the correct application of any equation, however, requires the use of an appropriate value for partial specific volume, and hence, as in all other methods, a knowledge of salvation. The correct value of in equation 17 is an empirical equation relating intrinsic viscosity of a number of proteins to axial ratios derived from sedimentation, and diffusion data, equations 12, 15, and 8, has been given by Poisson, working backward. Poisson, then A.E.O. Kramer and W.D. Lansing, Nature 133, A.O. Kramker and Statement in H. Mark, Physical Chemistry of High Polymeric Systems, Inner Science Pub Inc., for a discussion of other viscosity equations. See, for example, H. Mark, Physical Chemistry of High Polymeric Systems, Irritor Science Pub Inc., New York, 1941, pages 255 F. Key derives the molecular weights of a number of proteins from their intrinsic viscosities by means of the same three equations. The values of A6 obtained during T-Lyas procedure are not to be taken seriously since hydration is ignored, but the method may have certain value in determining M approximately when sedimentation data are not available. The determination of molecular weights by interpolation from viscosity measurements is possible only in cases where a number of members of a polymeric homologous stories have been examined. The equation of Stand and Johor, which may be exhaust-rest in the form, where Z is the degree of polymerization, K is a constant characteristic of a given homologous series, was derived for rigid rods with effective volumes qual to the volume of the disk described by rotation of the long axis of the rod. Other evidence, theoretical and experimental, suggests strongly that linear polymers are flexible or worm-like structures. This greatly limits the theoretical value of Staudinger equation, the experimental study of molecular rotation, and the interpretation of the data, CP. Equations 10 and 11 are difficult. This applies especially to the results of dielectric dispersion measurement because of the extreme generality of the Debye equation for the relaxation time, which will apply to any property which measures how much a system changes from one state to another when a periodic force is applied, and which in almost any system could result from one of or a combination of several different mechanisms. In the simplest case, the quantity derived from dispersion curves for dielectric constant or conductivity is a single critical frequency. The frequency at which from this we can calculate a single relaxation time are provided the relation between polarizability and dielectric constant is known. In many cases for solutions in polar solvents, the relation is linear, and then if the solute molecules are known or suspected to have dipole structure, it is quite probable that the measured relaxation time is coequal with the rotation of dipoles. in a viscous medium under Tlie influence of the PP Light field. And this interpretation can in many cases be supported by outlier evidence, particularly when the structure of the molecule is known in some detail. It can be determined whether or not the observed relaxation time is compatible with rotation of a SSI8 Recal unsolvated molecule, or with oscillation of a single group, or whether a solvation shell or a non-SGG dichroical shape must be assumed to account for the observed values. The Lattice case can occur if the second relaxation time is associated with a very minute dipole moment. It is usual to find the dispersion effect spread over a wider frequency range than that required by the Debye equation, and it may be possible to attribute this to the modes of rotation of an ellipsoid of revolution and to calculate the axial ratio, the molecular volume, 3F, the direction of the dipole moment vector, and the hydration. If two relaxation times are insufficient, other interpretations are possible. In the rays of thread-like molecules, there may be many relaxation times, because in the various configurations which a chain molecule can assume, we can find now one, now another segment of the chain acting effectively as a cooperating electrical two-unit relaxation mechanisms have been considered. The only one which appears to require careful consideration in connection with protein solutions is that discussed by Fricke and Jacobson, whose measurements on the dispersion of gelatin solutions and the effect of electrolytes and pH changes led to the conclusion that neither the orientation of dipoles nor the Debye-Falkenhagen effect could wholly account for the results observed. The important mechanism, according to Fricke and Jacobson, is similar to that operating in coarse suspensions, and is connected with some are enumerated by Powell and Eyring in Ref. 65. Relaxation of Debye-Huckel ionic atmosphere. Compare H. Falkenhagen electrolytes, 1934. Polarization of an interface consisting probably of oriented water molecules attached to the particle surface. Whereas in measurements of dielectric dispersion, only a very small proportion of solute molecules is actually affected by the field. The measurement of streaming double ref action depends upon the mass orientation of particles. The orienting torque is applied hydrodynamically by a velocity gradient at right angles to the direction of flow, and the degree of orientation, subject of course to a distribution law, is a function of the velocity gradient and the relaxation time of the particles. The intrinsic optical anisotropy of the particles is merely used as the index to the degree of orientation, and the optical quantities measured as a function of the velocity gradient must be interpreted theoretically in terms of a relaxation time, from which in turn Shaughnessy factors may be obtained by the application of equation. The method has given valuable results for elongated molecules with large relaxation times. It has only recently been extended IO molecules, which are also amenable to study by dielectric dispersion decuinations, essentially. It is too early to attempt a final estimate of its accuracy. 3. The Ively-Journet of hydration. Without a knowledge of hydration, the sliopy and size of molecules in solution are not susceptible to precise definition, unless T molecules are so elongated that the effects of shape narrowly outweigh the effect of any possible degree of hydration. Exact size and shape may indeed always defy definition, for the concept of hydration is itself manifold. Little effort has been made to reconcile the conflicting and certainly too circumscribed points of view which have bred unnecessary controversy. From the unique character of water, it must be evident that there may be many degrees of hydration, ranging from mere mechanical entanglement to the close-packed structure of dielectrically saturated water, QV, in an intense electrostatic field. The subject has never been adequately reviewed, nor has any sufficiently compared Hernal and it. Coller's discussion of IHC dielectric constant of ice, FCBM, Phys 1. A number of early papers bearing on this question are discussed by E. Heyman, Colloid, Check 66, 229, 1934, including those of Picara and of Amerkra, which cannot be dealt with here. The mode of packing of water molecules into cavities has been interestingly discussed by Batsia Obluha Protoplasma 381, 1927, DTC Barnes and TL Jan, Court River. File 9, 292, 1934, CH Mark, Reflu DRA, Gortner, outlines RF biochemistry. Comprehensive experimental study been made during the years in which other physical data concerning large molecules in solution have been accumulating. The resulting uncertainty of definition of various molecular magnitudes stands in contrast to the remarkable engineering skill and patient measurement that have given accuracy to many of the primary empirical quantities. Thermodynamic methods have obvious disadvantages in non-ideal systems. The experimental data are in many cases reliable, but their interpretation may be dubious. In a number of investigations, the activity of water has been varied by mechanical pressure across a semipermeable membrane, or by changing Eiley water vapor pressure at constant temperature. In others, by lowering the temperature XAS to an atmosphere of constant water vapor pressure, a specimen will eventually attain a constant weight. Liage can be measured, alternatively exposed to a constant temperature below its freezing point. A substance containing free water will in general separate into pure ice and an aqueous, e.g. haze or phos, of definite composition. And the amount of ice formed can be determined by measuring the heat of fusion or the volume change, accompanying or sometimes by weighing the ice extruded on the surface of a thin slice of the material at the average composition of the residue can. To be determined if its original composition be known. For a simple solution of sodium chloride at room temperature, a continuous series of equilibria between water vapor and salt solution is established as the water Va or pressure is reduced until it reaches a value slightly below 4 millimeters. Hg. At this point, equilibrium is attained only when all the water has evaporated. At all lower vapor pressures, the system is invariant. Similarly, on cooling, a series of equilibria between ice and solution is established until the temperature is below, when a mixture of salt and ice separates out, and the system becomes entirely solid. Most colloids show a different behavior when the activity of water is lowered. An electrolyte-free gelatin gel for M. Rubner, Abiach Prus, Acadwis. Number 1. Water G gelatin on cooling to about, and the composition of this solid solution does not change significantly on further cooling to analogous observations can be made when the water activity is reduced by other methods. Although in some cases these give a somewhat less definite plateau. Morin considers that the water content of the soluble solution of nearly constant composition represents a strongly bound fraction of the water, while at higher activities of water, a further considerable amount is more loosely bound. The state of the latter J-ortion has not been at all clearly defined, but in some sense the interpretation of the plateau may be a correct one. Dietrich provided the curves represent true equilibrium states. IES has been very plausibly doubted, although the objections may be equivalent to the ostensibly opposed point of view adumbrated by Morin. Single points on the vapor pressure isotherms of some solid proteins have been obtained by Rui. Amount of water bound by a protein is probably reduced by the gyrosine of neutral salts or other crystalloids. The bound water were also non-solvent water. The latter property has been used, perhaps rather naively, as a second criterion of water binding, the amount of bound water being calculated by comparing the apparent conquit of solvent water with the total water determined by drying. The former can be found by measuring the effect of added soluble substances on the freezing point or vapor pressure of the system. If it be assumed that the colloidal or other components do not absorb or otherwise modify the activity coefficients of the various substances present, and it is only with very simple solutions and carefully chosen test substances that, if ever the method can be trusted, it may be doubted whether any accurate data have been published. A variant of the method has been applied to solid proteins by Sirorensen and others. Analyses of mother liquor and of protein crystals with adhering mother liquor often show the presence of a higher proportion A.R. Newton and R.A. Gortner, Botmer. Gaz 74 442 1922. B.R.I. Kreit and K.C. Winkler, Z. Chishirtarf Anorg. Al Jem Henro 88 200 1930, C.A.V. Hill, Proctor Roy. Dosuki Ranazanon 6B 477 1930, D.E. Hatchek TR Faraday Asak T 32 787 1930 uses inability to hydrate anhydrous cobaltous chloride as an index for bound water in gelatin gels. The results, hydration around 0.5, are in agreement with those of Moran, but are perhaps open to other interpretations. 11 SPL Sironensen, Comte Red, Detrap Dulab. Carlsberg, 12, 164, 1917, of water to salt in the crystal than in the mother liquor. Adair and Adair have used Sironensen's distribution data to calculate the hydration of several proteins, with results again falling in the range 0. In a further slight variant, it has been found that a gram of dry silk fibroin immersed in a solution of the disaccharide trehalose adsorbs, about 0.2 g pure water. The surrounding solution becoming more concentrated from the equilibrium distribution of glucose between protein residue and ultrafiltrate, on the other hand. Much lower values have been found for castin, 0.01, IEMA gelatin, 0.05. This might, however, result from conjugation of glucose with protein. It is often found that there is excess salt instead of excess water in protein crystals, although there is evidence that the hydration of protein crystals is amenable to more exact study if there is reason to believe that all the water in a well-defined crystal takes part in the structure of the crystal. GDS is MT necessarily so. It is possible for water to exist merely in cavities from which it can be removed and replaced by air without disrupting the crystal. In recent studies of I-actoglobulin, it has been shown, however, that the unit cell shrinks when the crystal is dry due to a proportional change in crystal dimensions takes place. The change in volume is very nearly twice same as that of the water lost on drying, 84. And other evidence lies been given me that the dry crystals are Kamov, act, and free from air. Comparison of the densities of the wet and dry crystals, measured by a flotation metliod with organic media, leads to a similar value for the hydration of 3-lactoglobulin application of Estranceres method, however, gives 0.294, suggesting that the bound water is present in two forms, only one of which is available as a medium for the free diffusion of dissolved substances. Calculations of hydration from crystal densities were given earlier for a number of proteins by Adair and Adair using aqueous flotation media. Exchange of dissolved substances between medium and crystal water undoubtedly leads to changes of density, and it seems probable that the lower hydration values obtained in these experiments are in part due to this source of error. Stress this point in discussing the relation between the degree of hydration of proteins in the crystalline and dissolved forms. They all point out that values found when the activity of M. Searer, Art Ensign, and A. H. Palmer, Comp. Ren D. Trav. Dulab. Carlsberg, 21, 283, 1938. Water is low or likely to increase at the higher activities existing in solutions. Moreover, since inorganic ions can diffuse into the water of hydration of the crystal, the environment of the protein molecule in this condition corresponds closely that in solution. The former thermodynamic argument should not be unduly stressed, since the state of the protein molecules in the crystal can certainly not be defined in terms of the thermodynamic constants that are applicable in dilute solution. Krofutun considers that only part of the crystal water is likely to remain in association with protein molecules dispersed in aqueous solution. We have seen subsec 2. How hydration can be calculated from dielectric relaxation data if the molecular weight of the anhydrous particle be known. A few values calculated in this way are given in Fable 7, although they should be regarded as tentative. Some, if not all, of the water which is associated with the rotating particle in this way exists presumably in an oriented close-packed state in regions of high epoxy tile gradient. Water thus oriented loses its high permanent moments and can be distinguished, in theory at least, from diastetrically free water by reason of its smaller contribution to the polarization. The total polarization of a solution thus consists of Haas 3 additive components, resulting from the free water dielectric constant around 80, the oriented water dc around 2, and the Ardidrous solute. In J-rinsable, it should be possible to calculate the hydration from the dielectric constant of the solution and of the dry solute at frequencies high enough to eliminate any contribution from the permanent moment of the solute molecules, provided a satisfactory relationship between polarization and dielectric constant is available. The classical Clausius-Mazzotti ecipiation has been employed by Marinesco and others in such calculations, but there is reason to believe that for many polar solutions, this should be replaced by an empirical expression. Marinesco's results are thus. Doubly in error, for the difficult experimental methods are not beyond criticism. Nevertheless, some of the results are included in AREF 70 pages Loof. Attempts to demonstrate the low dielectric constant of oriented water have not been very successful. In electrolyte solutions, any such effect of hydration is masked by the Debye-Falkenhagen effect. B2 Kuhlmann and K.E. Dorsch, UHEM, 126, 305, 1927, as a result of direct measurement, consider the dielectric constant of a water layer 5. At the time, platinum surface to be greater than 40. Compare, however, C. W. U. Rallmer, Procuroi, SOK, 55, 1924. D.B. Derjagen. TR information obtained by other methods tends to be scanty and uncertain. Numerous qualitative observations have been made on G-cladding systems, which have suggested that the phenomenon is closely associated to vapor pressure, iotherm, non-solvent, water, vapor pressure, depreciation, freezing point depression, X-rays, shrinkage of unit, cell, high-frequency dielectric constant, electrostriction of solvent water content of crystals. The methods are identified more exactly in text. Air-dried specimens, values probably too low for T water activity too low for combination with anhydrous cobaltose chloride. With water binding, but it has been shown that neither dielectric constant changes measurably during the process. While anomalies in viscosity and diffusion constant are probably due to molecular asymmetry and the tendency to net and chain formation rather than to hydration. Neglect of these factors sometimes leads to remarkable conclusions. Harn-Marston, for example, has stated that all the water in a 0.5% solution of sodium thymonucleate is bound similarly or such phenomena as the absence of Brownian movement in certain bentonite suspensions and the high sedimentation volume of talcum. Powder rang, probably due to electrical repulsion between particle stand and not to solvation. X-ray analysis has to some extent revealed the position of water in fibers and protein and water binding by formation of hydrogen bonds, has been suggested from a study of infrared spectra. But in the case of gelatin, it appears that they are at least consistent with a hydration of about 0.35 di. It will be seen from a perusal of the data in Table 7, which is very far from exhaustive, that despite the diversity of criteria for bound water, a fair degree of consistency among the values found warrants the conclusion that hydration is by no means a negligible phenomenon. For Esquiva crop, routines at JRIU is 0.2 to 0.5. Although there are certainly plenty of discrepancies calling for resolution. If, as has often been suggested, the water of hydration exists in two fractions, each with its own properties, it would be surprising to find complete agreement among the data. This is a dangerous, if plausible, statement, and the extreme skepticism of some reviewers is perhaps due to a feeling that such a flexible idea can be too readily used as a mask for experimental error. Experimental results relating to size and shape of large molecules in solution. We can differentiate two kinds of dissolved macromolecules, linear polymers and globular molecules. The former are flexible thread-like particles, ideally unbranched, but often complicated. They may be tightly coiled threads, the tight or the spongy spherical clues of Signer, very highly Brankleyed linear polymers with interacting segments which produce rigidity, or strictly three-dimensional covalent lattice structures of varying degrees of regularity. These last tend, however, to be self-perpetuating and to give rise to insoluble masses, homodesmic in the sense of Chapter 6, such as the resins. They need not be considered here. The two classes naturally overlap. Some elongated molecules are not simple threads with a single polymeric backbone, but have a more elaborate internal structure which lends rigidity and causes the particle to behave more like a stiff rod than a thread. This provides an important practical distinction, for rigid molecules are much more susceptible to exact description than flexible ones. We must mention also the important accidental circumstance that while, for reasons that are not in the least understood, many naturally occurring molecules can be obtained in the virtually monodisperse condition, some degree of polydispersity of size and shape is almost universal in solutions of synthetic or natural linear polymers. On the other hand, the latter had the advantage that they are formed from relatively simple re-eating units, so that average molecular weights and average degrees of branching can frequently be determined by chemical estimation of free terminal groups. In the case of the globular proteins, which may be regarded as heteropolymers, although some evidence as to molecular weights can be obtained from chemical analyses, the physical data are at first sight completely at variance with the chemical and have to be considered on their own merits. Because of the comparative synergicity of the physical data, let us consider first the globular proteins. To a first approximation, all physical methods properly applied support the lemma that most soluble proteins, with the notable exceptions of myosin, fibrinogen, tobacco mosaic virus, and perhaps gelatin, behave in solution as more or less hydrated rods or spheres of definite molecular weight. Numerous molecular weight measurements have served to establish the range of molecular sizes encountered and to demonstrate a somewhat remarkable uniformity in the values found for particular proteins from a given source. Beyond this, and a further tendency for the molecular weights of chemically similar proteins to fall sometimes within the same range of values, there is really very little regularity to be discerned, especially in relation to the extraordinarily wide range of biological function covered by these substances. Proteins with widely different functions may fall within the same molecular weight range. Others with apparently identical function and apparently close chemical similarity, such as the antibody globulins or the respiratory pigments from different species, cover a considerable range of molecular weights. Association or attachment to indifferent carriers might be suggested to account for this. And indeed, there is the remarkable reversible splitting of proteins in presence of urea, glucan, and certain amino acids to favor the hypothesis, as well as the alleged grouping of molecular weights in multiples of the basic unit of 17, which has, however, been disputed, but there is no direct evidence. The shape of protein molecules has been discussed on the basis of all the methods outlined IP subsection 2, but without proper allowance until recently for the hydration factor, thus somewhat extreme points of view. Workers of the Svedberg school and others, as a rule, gave the conventional frictional ratios, GO, or the intrinsic volumetric viscosities based on the partial specific volume of the anhydrous solute, from which they deduced axial ratio. Adair and Adair contended that in several cases, at least, the apparent asymmetry vanished if hydration was taken into account. A review by Onkley of the most trustworthy available data suggests a less extreme point of view. Doubt G for each routine and aromatal method Onkley hydration against axial ratio in such a way that any pair all values of these variables falling on the curve E represents a possible incarnate rotation of the data for the method in question for a given protein. The curves obtained for all methyphols often tend to intersect in a certain region. The values of hydration and axial ratio in this region are those that agree with most, but not necessarily all, of the experimental data, and may therefore be adopted tentatively. Some of these, taken from Oncle's diagrams, are given in Table Vol together with the experimental values upon which they are based, and for comparison with selected values of hydration determined independently, compare Table VH chart. The results have been weighted in favor of the X-ray data, since any value of the axial ratio must conform to the dimensions of the unit cell. Due for this reason, insulin alone among the proteins considered is best regarded as a disk. As a convenient bridge to a discussion of linear molecules, we may refer to certain classes of polysaccharides, the structure of which can be inferred independently from chemical data. These form a series starting from glycogen, with an elaborately branchial structure and short averages chain length, passing through the progressively less branched arnylopectin and amylomylose, the two principal constituents of starch, to cellulose and its derivatives, which are essentially linear. The polymeric unit is in each case tripyranose ringed. The transition is marked by a progressive increase in intrinsic viscosity, by an increase in frictional ratio, and by the appearance in cellulose of streaming birefringence. Other effects become evident, notably a iron-ounce tendency of the sedimentation constant to fall off with increasing concentration, and for the osmotic coefficient to rise. These effects, which may occur at such low concentrations as to interfere seriously with the extrapolation to zero concentration, upon which reliable molecular weight values must be based, are highly characteristic of thread-like molecules. Even when the extrapolation is performed, S may be practically independent of molecular weight and account of the increase of frictional constant with chain length. Thus, molecular weight determinations become difficult and are further complicated by the polydispersity of nearly all linear polymers, which causes the sedimentation boundary to become very diffuse. Methods have been developed for calculating weight distribution curves from the boundary diagrams, sedimentation rate, and partial specific volume, V relaxation times, love, volumetric, intrinsic, vis apparent frictional ratio, most probable hydration, experimental, axial ratio from X-ray, axial ratio from electro. A similar situation exists concerning shape factors, for linear molecules can exist in an enormous number of configurations, and attempts to represent them in terms of rigid ellipsoids are highly artificial. The results can only represent, in very crude terms, an average configuration. This is clearly shown in the data of Kramer, who compares axial ratios obtained in the conventional way from viscosity and sedimentation, data with those corresponding to the fully extended chain. Some representative figures are given in Table 9. Probably the proteins included in the table are less flexible than true line or polymers, and therefore more accurately described as ellipsoids. To some extent, these thread molecules seem to function in independent segments, each with its own Brownian movement, behaving in some respects as separate molecules of low molecular weight, in others as a macromolecule. The anomalies of osmotic and vapor pressure arise in part from the former effect, while the viscosities of polyesters in the molten condition and in fairly concentrated solution acquire, for their interpretation i.e. to combination of a term involving flow in segments, with one expressing the condition that the random motion of segments shall be coordinated in order to result in movement of the WIO molecule in the direction of flow. The latter condition would not apply in absence of translational motion. Dielectric dispersion data should give information as to the modes of independent oscillation or stretching of polar chain segments, but would not be expected to indicate. In absence of special theoretical treatment, the Sizer-Shah E of the macromolecule. We have referred Closwedier to such a theoretical treatment of this question. It is worthwhile to mention some results obtained in the experimental study of simple linear molecules in solution. 1DH might be expected to show clearly the effect of oscillation of segments, uncomplicated by polydispersity. A lot depends upon the geodesy of the polar groups. Aliphatic alcohols with a single Euler group behave as if only a small segment, perhaps an O group, were free to oscillate W-dual linear molecules with terminals with T. such as the simple peptides and betanes, seem to behave far more like rigid molecules for which Liouville shape constants can be calculated. Thus, the axial ratios for the glycine peptides appear to be proportional to the square root of the number of residues. This behavior appears to hold for peptides up to alanoleucoglycinion for heptadisylbetane. WH is reported to act like a sphere of diameter equal to the length of the fully extended chain. The reason for this is not at all clear. On the other hand, when there are distributed Zwauderians or polar groups at intervals along the chain, and independent oscillation of segments, as the data on poly-W hydroxydecanoic acids show, actual distribution curves have not been obtained for any of these substances. For larger molecules such as the vinyl polymers, an average relaxation time given by the frequency for maximum loss factor, E, has been found proportional to molecular weight in Tane R.E. Powell and H. Earing, Ref 65, P. 183, B.K.H. Meyer and R. Luediman, variety with the theory of Kirkwood and Foss-Steinand. In none of these cases are exact calculations of segment lengths possible without a more precise knowledge of the relationship between macroscopic and molecular viscosity. The irrelevance of the former in calculations involving rotational motion has been shown quite clearly, and GTN is particularly obvious when the molecules of solid substances are able to rotate freely. Comparisons of the free energies of activation for viscous flow and for rotation likewise suggest that rotation is often much easier than translation. 5. Number and distribution of charge groups in protons and their relation to chemical constitution. Neither the diversity nor the general properties of the proteins can be adequately explained by differences in the size or shape of their molecules. Knowledge of size and shape can only provide the framework for a chemical topography, of which the elements are already in existence, and as this grows in detail, we may hope to observe the gradual convergence of our knowledge of chemical and biological specificities. Underlying the rather definite size and shape of fractionated protein molecules, there must be an ordered arrangement of euchoolomeric units. The flow nature of the units and the elementary plan of polymerization are, in fact, fairly well known, but the resulting model of the protein moleid is so much at variance with its polarities that there must be a secondary structural principle, the nature of which is still not understood. There is wide agreement that the important Je dimeric unit is the peptide linkage RHEONH, and that the immensely varied properties of the proteins depend largely upon the nature of the side chains. The chemical evidence shows that if this structure is substantially correct, the side decans cannot be identical throughout the peptide chain, since amino acids in considerable variety are obtained by the hydrolysis of proteins. In no single case has the entire protein molecule been accounted for in this way. But this is not surprising, since according to Vickery, adequate quantitative methods exist only for 9 amino acids, and somewhat less satisfactory ones for 6 others out of the 25 concerning each. There is no doubt whatever, while there are yet others which may be present. Table 10 summarizes data for several proteins selected from studies that show evidencia of unusual care and attention to controls. It will be seen that at best, the figures account for only about 60% of the protein molecule. In the case of insulin, only for 12%. More complete analyses exist for these and numerous other proteins, but are not considered reliable enough for use in the calculation of molecular weights. The minimal molecular weight given in the table is that implied by expressing all the molar concentrations as integers, taking the smallest values consistent with the experimental figures and their probable error. 70N values in the table have been obtained more or less in this way. 71E agreement with QL values of M is as satisfactory as Eoid bid expected. Mere increase of molecular weight does not, it is clear, give rise to any such continuous change of neutralities as is encountered with simple polymers. The multiplicity of SID chains attached to the backbogics, however, suggests an explanation. For it is obvious that the relative numbers and the set meaning of the individual amino acid residues can be almost infinitely varied. Ideas have been made to show that AC-Tooley neither number nor sequence is entirely arbitrary, and it is scarcely conceivable that this should be so. In the relatively simile case of the protamine, formulae have been given involving an imperfectly reheating unit, and more recently, Eigerman has claimed that the molecules of various proteins fall into classes containing a definite number of amino acid units, which may be arranged in such a way that each individual residue repeats itself throughout the protein molecule with a regular recurring frequency. It would appear from the published criticisms of this hypothesis and of experimental data underlying it that such a rigid periodicity has not been demonstrated. Cetane, the residue numbers given in label X for egg albumin do not agree very closely with the values 2X claimed by Bergman. The structural principles involved are probably more complex and are unlikely to be amenable to such singularly arithmetical expression. Up to a point, the u-properties of the proteins are those of the structure described above. This is particularly true of their amphoteric nature. The side chains behave chemically as if they were free. Naturally, in absence of complete analyses, this cannot be considered rigorously established, but as a rule, the acid and base combining power suggests the presence of more rather than of fewer reactive groups than those found analytically. A complete quantitative correlation is hampered also by our imperfect knowledge, for example. AAA, Nieborger, Frock, Roy, Soki 27B 25 1939, H. R. Bull in Advances in Enzymiology, edited TFF Core in H. Workinen, Interscience Pub Inkersign R. H. Workinen, Interscience 42. R. I. Hotchkiss, J. Bile, Genie 131, 887 1939. D. Wibnold's Bakerian Lecture V. U. Hein, Noel Pertin-Royce. Soki 131B 136 1942. I think that those interested in proteins would be wise to regard the Bergen-Nieden hypothesis as still tentative. For much of the evidence hitherto brought forward to Sweetport, it has been based on inadequate experimental data and has demonstrated nothing more than the hypnotic power of numerology, of the change in electrochemical properties of amino acids resulting from their incorporation in the peptide chain and by the combination of other ions than those of water during titration. Nevertheless, some progress reviewed elsewhere in this volume has been made in the analysis of titration curves in terras of the amino acid residues responsible for them. The instructive work of Sims was of preliminary value. The data on egg albumin, more recently analyzed by Hannon, illustrate the present situation with its rather more refined electrostatic theory and its leaven of empiricism. In this instance, Cly analytical figures give too few acid gauges to account for Cly titration curves. But in other respects, the agreement is good, perhaps surprisingly so. It is remembered that only 46% of the molecule is accounted for analytically. It would follow qualitative Eli that if the net charge V varies with pH as a result of ionization, the mobility in an electric field must vary also. This is indeed the case, and fairly close proportionality between titration and mobility data has ETCNM found. Calculation of net charge for mobilities is, however, difficult. Several factors have to be taken into account, such as the electrostatic screening effect of the DCC by ion atmosphere, its effect on the viscous flow of solvent, the influence of particle asymmetry and nominoform distribution of charge, and the possible binding of specific ions. Preliminary work has been done, taking the above-mentioned J proportionality for granted, in the calculation of shape factors, with results that agree fairly well with those of other methods. Table GI. However, lies more in its use as a very sensitive indicator of small differences in the charged condition of proteins and in the analysis of polydispersed systems, such as plasma, than as a source of absolute values of the net charge. The Gibbs-Donnan distribution law also provides methods for measurement of valence, either by the analysis of osmotic pressures or by measurement of membrane potentials. The latter, in particular, has been advocated with considerable success by Adair and Adair. Ultimately, the effective charge on a protein molecule varies roughly in the manner shown by the titration curve, becoming zero at the isoelectric point. The dissociation constants of the various groups present overlap in suculi, a way that the total number of charged groups is not zero at this point. The number of electrically balanced charged groups is maximal, while the total number of charged groups, balanced and not balanced, is maximal at some pH, not necessarily identical with the isoelectric point. The maximum in the number of dipoles J present at the isoelectric point does not mean, however, that the dipole moment is likewise maximal, since Telle's quantity dD depends upon the distribution of charge. A molectile with very symmetrical charge distribution might have a very small permeate moment at any given pH. But in GTL1, would expect Pli symmetry to vary with pH, so that a choimol might be either unique or arcane-existent for a particular problem. And here are very few situities of the variation of dipole moment with the ion. Though such information might be useful in plotting the distribution of polar gouges on the protein surface, the moments of a number of isoelectric properties are well known, however. In the case of non-spherical molecules, assuming the zwitteriorial region of the moment to be established, relaxation study should provide a further characterization of the moment at various PLL values in terms of the angle between the electric and the geometric axis. The moments record vary from IRESU for egg albumin to P200 to T through O for horse serum pseudoglobulin. The angle between the major axis of the ellipsoid and Pli dipole moment vector being estimated in the latter case as 45 Kelvin. The moment of egg albumin is that expected from a singly charged dipolar ion with a dipole aspiration equal to the diameter of the molecule. This value represents a highly symmetrical distribution. These facts are in accord with the Sim-J polypeptide structure of proteins, according to which the amino acids are arranged in lines, with charged groups attached to side chains at various points along Pli line and distributed sufficiently at random to give a very small resultant electric moment. This picture is, however, at variance with the dielectric dispersion. Sedimentation and viscosity data, which show that the molecules behave as more or less rigid spheres or rods. Moreover, the preponderance of nonpolar groups in the polypeptide model is such that proteins would be practically insoluble in water if they had such a structure. The conclusion forces itself to that the chain is folded and folded in such a manner that the acid and base combined in groups are either free or very weakly bound, while the nonpolar groups are to some extent enclosed. The reversibility of titration curves within certain limits proves that even if there is a certain amount of side chain interaction, it must be supplemented by some other type of binding, since there is no evidence that the molecules assume an extended configuration at acid or alkaline reactions. Degradation of the extremely sensitive protein structure without change of molecular weight can be caused by many means. There is good reason for thinking of the processes involved as the introduction of disorder into an originally VT regular iris fracture, to use Langen-Ur's phrase. And since there is an almost infinite number of possible configurations of a polypeptide chain, folded or contoured at random, it is not surprising to find comparatively little agreement as to the precise nature of the Ju product obtained by the action of the various denaturing agencies. It is certain that the product has usually lost the most highly specific of its original proper, sometimes irreversibly, as in the case of antibodies, sometimes reversibly, as with proteins, including certain enzymes and antigens. It is certain also that the product is often more viscous and therefore less symmetrical and less soluble than the native material, that it contains free side chain groups, tyrosine, hydroxyl, tyrosine, sulfhydryl disulfide, that were not originally detectable. On the other hand, it is a matter of dispute whether the titration curves and the electrorestriction of water achieve different proteins and denatured proteins. It seems probable that such changes in the former as occur are due to changes in the titration constants and not in the D. The facts have not proved sufficiently definite or unequivocal to favor any clear picture of the structure of the native protein. The one coherent hypothesis postulates covalent polymerization in 2 dimensions, made A.E. Mirsky and M.L. Anson, J. General Pfizer Siol 18, 84-5, B. 7, 1984-5. Ibid 19, 427, 1986, C. Ibid 19, 439, 1986, D.J. Pierre Priestide, J. Bile. Churn 126, 501, 1988, Ibid 128, 233, 1939. F. Ibid 130, 519, 1989. G.R.M. Horiot, Ref 172. H.A.E. Mirsky, Cold Spring Harbor Simp, 6, 157, 1988. I.J.T. Edsnell J.P., Arians Larry, and J.W. Mull, J.M. Cheney T. 61, 1618, 1939. J.J.P. Grunstein and J.T. Edsel J. Bilehem. 133, 397, 1941. K.J.T. Edsel and J.W. Mel, Ibid, 400 and 1940. Possible by iolization of the peptide carbonyl group, the resulting cyclo network can be folded joint and TO polyhedral cages. The hypothesis appears to be too much at variance with experimental facts. To find wide acceptance, it is admirable as a piece of ingenious crystallography. But as a vehicle for the diversity of the proteins, the cyclo cage seems remarkably inflexible. Whatever the stereochemical situation may exist, certain from entropy and energy considerations, that many WAK bonds are involved in the maintenance of a protein molecule in the native condition. A few of these may be covalent, such as disulfide or acetylcholine peptide linkages between side chains. But most are of residual character and may be salt linkages or hydrogen bonds. Idle latter appear to be panzea in solid protansin presence of water. They would tend to become disrupted, a convoluted peptide chain, LUD in a specific configuration by a number of such linkages, might still have a certain Nernst of degrees of fractium without loss of SSI specificity, but if a sufficiently large number of bonds were broken, genetically all specificity would be lost. If the unfolded chain be imagined restored to its original environment, one may conceive that in the course of time, as various random configurations are assumed during a Fraudian movement, certain of these will ungrain rhinoclive groups into opposition, and the portion of the chain involved in this fluctuation will become immobiles. D, the structure being subsequently stabilized by the operation of other residual fork ETs. Continuation of this process will result in formation of a globular molecule which may or may not have all the specific properties of the original native protein. If the reactive groups which were bonded in the original structure happen to be so along the polyoitide chain that their positions correspond to E-robal configurations of the chain in a E-articular environment, they will again react, and the denaturation will be completely reversible, or nearly so. If the reactive groups were originally linked in an unstable configuration under the influence of a special environment, such as the field of an antigen during the synthesis of an antibody molecule, then the original linkage will correspond to such an unlikely fluctuation that denaturation will result in permanent loss of specificity. It is perhaps in terms of some such model as this that we must in future discuss the URO molecule, but the picture will become sharp only when more is known about the sequence of amino acid residues in the J-derivative polymer and its relation to the distribution of polar groups in the globular molecule. The study of molecular aggregates in systems of several components encompasses a great many phenomena which are not encountered or are arbitrarily ignored. When interest is confined to solutions which have been artificially fractionated until they obey one or another of the physical criteria of homogeneity, the associations which occur must involve all the types of interaction enumerated in Chapter 6, and the products will vary from the one extreme of instability, Rheon, represented by a slightly increased duration of kinetic encounters between the reactants, to the other extreme, at which definite complexes of considerable G persistence are formed. It may be anticipated that in future, many of these interactions will be defined physical-chemically. Although an important start has been made in thermodynamic and other studies of simulated mixed systems, such efforts at semi-empirical definition of behavior are not broad enough in SCOC to be usefully applied to biological systems, except for purely descriptive general. In the meantime, TLN empirical study of various types of organomolecular aggregates continues. But in the absence of any unifying concept, we do not propose to review these studies. Significant as they are of the nature of specific precipitates of the various naturally occurring complexes of proteins and nucleic acids, or of the organ-specific ultra-microscopic particles which can be obtained from broken-down cells. Instead, we shall refer to a more dual question, basing our remarks upon an excellent pyre, examining criteria of purity of large molecules, extends classical conceptions to fit the peculiar circumstances attending the investigation of biochemical systems, including the limitations of present technical methods. His treatment almost compels a more radical approach, in which the very idea of purity, considered apart from a particular functional criterion, could be made to appear illusory. The size of a giant molecule in itself suggests a localization of chemical reactivities, and by extension of biological specificities, analogous to the independent kinetic behavior of chain segments or branches in a polymer molecule. Thus, it can readily be imagined that activity measured according to a given chemical, immunological, or enzymatic process may be equally associated with particles of different size or chemical constitution and with particles, which, seen in terms of some other mode of activity, may have little or nothing in common. Conversely, particles which prove to be indistinguishable by a given physical measurement may well be entirely different in biological specificity. From this point of view, the physical and chemical approach to the problems of specificity can prove misleading. Such methods of fractionation may be of doubtful value if they do not possess some degree of specificity closely related to that involved in the bit logical J process, which serves as the final index of uniformity. Fractionation-based OGI, the known properties of a prosthetic group, for example, might be effective in concentrating an enzyme, while separation of a polydispersed bacterial antigen into fractions homogeneous in respect to particle size might be less except as a means of establishing the point now under discussion. Examples pointing in the same direction could be multiplied to show that the most extreme specificity may reside variously in the molecule as a whole, or in a limited region only, the non-specific residue in the latter case being amenable to more or less radical alteration without interfering with the specificity. In the limiting case, the specific group may be detachable and able to function in the absence of a carrier. The literature on viruses and enzymes abounds in examples of adsorption. On the other hand, the ESJ specific group, although detachable, may retain its reactivity only in conjunction with a carrier or some other molecule suitably situated. The functional unit might comprise, for example, a large kinetic unit characterized by its sedimentation constant, acting in combination by residual forces with other multisimulas and with an atmosphere of solvent molecules. It could be argued that such a complex, to which a definite mean life could be assigned as an index of stability, leaves as much right to be given molecular status as does any covalent compound which has only a transient existence under given experimental conditions. It is clear, however, that such arguments substitute for the simplicity of the classical definition a highly ambiguous conception of the molecule, and it may be desirable to introduce a new term to distinguish the variable functional unit from the molecules of chemistry and physics. Our present intention, however, is solely to indicate some of the difficulties which are encountered as soon as any attempt is made to correlate the properties of systems at different levels of organization. It is hardly to be expected that at this stage any useful generalization will become evident. There is too little detailed information at either level. Alronson H. A. KLC drop layer click. Ranonuaya and Wanaluir Arkijia La Kialo Ian Memlison. Shen Cal alone. Alex with the electron microstudios. Von Cedilioid Systems. IV Schnickel Press. Liquiden 10 B7 Chibnall A. D-amino acid analysis and the structure of proteins. Hekirian lecture. Dubai P-polar molecules. Hemial at Autolog Company. New York 1020 Mirsky AE NAW. Polisler Studies on the Chemistry of Chromatin. TR New York Powell. RE and H Earring. Frictional and thermodynamic libraries of large molecules. Advances in Colloid Science. Edful O. Kramer. Interscience New Aorc 1042p. 183. Schmidt. CLA. And other ST. Chemistry of the Amino Acids and Proteins. Thomas Staudinger H. Dihomolekularen Organi HTN Verbindungen. Kotzehuk. One Elilosus Edberg T. Oloid Chemistry Torit. Ed. Hineil. Adalog O. New Aorc 1928. Symposia and Disquasions 1. Introduction. On crystal form and have it considerable in relation to the aggregation of macromolecules, sonic of the organochroniolacules identified by their behavior in the dispersed state, and particularly the highly isodiatric particles represented by the synthetic linear polymers and by cellulose are obtained in this condition by the virate down of solids distinguished in the former case by their amorphous character, and in the latter by the fibrous habit in which they occur in plants. It is not surprising that thread-like molecules should tend toward random distribution, nor that under proper constraint they should readily take up a parallel orientation. The latter tendency is so marked, however, as to be of inestimable significance in biology. Indeed, it may be said that the fibril is the most adaptable, providing on the one hand the basis for nearly all supporting structures, and a labile morphological foundation for nuclear processes on the other. It is this versatility of the fibril that lends such considerable interest to the study of its molecular organization. This question of molecular organization is fundamental. There are others, perhaps, less important, which have been scarcely touched upon. Given the structure of the G-renidative molecular crystallite, or its analog in the more random world of high polymers, we are still confronted once the gap between the crystal unit and the complex histological pattern form knowledge of the chemical vectors, defining the dynamics of growth. The problem thus overflows its boundaries to cover at length the entire field of morphogenesis. Molecular organization in fibrils has its parallel in crystallography, in the relation between crystalline form and the stereometry of the molecular unit. The more general question of morphogenesis can, perhaps, be similarly regarded as a biological counterpart to the mineralogical problem of crystal habit. For the two have in common their need for a description of the environmental factors operating to give rise to aggregates in which the gross morphology is not in any obvious way related to the fine structure. The essential unity of all intermolecular and interatomic forces, our thesis in Chapter 6 would appear to leave no room in biological organization on the purely physical level, for forces qualitatively different from TUS involved in inert matter. It is perhaps worth a while, therefore, to consider briefly the application of some crystallographic facts to aggregates of large molecules. We have in Chapter 6 considered in rather GC-general terms TLLND condensation of assembly of atoms to a heterorhythmic solid, and have at least by implication referred to the crystalline nature of the solid, meaning, by virtue of this term, the systematic repetition of units throughout the mass, however numerous the types of linkage in the system. We may imagine that, left to itself, an ordered arrangement will be attained in which all linkages standing in a given space relationship to the Riemann unit will recur in parallel equidistant planes, generally speaking, planes containing only weak bonds with correspondingly great bond lengths will be plancy V's of mechanical weakness in the crystal, and will also tend, under uniform conditions of crystal growth, to be parallel to an Imes-Orton and frequently occurring crystal face. This rough and ready generalization embodies the law of Bravais, and its recent extension by Donnet, them schools rather strictly applicable to a number of ionic crystals. The minerals mica and asbestos provide admirable illustrations. Urahedral groups, CN4, are united in sheets so that 3 of very 4 oxygen atoms participate in 2 Si4 groups. The linkages are J-robably artly covalent in character. The residual polarity of the 4th oxygen atom is satisfied by formation of weak cross-linkages with metal ions. These bind the sheets together and are responsible for the lamellar halate and the very strong basal cleavage of the mineral. In asbestos, the Ciod Graues form chains, again partly covalent, which are feebly connected laterally through metal ion links. In a single well-formed crystal, the chains may be several inches in length and can be easily teased out in the form of long fibers. In molecular crystals with covalent bellows bound by ionic or residual forces, the mode of packing. And therefore, the crystal form may be so influenced by the position of polar groups that any obvious relationship between molecular asymmetry and crystal form may be lost. This is well and appropriately illustrated by the behavior of elongated molecules. Such molecules tend to arrange themselves with their long axes parallel. Either they may form laminae, in which all the ends are coplanar, as e.g. a bundle of toothpicks, or else alternate molecules may overlap. The first type is exemplified by the monobasic fatty acids, which form lamina of double molecules, joined by their carboxyl groups, with residual CH3 to ill linkages between the laminae. The crystals likewise are laminar, with marked basal cleavage. In the overlapping type of arrangement, the strong compare R.C. Evans, An Introduction to Crystal Chemistry, Ambridge, 1939. Cleavage is absent, and the crystals are elongated in the direction of the long molecular axes. The same thing happens when 2 polar groups are present, the molecules then forming chains and crystallizing in needles, as does anthracene. Avheger are several polar groups distributed along the chain. The behavior is less predictable, and we have for the first time the possibility that several modes FF parallel association may be almost equally probable. The resulting crystal will have a certain degree of randomness in the transverse direction, combined with strict parallel alignment of chain molecules. At this LU point, we encounter the first departure from the conventional lattice structure. When a molecule with distributed polar groups becomes sufficiently deformed to be regarded as a colloidal particle in the direction of Tlie chain, and a crystalloid at right angles to it, we have still greater oscillity of random behavior. For several segments of neighboring polymeric chains may take UGA U-parallel orientation, while the remaining segments are free by reason of the flexibility of the molecule to unite with other chains or EDC to form closed rings. The number of possibilities is enormous and may range, according to the constitution of the chain, from the globular self-linked mononucleic molecules of the soluble proteins to tissues with a very Urfite alignment. In the latter case, we can visualize crystallization as a continuation of the process of random parallel pack engine. This may result in a fiber longer than the lengths of the polymeric chains, while composite, consisting of chains in parallel orientation, overlong, at random, in 10 longitudinal direction, and joined laterally also more or less at random, but with cemented regions containing on the average a urtane nomenclature of segments and a certain number of interlinked chains, in this partly random structure we have for the first time, and to a degree Nair encountered when the molecular packing was more rigorously governed by the laws of spatial symmetry. A striking correlation between the 4T and E properties of the crystal and those of the molecular units. The fiber owes its great longitudinal strength, however, not to the strength of the covalent bommels in the bioammeric chain, since all the constituent chains are joineal, end-to-end by residual forces oxally, but to the numerous ions of lateral cohesion. These bonds must first be broken if the chains aren't to slide over one another, as do when the fibers, in which we have anticipated some of the results to be given later, carries us back to the second question referred to above, namely, the articulation of crystal habit, where we can readily imagine the building of a fiber from elementary polymeric threads without understanding how its direction in relation to other structures can be regulated. In the growth of crystals, the ideal crystal displaying the relationships required by Donnay's rule or some more comprehensive state, it is not seriously suggested that the actual process of fiber formation is as simple as this. For example, association of chains and their continued growth by synthetic reactions may occur simultaneously. 7L Kimpeo Bio. Reverend Cambridge 16, 153, 1940. Merit can only be produced under very constant conditions. Small changes in the composition of the solution or of the melt may cause the appearance of new phases or the suppression of others. As in the unusual crystals of rock salt obtained in presence of glycine or formamide, while traces of adsorbable substances can sometimes inhibit altogether the continued growth of a crystal. The factors that can combine to produce deviations from the normal crystal habit must be very numerous and often very specific. Crystals and crystal aggregates may be needle-shaped, thread-like, arborescent, botryoidal, or even spherical without having any of the Geropides implied organization. An appropriately periodic molecular field may induce oriented crystallization, as in the well-known case of potassium iodide deposited UGK, a basal cleavage surface of mica. This phenomenon appears to be the result of a fortuitous agreement between the lattice period in the two compounds concerned, and it must have its counterpart in some of the SI-ECI interactions of biological components. W.J. Skinnett has ECK and CD to the influence of collagen fibers in regulating the oriented deposition of the mineral components of bone. Thus, it is not difficult to understand, in principle, how Tli growth of structural elements in a cell can be directed detrimative spherical interface deformed by adsorption of some surface active component. Acting locally as nucleus for aggregation of fibrils, G-dye new structures, in their turn becoming seats of metabolic activity, may exert reciprocal influences on the behavior of other parts of the surface by the production of diffusible substances, so that a further deformation of the interface perhaps will stretch the existing fibers and thus establish a geattern for the continued deposition of oriented material. This crude statement gives nothing more than a hint of the extent to which complex influence is analogous to those responsible for the habit of minerals, but inestimably more subtle may give rise to some of the structural features of living systems. There is, in fact, more than a hint of the operation of such influences in some of the processes of development, such as the formation of phylloxera and flagells. It seems clear that the form of cell congenants may be decided. Last analysis, the orientation of a fibril is equivalent to the orientation of a molecular structure. But it is clear that the orientation depends also on the morphological properties of the embryo considered as a whole. Compare Efferin, Crystals and Fine Structuring of Matter Trans by W.S. Stiles. Methuen with Tili Ejitercrusilon. Lias perhaps seeded the legitimate hoinids of a Teurotius. On lard mole, Julius, we may return to a more circumstantial anionive of the Strutmere solids, retaining Tinan emphasis already, Lael upon those in Eatu. The study of the Iran genitil of particles in bulk systems, in the account of the physical Jutsuar principles, underlying the use of X-rays in elucidating crystal structure. The crystallogride basis is the S-Awak lattice, compare figure 15 TP. If placile in a beam of X-rays, each lattice point in a single reW of lattice points will act as source of a new spherical wavefront, and now in certain directions, the WA from every lattice point will be in phase. There will be several diffracted plane locus of eicolificide ray, is obviously a riglet conical surface W to the EA apex at the point of incidence of the beam, right side of figure 15. middle, and WD is the row of lattice points as axis. A second row of lattice points intersecting the first will also give conical diffracted rays, the diffracted rays from a two-dimensional lattice, each point of which belongs to both rows. Must therefore fall along the lines of intersection of the cones, which will generally be 2 in number. In 3 dimensions, 3 cones must have a common intersection if there is to be a diffracted beam. Thus, a crystal WDL not in general produce a diffracted ray, except in a certain series of orientations with respect to the incident beam. This concept of intersecting cones can often be replaced without loss of precision by the simpler idea of optical reflection from parallel lattice planes, compare Figure 15 bottom, the plane containing the INSEE top, illustrating in 2 dimensions the formation of lattice planes. The sets of planes shown are indexed in the Miller notation described in the text. Middle scattering of X-rays by a linear array of particles. The circular arcs represent the secondary rays. The heavy lines represent the resultant first and second order double wave fronts. On the right are shown 1 and 2. Tying in corresponding diffracted rays. Bottom, illustrating but not proving that when the lattice linoid diffracts in the nth order and obby the nth order, the direction of the diffracted ray corresponds to optical reflection of the incident ray from the lattice line. The case illustrated lines define the lattice lines. The dotted lines show the incident and diffracted rays, and the thin continuous lines define the reflecting lattice line. 12 gent and diffracted rays, and the angle Hettuchen-Plios rays serve to identify the lattice plane responsible for the reflection, while the correspond in lattice spacing d is given by Bragg's equation where x is wavelength, b is the glancing angle, and I is the angle of incidence on the reflecting plane. This represents the restriction imposed by interference between rays reflected from successive lattice planes. In the Bragg spectrometer, each recorded point defines a particular value of d and I. Results are obtained more rapidly from rotation photographs, for which the crystal is mounted with a crystallographic axis. Say the C-axis, coincident with an axis of rotation and I-terminal to the incident X-ray beam. During rotation, each set of planes, capable of reflection, comes in turn into a suitable position, so that a point patch current is produced on a cylindrical film perpendicular to the incident ray. Apply points B sides next and make wide placed symmetrically with respect to the rotation axis, and a line JX tendicular to it in the plane of the plate. Also fall you on horizontally disjointed lines, the so-called layer lines. Successive layer lines caress. Onto successive lines correspond to reflections from lattice planes with general indices if Q, etc. The reason for this is obvious from Figure 15, NDD. For since the C-axis remains perpendicular to the incident ray T, angles of the diffraction cones do not change during rotation, and all diffracted rays thus therefore lie on these cones, which intersect the cylindrical film in straightlit lines. For this reason, the positions of the length lines are of great value in determining the dimensions of the unit cell, the corresponding values of a and H being, of course, obtained by rotating the crystal about the A and B axis. From the dimensions of the unit cell, the number of molecules it contains can often be calculated if we know the density and molecular weight of the substance. The separate points on the rotation diagram are ambiguous, since we know their position only with respect to the NC X-ray beam and not with respect to the crystal. Nevertheless, their significance can often be deduced with considerable certainty. Many difficulties of interpretation are removed by using Weissenberg's device of a recording film moving in such a manner that its position corresponds always to that F, the rotating crystal. This introduces the additional variable required to establish a 1-1 relationship between the position of a U point and the lattice plane producing it. From the Weissenberg diagrams, projections can readily be prepared on which the points can be unequivocally indexed. When single crystals are not available for examination, it is possible to make use of powder photographs. Here, each point of the 3 rotation photographs is replaced by a circle, since crystals are present in all possible configurations. Consequently, the number of circles is often too large to be of any more than qualitative value. But when the three axes of the unit cell are equal and at right angles, the photographs can be used in the analysis of structure. If the particles were not entirely in random positions but had one axial direction in common, the powder photograph would be exjected to resemble the rotation diagram of a single crystal. Diagrams of this type are characteristic of fibers and will be referred to later. On the other hand, if a body were amorphous, no diagram would be exjected, although substances like rubber commonly show a single diffuse circular E-turn, which indicates the existence of some rather indefinite undirected periodicity. Liquids similarly show diffuse rings, the interpretation of which in terms of a distribution function for the distance of separation of molecules or groups of molecules has given rise to considerable discussion. The Bragg-C equation is not applicable in such cases. The space group can be determined by a detailed examination of diffraction patterns. What has been considered above as a series of diffracting points, coinciding with the lattice points, is actually a series of groups of points within the unit cell, so that each lattice plane should be replaced by a number of lanes regularly or irregularly spaced according to the degrees of symmetry of the I-articular space groups concerned. This subdivision of the primitive translations is responsible for differences in intensity of the various SEIOTs on the X-ray diagram. Since each plane participates in the reflection phenomenon and the various components of the final reflected ray differ in H-phase, when certain definite types of symmetry operation occur in TLGSA, the GIS difference may be exactly a half period, with the result that certain reflections may be absent from the diagram. The identification of these systematic extinctions, each of which is characteristic of the symmetry operation which produced it, thus serves to determine the space group uniquely. This knowledge usually suggests possible arrangements of molecules in the unit cell. Knowledge of the structure of a crystal in further detail depends upon accurate measurement of the absolute intensities of a large number of diffracted rays. The intensity of a ray diffracted in a particular direction represents the result of superposition of rays scattered in that direction by each electron. The scattered intensity of a single atom can be calculated as a function of the angle between incident and scattered rays. When this angle is 0, is AF approximately n times the amplitude scattered by a single electron, n being the number of electrons in the atom. Since the path through the atom is then the same for all rays, it falls off with increasing deviation of the ray. Idle amplitude phi, including numerical amplitude and phase, of the scattered ray from the entire unit of structure can be calculated by superimposing all the rays, scattered by the various kinds of atom A, C, present in the unit. Clearly a particular value of F for a particular angle does not define a Lewis structure. The diffraction of X-rays and electrons by amorphous solids, liquids, and gases. Gappian a curve relating F to the angle of scattering would be open to fewer conflict in interpretations, and the customary use of a complete diffraction diagram amounts almost to this, with the important qualification that the measured intensities are proportional to FEA, so that we actually know F only in magnitude and not in sign. Despite this limitation, it has been possible in a number of cases, by calculating the F curve for several plausible structures, to decide which of these corresponds most closely to the experimental flata. The intensity curves can be interpreted in other dual ways. The electron density at any point is repeated periodically in any arbitrary direction, the period being related in a simple manner to the Miller indices of the plane, normal to the direction in question end. This can be expressed formally of these different periodic functions, Cly amplitudes of which are given in the formal expression as unknown coefficients OI. Now, FEHD is an integral of the electron density at every point in the unit cell, and it is possible by substituting the Fourier series in the expression for F to calculate the coefficient A in terms of F. Fe result is of surprising simplicity, the coefficients of the harmonic terms corresponding to the various possible crystal planes being proportional to Fe. Ideas, the observed values of F, can be listed to calculate the electron distribution in the unit cell. Via the signs art, the application of such series is, however, limited to casts, where the phase can be calculatable or can be teleduced from symmetry considerations. This difficulty of sign is a serious obstacle to Lie construction of density diagrams for complex unit cells. It is possible, however, to CT@pound the various intensities by means of Fourier series containing these values, proportional to insteel TF the amplitudes as coefficients. The theory of such series was considered by Patterson, who was able to provide a physical interpretation and to show that dualigrams obtained from FA series are capable of being used in determination of structure. The density in a Patterson projection at the end of a vector drawn from the origin represents the integration over the unit cell of the product of densities at all pairs of points in the crystal structure which have that vector relationship. In other words, in sufficiently simple cases, it gives these the position of every atom with respect to every other atom. For a complex structure, the interpretation of a Patterson diagram, two-dimensional projection, may be extremely involved, and that of a section impossibly so. It is quite difficult to trace the relationship between the density diagram and the Patterson diagram, even in cases where the structure is known. Not only the relative positions within the molecule, but also those of atoms in neighboring molecules related by the symmetry elements are represented by superimposed diffuse peaks. And these combine in sucly a way that it is extremely hard to unravel the tangle 3 notes on the structure of certain crystals. The study of the arrangement of large molecules in undispersal aggregates, at least insofar as it has our affinity to biological materials, is largely the study of differberm systems, thin films and fibers. These are not strictly crystalline. Some crystals, others such as starch and glycogen, occur in granular habit. These facts alone, and inclusion here of some reference to the structure of true crystals. Other reasons also have determined the selection of the SD-viral groups of substances referred to in the following notes. The chief of these is the SI-ischal structural relationship between the small molecules and the large, between the simple sugars and the cellulose fiber, or between the PIA linkages in diketoprasine. And those in, for instance, a relationship that makes a knowledge of the molecular dimensions and packing of the small molecules indispensable to an understanding of TGI large. Even mate to long chain allyhadic compounds and to the lipids and sterols is omjali justified by the peculiar importance of THC-TSD substances as components of the cell membranes, in which they are undoubtedly present in the form of intercormolecular complexes with proteins, while preserving some of the structural features characteristic of their configuration in the acetylene state. Calrite, aragonite, and apatite. Skeletal structures, external and internal, are largely inorganic in nature. Alt-Leov deposited under the guidance of organic formative influences, and often giving little morphological evidence of their inorganic nature. Of the fine structure of substances commonly found as minerals. The immediate circumstances may be very deceptive. It may happen that a calcareous jewel of obviously organic origin is actually a single crystal, highly eccentric in habit. On the other hand, morphologically identical crystallites in comparable biocleomeal situations may be composed of chemically different substances, apart from silicious exoskeletons of, say, TI organisms. The most common mineral components of invertebrates are identical with one or other of the two forms of calcium carbonate, chelate and aragonite, while the mineral constituents of bone, including the enamel and dentine of teeth, are very closely related to apatite, CF5, FPA, probably by substitution of hydroxyl for the fluorine atom. These are all ionic crystals. The crystal structures of calcite and aragonite are rather simple, and can be readily understood as distorted examples of cubic and hexagonal close packing, and below the layer AA, either the upper layer can occupy the row of deeper ions, BB, in the lower layer, the row CC, or vice versa. Or else hotly upper and lower layers must occupy the rows BB or T. Would give a vertical pattern, cab, in the latter, the pattern ba. HEI art from Tlu distortion or IE men below, comparing the environments of the carbonate ion in calcite left and aragonite right. The diagrams are basal projections in which the atomic positions perpendicular to the plane of the paper are represented by fractions. Heavy open circles are calcium, light open circles are oxygen, black pools are carbon. It will be noted that the packing of the calcium ions in calcite and aragonite resembles that shown above on the left and right respectively. The carbonate ions are so placed as to give each oxygen 2 calcium ions as close as neighbors in calcite and 3 in aragonite. Apatite forms a denser and much harder structure in which the fluorine ions, or their analog, occupy a key position on the edges of the hexagonal unit cell from which they are linked, each through 3 cane ions to the phosphate structure. It is suggested that the carbonate in bone replaces fluorine in the apatite structure, but this would require such a considerable distortion of the lattice that tricarbonate is probably present only in regions where the apatite sits. Hydrocarbons, fatty acids, lipids, AMI, sterols, these substances, covering a very wide range of molecular complexity, have in common some of the striking features of intermolecular organization. And as these are PC in any discussion of the mode of association of the substances in showing distances between adjacent and alternate chain. On the right, projection on a plane perpendicular to chain axis, showing the effective cross-section of freely rotating polymethylene chains and the resulting mode of packing. S showing the decreased symmetry of polymethylene crystals, WEM, free rotation. Illustrating the formation of hemolecular leaflets by aliphatic molecules with a single terminal polar group. AA repri dots the basal or cleavage plane. In 4, the chains are perpendicular to the basal plane. In 5, they are tilted. Living matter, we prefer to underline them rather than to enter into a detailed description of specific complexities. We wish to stress in particular the predominant modes of packing of unsymmetrical molecules. The one assumed when the intermolecular forces are uniform, and the other when there is a specifically reactive terminal group. Tion between the chains is sufficient to cause loss of rotational freedom, and the chains then pack with a less symmetrical mutual configuration, allowing the maximum area of contact. This is characteristic not only of the paraffin hydrocarbons, but also of benzene, anthracene, and other chemically inert ring structures. When the hydrocarbon chain is terminated at one end by a polar or ionic group, as in the monobasic acids and alcohols, the units are double molecules joined end-to-end by their reactive groups. In general, the substances are polymorphic, with chains oriented vertically or obliquely with resject to the basal plane, a figure 17 diagrams 4 and 5, which is also a cleavage plane. At higher temperatures, these substances, like the eterarphins, may assume the hexagonal arrangement with rotational free atomium. The same binuclear units occur when the terminating group is P-complex. They are difunal in the triglycerides and apparently in the lipials. Baer, Palmer, and L. Schmidt have noted in the X-ray allegrons EF several dry lipids, lecithin, cephalin, cyclomyelin, frenosin, kerosene, a common short U-spacing reflectation at about 4.2A, corresponding probably to the close packing of parallel hydrocarbon chains, and long spacings, which, allowing for some uncertainty in the length of the chains, agree quite well with the values calculated for fully extended double molecules. Similar spacings are found in the total dried lipid from brain or nerve, among the sterols, I, and the related sex hormones, which show an astonishing diversity of crystal structures. It is possible to distinguish single-lane double-layer types of unit cells or of the single-layer type. The most frequently occurring cells are the single-layer type, with dimensions that suggest a molecule about 4.5, a thick 7, a wide and 20 long Patterson project ions of cholesterol chloride and L-arginide, showing two ridges running the length of the C-axis confirm this interpretation. These dimensions are in conformity with a Pukin ring system and a chain continuing along the line of Tly rings, and the Dewey acting of these long, flat molecules is closely similar to that of the linear or cyclic hydrocarbons. It is significant that often the single-layer crystals have no polar groups. If such groups are present, either they are in an unfavorable position for association, or else there are two of them at opposite extremities of the molecule, as in androsterone, which can interact without any considerable distortion of the one-layer structure. On the other hand, out of 48 compounds giving double-layered CE, 88 are known to have an hydroxyl GRAU in the 8GE position. In 7, the PP position of the groups is uncertain, and in the remaining 8, the reason for the double-layer structure is unknown. Pyrocalciferol, which satiety has an O group, in the 8-ESA position forms single-layer cells, while anhydrous cholesterol and anhydrous ergosterol form very complex crystals, with a unit cell containing as many as 82 molecules in the latter case and 8 in the former. LAIs, ITs, and other anomalies, there is not much doubt that the double-layer structure is usually associated with interaction between two O groups in the 8 position. The accepted view that cellulose is made up largely of I-glucose residues and starch of ORF glucose makes the structure of these relatively simple compounds a matter of peculiar imins or tan-C in the study of macromolecules. Although recent chemical studies have established beyond peradventure the constitution of many of the stearoids-americ sugars, the precise spatial arrangement is still uncertain. This is mainly due to doubt as to the form of the pyranose ring, which may be built in various puckered forms with bond angles approaching the normal values, or in other forms with distorted bond angles, giving in an extreme case a flat ring in which the pyranose oxygen lies above or below a plane containing the 4 carbon atoms. The puckered rings add considerably to the number of possible stereoisomers, and the fact that these have not been shown to exist is perhaps a point in favor of a plane ring. The energies of activation for tautomeric interchange between the various theoretical forms appear not to have been worked out. In any event, it is important to know an average configuration, since a small change may alter considerably the extracyclic valency directions, and may be the principal factor in determining the conformation and mode of packing of rings in a pyranose PT dimer. The study of the sugars with X-rays is singularly difficult. The variety of different structures indicated by the extensive data available concerning crystal class, dimensions of the unit cell, and space group is perhaps as considerable as among the sterols. Apart from possible variations in the ring, this is largely the result of interaction between hydroxyl groups, to which the crystals also owe their hardness, density, and high melting point. Replacement of a hydroxyl group or a change in its configuration may necessitate a complete readjustment of the relative positions of the molecules. Such rearrangement may make it difficult to arrive at any reasonable estimate of the effect of the change upon molecular dimensions, although this may sometimes be possible. Consideration of TLL relationship between the unit cells of alpha-V-cellose, 3-methyl-xyloside, and A-diglucose, for instance, leads to the Foltwing values for the molecular dimensions, from which it has been concluded that the change from the A to the 3 configuration does not alter the thickness of the molecule, although it should do so if the ring were puckered. Furthermore, some indication of the J-positions of the extracyclic TH2O group in glucose and of the methyl group in methyl-xyloside is given by the changes in length and width. Only occasionally is it possible by increasing the volume of a single substituent to expand the lattice without causing any other change in the unit cell. The following example degrees gives the molecular dimensions in such a case. Constancy of thickness of AN's derivatives, which would provide important evidence in favor of the flat pyranose ring, is difficult to establish in the majority of sugars because of the uncertainty attaching to the mode of packing. Apart from the cases mentioned already, decellulose 4,3-diglucosido-D-glucose, alone has a unit cell dimension of 5A or less. Conditions are far simpler when the effects of hydroxyl interaction are eliminated crystals with a very short cell dimension, parallel to the long axis of about 4.5A. The cases listed in illustration include derivatives of glucose, cellulobiose and chellotriose, from which it may perhaps be concluded that the flat ring is the form assumed in these substances. A certain amount of other evidence has been adduced in favor of a similar ring structure in the free sugars. It has been ioted that E. arabinose gives a particularly strong 18th order reflection parallel to 10, indicating a concentration of scattering mass along the 5 axes at intervals of 5/18, or 1.08. This period corresponds roughly to the positions of hydroxyl oxygens above and below a plain pyranose ring, but is difficult to reconcile with a striates ring. More recent evidence concerning the unmethylated sugars, however, appears to favor a slightly puckered ring. A complete X-ray synthesis of the structure of a glucosamine hydrochloride and hydrobromide has been achieved without recourse to any stereochemical assumptions. Both 3-dimensional Patterson sections and Bragg sections have been made. The signs of the structure factors required in the latter having been determined by a comparison of corresponding intensities for the chloride and the bromide. The results demonstrate for the first time the real existence of the pyranose ring in a crystalline sugar, whereas the chemical evidence has hitherto been strictly applicable only to glucosides. The data apparently exclude the boat-shaped striates ring, but the ring is nevertheless slightly puckered. It is interesting that the number 1 oxygen atom is found to project almost vertically from the ring, so that this atom in the corresponding 3 sugar must lie practically flat. The same difference, if it persists in maltose and cellulobiose, must be of great significance in the stereochemistry of starch and cellulose. Starch, despite its chemical similarity to cellulose, both substances being polymers of seed glucose, occurs always in granular habit. The granules possess a concentric layer structure with radial symmetry, resulting from the presence of small elongated crystallites, probably not more than 100A in length, arranged with random orientation about an axis which coincides roughly with the radial direction. The unit cell corresponds to 2 maltose or 4 glucose residues. The crystal structure is very imperfect, as would be expected of a substance which contains at least 2 polymeric components, each probably polydisperse. These may be distinguished as amylose, the water-soluble component of low molecular weight, and the giant molecule. Amylose is probably an unbranched chain, and amylopectin an elaborately ramified structure of polymerized maltose, 4Q, RF-glucosidoEF glucose, residues, i.e. degrees of branching and molecular weight of the latter showing pronounced differences in starch from different sources. As a result of these differences, and probably also differences in the degree and mode of aggregation of crystallites, the reactions of starch granules from different sources vary, specifically in relation to the systematic botanical eposition of the sort. The X-ray diagrams, similarly, vary according to origin, but the diphthongs can be abolished without destroying the typical features of the starch diagram. According to Catullus, Meyer, nothing more than the fact of crystallinity and the existence of different modifications has been established. The optical properties of the grains in the comb, located changes observed on swelling, suggest that the radial arrangement of crystallites is a very loose one. With intermediate regions in while the crystallites are widely separated from one another, being connected only alloy molecular filaments. It is the size and the highly ramified structure of the amylopectin molecule, which makes it possible for EQ art of the molecule to remain in lattice like micelles. Micelles in another part of the same molecule to be surrounded by sulfate, while the unbranched amylose probably is present in dissolved form. DG-didecyfiperazine, glycinealanine. Tentative models of the ILI peptide chain have played a considerable part in the elucidation of fiber structure and have figured in speculations on the structure of globular proteins. These modes have lacked precision because until recently there have been no complete analyses even of the similase surfaces. E.T. Reichert, a biochanic basis for the study of problems of taxonomy, heredity, evolution, etc., with a special reference to the starches and tissues of parent stocks and hybrid stocks, and the starches and hemoglobins of varieties, species, and genera. Carnegie 90H. Meyer, Advances in Ooloid Science, edited by E. Kramer. Inter-Science Sucli data are now available for dicatoparasitic glycine alanine. The results are of considerable interest, providing information which we cannot yet expect from the X-ray analyses of proteins themselves. The molecules lie nearly flat in the 101 lane in straight parallel rows, the molecules within a row being lifted so as to equalize 2 NH1 distances between Ni-boring molecules. The structure is thus determined largely bonded molecules both within the LNO1 plane and UENAP, lure to it being considerably HVSS and giving rise to marked shabbage along 101 and 10. In glycine alatine, possibilities of hydrogogni bonding are far more numerous than in lycopiprazine. The glycine dialkyl has the form as shown in figure 18b. In the crystal, the molecular Z's are packed in bimolecular sheets. Between the sheets, only van der Waals forces are involved, so that the GD of sheets 10 is a cleavage trillion. Within each sheet, the cohesion results from the system of hydrogen bonds indicated diagram analytically in figure 18d. The molecules are joined symmetrically in pairs, head to tail, Li2 bonds of length, 8.05. Each is linked with others in its own Jew lane by 4 bonds, 1 for each oxygen atom and 2 for the nitrogen, the UI bond being 2.88A and the now 2.76 along additional Noi bonds, 2.98A. Link each molecule to one of its neighbors in the other molecular layer of the bimolecular sheet. Thus, in all, each nitrogen atom participates in 4 hydrogen bonds involving only 3 hydrogen atoms. It has been suggested that the hydrogen atoms and the A carbons are disposed tetrahedrally about the nitrogen atom, and that the 8.05 and 2.98 bonds are formed by a single hydrogen atom situated at 2.84A from I, 2.22 from on, and 0.99 from it. Besides necessitating a forked hydrogen bond, trilateral arrangement has been taken as further reduced for tri-dipolar ion structure of glycine, responsible for a more complex structure than is followed in glycine. The E-airing of nialkyles does not occur. A tubular framework of hydrogen bonds with neutral groups packed in sealed tubes, separated from one another by the unusually short distopiperazine. Drawn from data given by large open circles, oxygen small open circles, NH large closed circles, carbon 2 small closed circles. Carbon bond lengths are in angstrom units. B the glycine molecule, drawn from data of G. Albrecht and RB. Or A double open circles, nitrogen. Other symbols as in AED showing the different kinds of hydrogen bond in glycine. All these diagrams are projections on the same plane. E shows bonds between glycine molecules within a single sheet parallel to the plane of the paper. D shows bonds between corresponding glycine molecules within a bimolecular sheet. The bimolecular sheet may be is 4A. All ill. Nesting point in the final Steenacher determination is that the entrelintion of the hydrogen atoms assigned to plausible geocities I's had to be eluded in the aliens LF for the intensity data OU will be accounted for satisfactorily. Besides showing the extreme importance of hydrogen ions in determining the configuration of strontiums containing duoptide or amino-8 groupings. These measurements give integer values for the durable bond lengths and bond angles of EGTs. It is significant that the introduction of a methyl group into glycine causes no appreciable alteration in the end bond lengths, although the actual value 1B9A is for an unknown reason considerably less than the normal value, 1.47A. The bond lengths in dicatoprazine are also shorter than the usual values, probably as a result of the electric visualized by imagining a second layer like that, shown in C to be rotated to 180 degrees, and then imposed upon it. Shows bonds between a glycine molecule in one layer of I, a bimolecular sheet, and its second nearest neighbor in the other layer. It will be noted that according to these diagrams, each nitrogen atom participates in 4 hydrogen bonds. The fact that only 3 HD-yandrogen atoms are available for these bonds led to the suggestion that the D2.99A and 3.05 bonds of D and E are actually split hydrogen bonds involving only 1 hydrogen atom charged up. This is to be expected for the CN bonds, but is surprising for CC, which has Ti value 1.47A. Instead of 1.54A in glycine, it is 1.52AA. On account of these variations, it is not reasonable to assume that no further revisions will have to be made when more complex structure. EDAs have been examined, but the H-allowing values for the bonds in polypeptide chains nil-C-mu can perhaps be accepted provisionally on the basis of these and other recent X-ray analyses. Protein crystalline, the discovery of crystalline proteins around the middle of the last century, Rudolf said immediate discharge. Those who considered that nature would do violence to scientific DC which they were inclined to promote to Tinnen status of heavenly decree, denied the ability of a colloid to crystallize. In this, they were subjugated by certain genuine peculiarities of protein crystals, MMETL, and sting of controversy, added to the great intrinsic interest of the subject. Stimulated a number of meticulous researches to which we owe most of our UJET knowledge, and indeed, a good deal more which awaits resuscitation. Only now, with the advent of X-ray analysis, is TLECH a protease of further advance. Much of the argument was unnecessary, for the occurrence of definite crystal forms, admit lie with a certain variability of interfacial angles, was an accidental or ornamental fact, and as Negelian pointed out, must indicate a periodic arrangement of particles. The dispute really centered around a secondary quality, namely, the ability of water and dissolved substances to penetrate the crystal fabric without disrupting or essentially altering the form of the crystal. It was clear to Negeli and many authors that this involved the separation of molecules in contact with each other in a dry crystal by thick layers of water, and the resemblance of the phenomenon to the swelling of cells in starch granules received a lot of attention. It was said that since protein crystals swell like starch, they cannot be true crystals, but oily crystalloids. It was also deduced from the same facts that starch granules must be made up of microcrystallites, their entirely crystalline nature being mosque in the rounded form of the granule faces. This view gains somewhat in credibility when one considers the genesis of protein crystals, which often start as globulous of amorphous aspect, the crystalline form being assumed by subsequent rearrangement of ex nihilo Sitzung Sudi. D. Albert Akkad, Wistes 1862, p. 120, for early literature sec FWS Dime per ZT 0F Christ 6 131 FNFNA. Schulz, die Kristallisation von Kieweißstoffen und ihre Bedeutung für die Eiweißchemie. G. Fischer, the particles constituting the aggregates, Eberl, believing that dissolved protein molecules are too large to form true crystals. Tulu rearrangement to degilymerization, and into esting luigialucis UNI, an insecure found ion which has recently reappeared in an alluent to explain certain failures of Illy-Patterson projections of protein crystals. The systematic description of these crystals has been the subject of a number of early papers and has since been rather neglected. With the deflection of interest to the use of crystallization as a part of the serooperative technique of protein chemistry, which received impetus from the isolation of ureases and of insulin, and has since extended to the operation of other enzymes, enzyme precursors, and viruses in crystalline or U-crystalline form, idle variability of interfacial angle. The giratin crystals was noted in the Geely's measurements and shown to be dick, at least in art, to the anisotrope of swell. with consequent change of axial ratios. A further cause is undoubtedly to be found in the elasticity of the crystals, a possible resistance to external forces, with change of axial ratios and development of a Lefevre grade of syndrome injury, so that it is not surgerizing that some uncertainty arose as to crystal class to which various protein crystals should lie assigned. The extensive work of Reichert and Oronoglen on true crystalline lune models in many animal species showed that while the crystals from each Jucals ring, easily recognizable by their characteristic habit, and currently belong to several different crystal classes, telluri are actually all merlexers of an isopolymorphous series, the crystals belonging to the Higlet-Nutri groups being derived by mimetic twinning from Tlung orthorhombic and monoclinic types. The relative importance of environmental factors and of possible specific differences in the globin CMD ions is not yet clear. Wichmann has described the isomorphism of various albumins, and it is likely that many other instances could be found. The study of protein crystals with X-rays is still in its early stages. Powder photographs show sharp diffraction rings, which could be hitherto, for example, A. Nigeli, Sitzensby, DGL Belbayer, Akadwis, 1862 P121 A. Colton Vivan Lang, Sitzensby Wiener Cat, Wis, Math, Naturus, JGI 4665 1862, CAFW Shinwiper, C. Chetrayev, Kryev, Krysite 6 131, 1881 DAWL Schmann, Chetrayev. Physiol, Baitin 27 575 1899, EET Reichert and AP Brown. The differentiation and specificity of corresponding proteins and other vital substance is in relation to biological classification and organic evolution. The Civistolography of Hemoglobins, Carnegie Institute, Washington, D.C. They're terniolecular or interterritoric in origin. These are difficult to interpret in detail and have been superseded by the study of single crystals. The unit cell dimensions and space group have been established in a number of cases. DLNV say, provide useful molecular weight values, subject to the usual uncertainty as to the correct value of the partial SHI-specific volume. And they also imaged O's are restrictions upon the possible dot shape of the mold. If W assume in each case that the molecules I present in solution are also F zent in the crystal, the case of insulin is rather simple and definite, since IR3 is only one molecule in the unit CDL, which is a flat rhombohedron at AO proxenating to an oblate ellipsoid of diameter 74.8 A, and water outfit of the crystals is of both theoretical and practical importation in X-ray work. The W crystals give much better photographs with higher resolution than the dry ones, the smallest observed spacing being around 2A for wet crystals, and sometimes as high as 120A after drying. This limits the value of neodarison between wet and dry crystals in the study of the interatomic arrangement, and shows that drying is shown to give unusually perfect photographs down to 2A in the dry state. Taufo has discussed the effect of water upon the distribution of peaks and Patterson projections of insulin and lactoglobulin. In both cases, it seems that two large SACs change a good deal. While the small spacings are shiftable in a body when the crystals are dried, and the simplest explanation is that the molecules are nearly compacted with some angular moving unit during the process. The same is true of wet and dry GGDs of tobacco mosaic. Virus, naturally TLNSA observations tell us nothing about the state of the Wachuli other than its intermolecular situation. Kott's degrees found the water vapor isotherms of crystalline proteins to be continuous, from which he concluded that the substances contain no water of crystallization. Dye theory of the stability of concentrated systems of charged particles, SUG, Watts is probably mostly present in the free state, and that proline crystals should be Regenhall as bipolar conservates. The in-C cratatomic arrangement has not yet been deducible, even in its main features, from the Patterson projections of crystalline proteins. The most striking feature in the intramolecular return is the occurrence of important spacings of 4.5 and 10A, corresponding to the lateral spacings of packed polypeptide chains. These SI-issues are terminant alike in the photographs of native, denatured, and fibrous proteins. There is a tendency for the peaks in the L-Crystal diagrams of insulin, methemoglobin, and lactoglobulin to fall on a hexagonal network, and their coordinated movement during drying does serve to some extent to identify those which are of intramolecular origin. Attempts have been made to interpret the insulin pattern. Rinch and Langmuir use a cycled polyhedron as the basis of their interpretation, to which they add the more or less gratuitous assumption that certain slit-shaped spaces corresponding to edges of the polyhedra are regions of high electron density caused by the presence, possibly of J-articular side chains. Ilmo reloads Tulu hexagonal ha. A turn on the basal projection to a body-centered cubic array of scattering centers and concludes that these correspond to submolecules, E-roll 24 in number. The cycle interpretation has been freely criticized, probably both are premature. To the lay, Roger JML. Robertson's arcunarchs carry considerable conviction. It is quite obvious that 59 relative measurements of amplitude cannot define a structure consisting of several thousand atoms. So, F-steer as the measurements go, the structure is effectively a continuous distribution of scattering matter, and every arbitrary assignment of phase constants to the amplitudes will yield a solution. The suggestion that certain concentrations of atoms in the molecule can be treated as point scattering sources does not seem to constitute even a reasonable approximation. The intramolar tender pattern in tobacco mosaic virus can be discussed in this context, although the interparticle arrangement is really more like that of a fiber, with a very perfect hexagonal close J-acking of rod-shaped I-articles about 1,500 along, arranged at random in the axial direction. The small spacings, unlike the large, are indeed endant of the water content of the gel, and their extreme sharpness shows clearly that the particles themselves are crystalline. As in the true protein crystals, the spacings at 11 and 4.5 A are dominant, with the yellowfirence that the 11 arefication perpendicular to the G-article length exceeds all others in E-mist ortons. The other spacings are, however, anomalous, in the sense that in order to obtain rational indic, it is necessary to assume a unit cell L rotor than the particles themselves. Considering the small number of repeating units present in the cross-section of each particle, diameter 150A, however, it is not to be expected that Bragg's law will hold, and Bernal and Fancuchen have discussed their diagrams in terms of a structure of subunits of about 11 a cube. 264 pour reference to papers describing the Giclo fabric and the polyhedra that can be derived from it by folding. C. 184. C equals 68 AHI. A deeper analysis is scarcely possible without an extension of the theory of X-ray diffraction by thin layers. And for the present, the observed URFLCTs have to be expressed in terms of fractional indices which lack Jointitai interpretation. 4 paracrystals, tactoids, and conjugate. One cannot consider the transition from order to disorder without encountering the paradox of symmetry, by which I mean the high degree of symmetry exhalated alike crystal and the amorphous body. For DSI, hierarchical symmetry of the latter is statistical in sense, tie no symmetry. Precorration will lead to complete coincidence of all analogous J-articles, while in a true space lattice the existence of symmetry decunence is axiomatic. Now the restriction of symmetry operations to 1 or 2 dimensions leads to the definition of various types of partial crystals, but does not by any means exhaust the degrees of ordered arrangement. For order does not necessarily immensely periodicity, with a J or R per definition of statistical symmetry, luminance. It is F oscillez. To arrive at a compluentity Of the transition types of ordered arrangement analogous to the enumeration of the non-statistical space crews of crystalligraph, of which 2 or perhaps 3 are commonly acknowledged to occur in nature. Others will undoubtedly be all-served and should be recognizable from the nature of their X-ray diffraction diagrams. The existence of types of ordered arrangement other than the strictly crystalline was first cognized by the observation of anisodiametric polar molecules, such as D oxygenosol and E potassium olea, which gave rise to a doubly refracting Messier haze during melting and again on cooling of the isotropic liquid. This combination of anisotropy, a sure sign of order with plastic fluid dualities, led to the introduction of terminologies that have since proved misleading. Lehmann use of the terms fließende Kristalle and flüssige Kristalle, the former embracing also the plastic deformability of true crystals, while Fritzsche referred to the mesomorphous state. As Lehmann has pointed out, substances exhibiting this characteristic, autonom anisotrope UI, may range in mechanical properties and in morphology from the limpid fluid to the glassy or fibrous solid. The criteria implied in the earlier terminology being thus irrelevant. Oswald lists a number of experimental criteria, which, although apparently selected under the influence of the early definitions, are broad enough to cover the wide range of properties: liquid or plastic character, anisotropy of viscosity and surface tension, absence or lability of angular boundaries, spontaneous birefringence referable to internal forces of the same order of magnitude P. Kinnick colloid Zelschitar, 60-288, 1932. Chuar Faraday Su, 29, 1060. As casual external influences, if we insist upon the structural criterion manifested in spontaneous anisotropy, as the union PJC1, it is well to choose a term which emphasizes both the resmiability to the crystalline state and the characteristic diftings. Rin's term IR Stalin will LE used here in this sense. The subdivision of paracrystals into IWO distinct ELF is based upon the observation of characteristic, although extraordinarily very efferents under the polarizing microscope. Friedel and Tranjan distinguished between thread-like and conical forms, H. wides aphils, Leides aconias, which were later Jews referred to as lunatic and which, notwithstanding reasonable criticism, have been widely adopted. Blue properties of the nematic state can be ionied for in terms of an array of anisodiametric molecules with a common axial direction and a random distribution of centers of gravity. This type of arrangement shows only diffuse X-ray reflection corresponding to the absence of true periodicity, and it may be observed, for example, in liquid azoxip cut netol and in anisobenzolazonidala de lanium and all resinous solids as a E-Ullmann characteristic of fiber structure. It will be referred to later. The X-ray diagrams of substances in the smectic state, on the other hand, show tin existence of reflecting GD dyes, like the allyl reticular UANs of a crystal corresponding to a periodic disposition of centers of gravity. The arrangement may be sufficiently angular to give a rotating crystal diagram. As with a smectic drop of ethyl p-azoxybenzoate on a cleavage surface of mica, or it may correspond to a random disposition of etiolates. As with ammonium and other oleates, which give powder diagrams with a characteristic spacing of 43.5, approximately a sepal to the thickness of the molecular layers occurring in the true crystals and in soap films. Thallium, stearate, and olate show repeating unils of 36 and 3 respectively, compared with 42 and 45. For the crystals, this may indicate, rather improbably, that ply chains are tiltial to the reflecting planing, or it may result from a liquid randomness of orientatium EF, the hydrocarbon chains. Since the number of diagreeses of freelime in JR crystals is greater than in crystals, isomorphism is far more frequently encountered real. None of their most 2M de Broglie and E. Friedel Comptrend Acadie. S. Key, 176, 788, 1923. Remarkable properties indeed, and one of the most important in relation to their occurrence in living systems, is this ability to form complex paracrystalline mixtures, foreign substances of all kinds, glycerol, olive oil, paraffin oil, water, obtained here to facilitate dispersion and to increase stability. The profound influence of water is of essential interest to us. The first case to receive much attention was that of 10-bromphenanthrene, 6R6 sulfonic acid, formed under an 80 colloidal haze with relatively large amounts of water, and a more concentrated as or need a single spacing, 3.47, compared to 3.4 for the anhydrous crystals, showing that water must have penetrated between the molecules. Later, Rinish drew attention to the extraordinary spheriditic and myelin forms of terri with aqueous emulsions of the phosphatides and cerebrosides, which vary in a most striking manner with increasing water content and are in many respects similar to the myelin forms originally observed by Vercoen with nerve substance and other organ extracts. The X-ray diagram of the emulsions show very clearly the changes in fine structure according to dilution. The various substances taken singly do not always form very stable emulsions with water. Cholesterol not at all sphingomyelin, rather more readily, and ephyllin very easily. The characteristic bimolecular spacings are increased on uptake of water. Mixed emulsions in which cholesterol can also be stably in core or at H show only a single important spacing, which increases continuously from 63.5 A for the slightly moist mixture to 150 A for an emulsion containing 75% of water. Aqueous suspensions of this TIJE containing rod-shaped, or leaf-shaped particles separated by water layers up to as much as 5,000 thick, and yet preserving their paracrystalline or ETH and crystalline CTN configurations are a very general occurrence. They are commonly found in the form of coservates, gidiases of high concentration, which arise by the spontaneous separation of a suspension into a dilute and a concentrated portion, SJK mutaneous anisotrory, is not invariably found in the concentrated layer, in suspensions of clay. Of iron oxides and of VIDMP hydroxide, the anisotropy appears only under acetylene conditions of concentration or aging, or when the phase is disturbed by shearing stress. The concentrated phase in suspensions of the clay bentonite tellurides to form an isotropic gel in which, according to Langmuir, the disc-shaped particles are arranged in an isotropic face-centered cubic lattice. The axes of the discs are not arranged in random directions, but oscillate about definite equilibrium axes, which are related to the crystal axes. In the anisotropic gels, which occur at certain concentrations, a mutual orienting effect of neighboring disk causes them to become parallel with formation of a new kind of uniaxial crystal grain of higher density. One of the best examples of a truly paracrystalline aervate is that of tobacco mosaic virus, the elongated particles of which show a strong tendency to form positively birefringent aggregates. Solutions of the virus separate two phases by formation of teratoids, spindle-shaped regions of low or high density which rise or fall in the solution, and OLS res actively with the upper or lower J haze. High X-ray patterns of the lower phase show sharp lines, corresponding to reflection from A. Two-dimensional hexagonal lattice with interparticle distance varying with the water content of the phase from about 100 A to 450 absence of reflections, corresponding to the length of the I articles shows that the IRTLs overlap in an irregular manner as they do in a pneumatic paracrystal. The factors involved in the stability of phase and its equilibrium with the dilute phase have been discussed further. The phenomenon was at first attributed to Longrang van der Waals forces of attraction, but more recent papers, of which by far the most intelligible is that of Langmuir, have shown that the situation can be analyzed satisfactorily without recourse to any such unsupported hypothesis. 4D dilute and concentrated phases are obviously in osmotic equilibrium. This would not be possible in any system of uncharged and unassociated dead particles, for even if the particles themselves were unable to diffuse rotate idly, movement of water into the concentrated layer would soon result in uniform dispersion of particles throughout the liquid. Now that each profound influence of electrolytes upon the properties of these systems shows, together with a considerable body of other evidence, that we are dealing with charged A. J. Langmuir, J. Chem, is 878, 1988, B. S. Levine, and G. P. Dube, T. R. Faraday, Soc. 35, 1125, 1989, C. S. Levine, Procty Boy. So key 78, 145, 164, 1989. D. S. Levine and G. P. Dube, 36, 215, 1940. S. Levine, 25, 1940, 720 P. Fleet. Dube and S. Levine, a bid, 35, 1141, 1989. G. B. Terjagan, a bid, 36, 208, 1940. Jen, Physiol, 25, 111, 1941. K. H. C. Heinecker, T. R. Faraday, Soc. 36, 186, 1940. For short qualitative statement on Avivine's papers, C. F. Muller and New York Acad, S. Key 39, particles with which must be associated an II atmosphere of opposite sign. Accordingly, there are electrostatic forces tending to counteract the disperse and Y effect of Brownian movement and cause the system to separate into a dense solid phase in equilibrium with its saturated solution, the concentration of which is that at which osmotic and electrostatic forces balance each other. Alias, to account for the fact that the particles actually remain aspirated by thick atmospheres of water. We require an additional repulsive force instead of the attractive force postulated by Freundlich and others. Lee's repulsive force is identified in the various theories referred to above. With the electrostatic repulsion between suspended particles with overlapping ion atmospheres, the case resembles the electrostatic problem Pruss ignited by the interaction of atoms, with the important difference that the size and shape of the micelles have to be taken into account. Theoretical E per I stands for infinite plane. Sphere cap and cylinder cap particles appear to account for the stability of the paracrystalline solutions, and for the characteristic swelling of the lattice by continuous penetration of water into the ice spaces. Lie phenomenon has its counterpart in the swelling of gels, in the shrinkage of the unit-celled EL protein crystals on dehydration, and helps also in changes in the degree of dispersion of chromatin during cell division. The biological importance of paracrystals in general can hardly be overestimated. It is almost superfluous to mention how much of our knowledge of the fine structure of cells depends upon the ubiquity of this state of matter in rotoplasm, and upon the very convenient and significant fact that the birefringence of oriented protein happens to be positive, and that of the lipoids and nucleic acid negative. And Rin has pointed out how singularly well fitted the paracrystalline state is to provide complex forms in which organization and mobility can be combined to a unique degree. 5. The structure of fibers. A general features of crystallization of linear polymers. The Ti-Eichel fiber, according to PRCV set knowledge, is a linear polymeric system which owes its most characteristic properties to those same peculiarities of elongated molecules, which we have seen to be responsible for their behavior in solution, that is, to their length, flexibility, variable size, and the kinetic independence of segments within a single molecule. It follows that in such systems, perfect crystalline regularity is an extreme rarity. Invariably, there are structural defects and sometimes regions of disorder which impose their amorphous character upon the tangible qualities of the substance. There are several sources of irregularity. Defects arise from simultaneous crystallization at several nuclei within a single covalent chain, and are promoted by the thermal motions 286 pqj. Discussion of the biological importance of paracrystals and of the value of the polarization microscope in the elucidation of fine structure, the reader cannot do better than to consult the two books by W. J. Schmidt. 1. die Bausteine des Tierkörpers in polarisiertem Lichte. Cohen, Born, 1924-2. Die Doppelbrechung vom Karyoplasma, Cytoplasma, und of the chains, since simultaneous crystallization at several positions may freeze a chain in some irregular configuration and result in a polycrystalline material with a MRly random distribution of crystal axes. In extreme cases, as in Rubler, normal motion may result in nearly complete disorder. Added to see sources of defect are the effects of dispersity of molecular weight or irregularities in the intramolecular pattern, resulting perhaps from copolymerization or other chemical command decaying, and the presence of amorphous inclusions or foreign bodies in general. However, despite these numerous 2D DIUs, there is sufficient interaction between chain segments and enough periodicity over short lengths of chain to give a structure with inertial orientation of crystal axes and a inertial tendency for the chains to assume more or less excelsuted forms. In the crystalline regions, the U-referred form of Toulon chains is conditioned by such factors as the nature and size of substituent groups and the U-real bonds, double bonds. The mechanical behavior of a fiber is determined largely by the opposing tendencies of crystallization and the random coiling of the chain molecules. The contrast between the brithuous of sucrose and glycine and the flexibility of cellulose and hair illustrates well enough Ply difference between a perfectly crystalline material and its equally condensed but slightly disordered counterpart. IDI physical basis of other properties of condensed linear polymers will become evidered in the ensuing paragraphs. H. Peculiarities of X-ray diagrams attendant upon the crystallographic imperfection of fibers added the resulting difficulties of structure analysis. When a Jamlet crystaltio specimen is without any orientation of crystal axes, it yields a powder diagram line examined with X-rays. More commonly, examination results in a fiber pattern. One WLI resembles on the one line a rotation diagram for a single crystal, although obtained without moving the specimen. And on the other Leodide, a powder diagram in which certain arcs of the Debye-Squier rings are enhanced. Fiber diagrams result from an approximately parallel alignment of one crystallographic axis of the crystallites, while the remaining axes are disposed at random. Certain peculiarities of the X-ray diagrams of such specimens arise from their polyaristolane nature. Reflections often fall on the meridian, the line through the origin at right angles to the equator. They arise, therefore, from basal planes tilted with race P to the fiber axis. Such diatropic reflections, improbable from an accurately mounted single crystal, result from the imperfect axial alignment of the crystallites, and are often valuable in determining the identity period along a fiber axis. The imperfect alignment may be a random tilt, or it may result from special circumstances, such as spiral arrangement of crystallites or both. 2Ga, the spots on a fiber diagram usually lack the sharp definition of a single crystal diagram. Their more or less diffuse character is a consequence of imperfect resolution by a lattice of limited extent, a phenomenon with a well-known optical counterpart in line gratings with a small number of rulings. At yet the effect can be put to good use if the intensity distribution over each spot can be measured in determining Ply size of the crystallites. Clear are, however, alternative explanations, such as the effect of internal stresses on lattice constants, and the somewhat irregular large spacings are perhaps more reliably measured the origin. A relatively sharp definition of the layer lines corresponding to regular axial periodicity may be accompanied by spreading of the reflections aquoid layer lines. This indicates a criterion of lattice plane colorations in the axial zone, and in studies of keratin, it has been taken as evidence for the penetration of water into the crystallites, introducing a lattice. Methods of Riprovage orientation in gibers. It is clear that a detailed knowledge of fiber structure may depend upon the JAS ability of obtaining specimens with an adequate extent of crystallized regions, preferentially oriented, if this be easily with all three axes parallel. Occasionally, natural sources of highly oriented material are available. Cellulose irie, the cell wall of Valonia, or Lalanestes, for example, and the filxer of natural silk. Examples are not very ornanon, and even natural silk can be made much stronger by causing the silkworm to produce it under tension. Fretching is often affected in J-reducing orient sexual specimens. Fibers edged Gerschitzgion, UF myazin or of cellulose are more highly oriented if dried under tension, while rubber and weathered zilre and certain related synthetic J-products such as the polyvinyl derivatives and polyisobutylene actually remain oriented only as long as the tension is maintained. RIN orientation, which accompanies viscous or plastic flow of solutions or melts of linear molecules, is also made use of in the formation of oriented sheets or fiber dyes. By extrusion through a die, the I-era crystalline groupings formed during flow tending to persist in the transition to the solid state. Other mechanical devices are known and are of considerable industrial importance, such as the calendaring or rolling of plasticized material, which involves both stretching and lateral compression, ENA in some cases. Lateral compression even induces parallelism of the crystallites with respect to a second crystallographic axis. In addition to the fiber axis, an occurrence which seems to imply a relation between their morphological and axial dimensions. Blias 285, P. Bragg. The Ristoliic State, Bell Lomon, 1933, P. 188, H. Mark, 1934. Cited by R. Gelowiak, Clasliety, Plasticity and Structure of Matter, R. Brill and E. Halle, Naturwissenschaften, 26, 1938. S. Euler, J. Erosa, and has been of value in identifying certain spacings in moist keratinide, has made possible the production of rotation diagrams of cellulose DPTA in the case of fusible polymers. Crystallization may be promoted by solidification near the melting point or by annealing after the melt has been quenched. The rate of crystallization varies greatly with the nature of the chains and their degree of interaction, depending in all probability upon rotational freedom. The process is essentially the same in reverse as that which produces increased symmetry in crystalline paraffins on luting and is accompanied by disappearance of diatropic reflections and resolution of certain layer line reflections, while the latter is revealed by their coalescence substance to the vapor of a suitable solvent which penetrates between the chains, ruptures hydrogen bonds, and thus promotes free rotation. Undeniably, the same in chinisin plays a part in Tli formation of an extremely highly oriented native cellulose from cellulose hydrate by heating in glycerol at 250 degrees Celsius, procedure that has made possible the production of very sharp and detailed X-ray diagrams. D. The crystal structure of certain synthetic polymers. E. Or all such procedures have been tried, a fiber photographs a natural material is usually still far from perfect. Added to this serious source of difficulty in carrying out an X-ray analysis of the crystallized component is the uncertainty, which often surrounds the chemical constitution of naturally occurring substances, a difficulty which in the past has perhaps caused true progress to be simulated by mere facile juggling with analogy and numerical coincidence. The study of synthetic materials of known constitution, with its almost infinite scope for the controlled change of parameters, would seem to offer a more solid basis for an understanding of the architecture of natural polymers. Such investigations, impelled by the exigencies of industrial development, and issuing largely from commercial laboratories, are in their infancy, still greatly outnumbered by those dealing with rubber and the textile fibers. Although some important principles of fiber structure have been deduced from this more numerous group of early studies, which include the cell D-rated researches of Meyer and Mark and of Asbury, We shall begin more logically. It must be remembered that the advantage of a definite chemical constitution is by no means easily achieved in practice. Perhaps the lack of any systematic work on structures is due largely to the difficulty of ensuring uniformity of molecular size and constitution. We shall refer here only to CFM Matthew T.R. Faraday SOA 29, 122, 1933. C.S. Fuller, W.O. Baker, N.N.R. limers formed from reactants, and by processes seem to preclude the formation of branched chains. We shall, moreover, take for granted the coexistence in these preparations of crystalline and disordered states, ignoring those changes in the X-ray pattern, such as improved definition, resolution of fused lines, and so on, and which merely provide an index to the degree of orientation, and shall consider only the structure of the crystalline portion. The most definite information is often obtained from the identity period, the direction of the fiber axis. In a short chain paraffin crystal with N carbon atoms, the identity period is determined by the presence of basal planes. S are rated by the length of the extended zigzag carbon chains. If plies are vertical to the basal plane, or by the vertical components of the chain length if they are tilted, while a secondary period, indicated by an enhanced intensity of the order basal reflection, corresponds to the length of two carbon-carbon linkages resolved in the direction normal to the basal plane. In a high polymer of the polymethylene type, on the other hand, the long spacing is absent because the chains overlap. The Ordi identity period observed is that corresponding to the doubled bond length. This behavior is readily modified if the uniformity and inertness of the methylene chain is disturbed by almost any means, such as the introduction of a double bond of a polar group or a bulky substituent. The simplest case is found when polar groups are introduced with strict periodicity. These provide centers of crystallization or lateral cohesion along the chain lengths and generate characteristic reflecting planes, which, assuming the function of the basal planes in crystals of short-chain aliphatic compounds, again give a long identity period. Polyvinyl alcohol and various linear polyamides and polyesters provide interesting examples of such intramolecular identity periods. The chief effect of inert substituents of double bonds and of chains linked up by oxygen atoms seems to be a distortion of the chain from the plane zigzag form into some kind of helix or spiral, which gives a long identity period, corresponding to the pitch of the screw and a decreased interatomic subperiod. The reasons for this are probably various. In polychloroprene, chi-Z-chi-ko-1, sil-2-chi-N, the identity period is 4.8 in rubber or polyisoprene, chi-H2N2net. It is 8.2, rather less than twice the polychloroprenene value, corresponding to the distance between alternate methyl groups, with a contraction of Tli fully extended chain by about 0.35 a per pair of chain atoms. Il polyisobutylene, CH through 2AGN, the identity period is 18.6311, with a very strong 8th layer line, and a subperiod 2.33a, JAG thus cited by R. Brill and F. Hal-Iveth, an Ineor reference to W.H. Carruthers, EFFW our others, in Angstchem, 2630-1934. Compare K.H. Meyer and H. Mark. There are 8 isobutylene units in the fiber period, and it has been suggested that successive methyl group pairs are rotated through 4 degrees, completing the cycle within Tli fiber period. This is presumably a chain distortion arising from steric CFL-X and is reminiscent of Tli twisting of the CC bond in ethane, the presence of glycol or EO for her linkages in Tli chain likewise causes a helical form to be. The effect is marked, e.g. polyoxymethylene and polyethylene oxide, Q220, and is even to be earned in the polyethylene esters of dibasic acids. Particularly in the returning to the question of extended chains interlinked by polar groups, we find several points interestingly illustrated in recent papers. Polyvinyl alcohol has received a comparatively complete structure analysis, suggesting the presence of double chains associated through hydrogen bonds, figure 19, and linked to neighboring pairs only by residual force. In the linear poly open circles, oxygen, lost circles, carbon, QN, the same principle operates. But the actual mode of alignment of polar groups is somewhat more complex. In both cases, the fiber period corresponds to the length of the repeating chemical unit, if this is assumed to have the form of a slightly contracted or a slightly tilted chain. The polyesters also show a strong reflection of spacing 2.13a attributed to an oblique plane containing two carbon atoms, figure 20. In the even esters, represented spacing formed apparently by a longitudinal displacement of carbonyl groups in neighboring chains, figure 20, while there are also strong 12th order layer line reflections, showing that the carbon atoms are disposed in horizontal planes. The azolate W equals 7 gives no pineidal reflections. Apparently here the repeating units are exactly aligned, giving horizontal reflecting planes, and an orthorhombic unit cell closely analogous to that of the paraffins, figure 20. The situation is rather less definite in the polyamides, but it appears that here black circles, carbon heavy open circles, nitrogen, light open circles oxygen, left even polyethylene esters illustrated by polyethylene subarrow. Pineal planes with a maximum density of polar groups are indicated by the heavy lines. These give rise to long spacings, which are subdivided by the planes of spacing 2.13, involving two carbon atoms in each chain. Fiber subperiods of 1.27a, the distance between carbon atoms in the axial direction, are also present. The details have not been worked out. In particular, the oxygen-oxygen distance between chains is improbably small in the arrangement shown. Right, showing that the formation of such pineidal planes is improbable in odd polymers for geometrical reasons. The example given is based upon the properties of the 9-9 copolyamide, but with each methylene chain shortened by two CH2 groups for convenience in drawing. It is clear that the maximum amount of polar association is obtained when the polar regions are planes perpendicular to the fiber axis. The polyamide diagrams show a certain amount of disorder resulting probably from chain inversion. A similar effect can be produced when the periodicity of the dipolys is upset by copolymerization. A polymer formed, for example, from an equimolar mixture of the diamonds P equals 6 and 10 and the acids M equals 4 and 8 will contain segments of the 6, 6, 10, and 10, 10 units distributed at random along the chain. The fiber periods of these copolymers are strikingly different from those of several simple polymers and have so far defied interpretation. It is, however, noteworthy that the NIDGs of polar groups are sufficiently numerous for arystolysyl ion to occur. In other instances, as for example in J11A tape, the disorder resulting from the irregular sequence and orientation of tidal groups and the presence of UE esterified hydroxyls may destroy any semblance of crystallinity beyond the mere paracrystalline alignment of chains. The mechanical properties of linear polymers, the extent and stability of the crystallized regions in linear polymers are major factors in determining their mechanical properties. The chains possess in varying degree an inherent tendency to assume randomly curled configurations. If unknown, posed by a considerable density of interacting groups, by the presence of ring systems which lend a certain rigidity to the chains, or by mechanical forces applied externally, this tendency may cause the substance to have the disordered character of a liquid. Upon this property is imposed mechanical toughness arising from the entanglement and overlapping of long curled chains, and a rubber-like extensibility attributable to the ease with which they can be stretched into an extended configuration. The stretching may be accompanied by crystallization with an appropriate increase in density and evolution of heat, the chains then assuming a final form, fully extended or helical. As the case may be, that is not distorted rubber-like behavior are not completely understood. There is little doubt that flexible, inert chains with an open structure, DCH, are a primary requisite. The simple polymethylines do not satisfy this because of the close packing of their chains, which are subject to dispersion forces over a wide area, while polyisoprene, isochloropyrene, and aoleisobutylene are typically rubber-like. When stretched and crystalline, these substances are more rigid than in the relaxed condition. This is so when the crystallinity is maintained, either by continued application of stress or by cooling to a temperature at which the lattice forces exceed the thermal forces of a disorientation. The same is true of polymers, which, by virtue of their polar character, do not spontaneously revert to a disordered state at ordinary temperatures, called jot. It is widely agreed that fibers of these substances owe their flexibility partly to the pliable fibrillar portions. Those regions of loose or defective structure that interlink the crystallites, and partly to the loosening of lateral forces within the lattice by the presence of bulky substituents or small molecular penetrants, which diminish the effects of hydrogen bonding. Such plasticized fibers have something of the tugliness and flexibility of rubber without its long-range extensibility. Increased crystallinity and increased density of strongly reactive groups, on the other hand, result in more rigid, strong, and inextensible fibers, cellulose. Of the naturally occurring fibers, cellulose has received the greatest attention. In the various forms in which it has been studied, it illustrates most of the known principles of fiber organization, being indeed the parent structure from which these principles were deduced. The properties of cellulose are probably due in the main to a single substance, a linear polymer of cellulose, 4,3-glycosido-D-glucose, long and comparatively rigid chains, of which have a Satinio tendency. By virtue of hydrogen bonding to form crystallites, these often incorporating the ends of several Y-polymer chains, but nearer extending along their entire length, are interconnected at random by the loose, flexible strings of single chains emerging from them. The effect of stretching fibers and oriented sheets of cellulose are roughly what would be expected from such a structure, being highly dependent on the general direction of the chains in relation to the direction of the APP, live stress. In cotton and ramie, in the very highly oriented Lilienfeld rayon, the chains nearly coincide with the fiber axis. These fibers are strong and relatively inextensible. In flax dye's modulus may be nearly as high as the value calculated for stretching the covalent single bond between carbon atoms of the rayon. On the other hand, with transversely oriented chains, is ductile and can be stretched by as much as 30%. The rupture stress is similarly anisotropic. When stressed in the direction of the chains, a fiber can be broken either by pulling the ends of the chains out from the crystallites or by breaking covalent bonds. The extremely high tensile strength of well-made fibers bears out this statement of the possible mechanisms of ruptures QDE. Without excluding either, it has been guessed from the angular width of the X-ray spots is G, and by the observation of diffuse reflections near the originate, the crystallites in cellulose are at least 50 wide and more than 600 long, but it is improbable that they are as uniform in size and shape as this result might suggest. Concerning their structure, it may be asserted that only the most elementary features are well established. Compare AV. Gray whistling protoplasma 26, 251 1936. O. Kratky and H. Mark, ZCGF Physik Chem 36B 129 1937. K. Sauter, ZC Schergfer Physik Chem 36B 117 1937. H. Mark, J. Phys Chem 44704 1940. According to earlier views, the crystallites or micelles form discrete units. Compare Meyer and Mark Ref. 309, pages 150 MFF, J. Trogus and K. Hesper D. Deitch Camges 68 1035 1935. K2 Meyer Cooids Chapter 3 62 819. Most of the observed reflections, which have with recent technical advances become quite numerous, can be referred almost equally well-chained to either of two unit cells with a common fiber axis B of 10.3 to 10.4a. The length of one anhydrocellulose unit, the A and C axes of the two cells stand in approximately diagonal relationship to each other's, as shown in Figure 21, with some uncertainty as to whether they are orthorhombic, equals 90 degrees. or monoclinic 3, around 84 degrees. The larger cell contains 4 in the smaller cell, 2 upper left, basal projection showing the packing of chains in cellulose. Her arrangement. Can he refer to either of 2 unit cells, the dimensions of which are shown? Upper right, showing the indexing of certain planes in the 2 unit cells. The plane, 3, in the larger cell obviously cannot be indexed rationally with reference to the smaller cell. Lower left, projection of the cellulose molecule according to K2 Meyer, and L-MIST are Dietrich-Keldios units. When certain artifacts in the experimental data have been disposed, the only reason for preferring the larger cell is the questionable existence of a reflection parallel to 101. In the small cell, which 534 Polanyi, Naturwissenschaftlichen 9, 288, 1921 monoclinic, K.H. Meyer and Sukumark, Ref 64. Pages 94 FF requires a doubling of the axial lengths for its rational indexing. Thus, 101 in the small cell becomes 2 in the large, and the questionable reflection can be indexed as 3. The spreading of certain reflections from planes at 45 degrees to 101, small cell, along the Debye-Skerrer circle containing the disputed reflection is, however, so great that it cannot be certain whether the latter is really present. It is agreed that the arc in question is composite. The presumed molecular dimensions of cellulose are consistent with the orientation of the chains in the manner shown. In figure 21 with TT, this arrangement gives rise, however, to certain difficulties. Since Tli cellulose unit, as ordinarily conceived, possesses a diagonal screw axis, a circumstance that demands systematic extinction of the odd orders of the basal reflection, OCO, actually. Certain of these forbidden diatropic reflections are present, although with very low intensity. It is quite likely that extension of recent work on the Strucosine fact. For the present, we have only the tentative suggestion that the exacting requirements of hydrogen bonding between cellulose chains distributed statistically in the axial direction B and D may cause a slight displacement of the oxygen atoms G and G shit. This distortion, generating in effect a twofold symmetry axis through oxygen atom numero or perpendicular to the plane of the rings, will make the direct and reverse chains almost exactly superimposable, and therefore equivalent from the point of view of molecular packing. At the same time, the diagonal screw axis will be abolished. G protein fibers, it may be claimed with little hesitation that the insoluble proteins have the essential properties of linear polymers which occur in characteristic fibrous or laminar habit, the laminar forms being themselves composed of matted fibrils. This is true not only of the well-known thread-like proteins such as silk, hair, wool, and tendon, but also of the contractile elements of muscle. If it is reasonable to link this universal property with the hypothesis of polypeptide chains, it is necessary to attribute the great diversity of projorieties within the group to the diverse nature of the side chains, the interaction of which may be supposed to determine the particular form assumed by the peptide backbone under given conditions. Postulating such a structure, it is equally reasonable to expect to find in the fibrous proteins that juxtaposition of order and disorder DR, and that correlation BC between mechanical and chemical properties that we described in the Sint-Loop Tech polymers. A limiting case is that in Willich, the lipid chains are present in the fully extended form. The X-ray pattern TF native silk fibroin with a unit residues has been interpreted in this sense, the unit translation 7 are representing the length of 2 peptide linkages. With this is correlated the anticipated very small breaking strain. A similar X-ray UA turn, referred to by the prefix 3, and somewhat similar mechanical properties, are characteristic of feather and are Tillian carinin in the natural statuses and also of other forms of keraterian and of mucin litum. These are stretched under suitable conditions to the maximum extent. And incur as detranslation in the unit cell 9.88 is correlated with the presence of longer side chains than the methyl groups of silk. Most native or unstretched keratins and myosin in relaxed dried muscle T give almost identical X-ray UA turns, which are quite different from the S diagram. The side chain spacing 9.8A is retained, but there is a pronounced axial period of about 5.1A, while the A translation in keratin has been given as 27A. Although these facts point clearly to a chain folded in some regular minor in the plane, perpendicular to the SID chains, the form of the folds is by no means established. Recent speculations, however, improve dominantly upon the earlier ones. Whatever the structure of a keratin, it is certain that the intramolecular transformation to the zero form is a complex one, involving rupture of several types of linkage, for the mechanical properties of this substance are remarkably intricate. The maximum extension corresponding to complete transformation to the zero form is about 100%. The first 20% is without effect upon the X-ray pattern and is attributed to unfolding of the chains in the amorphous regions of the fiber. The next 30% requires the presence of moisture and is accompanied by some change in the X-ray diagram. These changes are reversible. The complete transformation requires heating in steam or immersion in sodium hydroxide solution and is irreversible. The fibers stretched in steam or alkali, having evidently suffered hydrolytic rupture of certain linkages, is in a labile condition, and its behavior depends on the conditions under which new linkages are permitted to establish themselves. Plunged into cold water, the stretched fiber retains its maximum length and can only be caused. R.O. Herzog and W. Janke cited High K2 Meyer and H. Mark Refs 9 B21. R.F. Snyder. Brill. Liebig's Analyse der Dürreiter 434 204 1023. K2 Meyer and the suit marked Birdie contract by being related. If allowed to relax in steam or alkali, the fiber becomes much shorter than its original unstretched length, supercontraction, and after this process, probably one involving principally the non-crystalline regions, and occurring, therefore, without any necessary accompaniment of altered reflecting power of X-rays, it can be reversibly and completely transformed to the ET state by stretching at ordinary temperatures. The linkages in myosin are considerably more labile than in keratin, a fact that has been associated with the smaller sulfur content of the former protein, and in the consequently diminished importance of covalent SS linkages between neighboring chains by myosin may be caused all the more readily to supercontract, which it may do indeed while still in the A form without previous stretching. The remaining proteins have received attention, appear to exist in fornus analogous to and supercontracted keratin, with important differences. The X-ray diagram of collagen, the chief protein of connective tissue, tendon, and cartilage, can be referred to a unit cell, E5 along in tie-E direction of Cli fiber axis, corresponding to a residue length 3, and suggesting a somewhat contracted cleon B. The supercontraction of collagen to about 1/4, its original length is well known, being produced by very moderate tyranny. The substance becomes rubber-like. Gelatin, a partly hydrolyzed collagen, resembles supercontracted collagen in that stretching causes the amorphous X-ray pattern to be replaced by the fiber pattern typical of native collagen. The material comprising certain supporting fibers in the fins of the Lazarno branch resembles collagen in being transformed on heating to a supercontracted Fornridge VX, according to the evidence of the X-ray diagram, is amorphous at and acquires a certain degree of crystallinity at room temperature. The crystalline picture closely resembles teliades of the native substance, but the thermoelastic properties indicate that, as in other cases, the process of supercontraction is one of liberation of flexible chains from a state of association in a lattice, elastin, present with collagen and connective tissue, elastic fibers. Possesses in the native form thermoelastic properties and X-ray scattering powers reminiscent of those of supercontracted collagen. Cachichichi, it is perhaps pertinent to refer to the evidence derived from X-ray studies as to the relationship between crystalline, corpuscular, denatured, and fibrous proteins. The evidence is scanty, and no very far-reaching conclusions should be drawn. Reflections corresponding roughly to the backbone and side chain spacings of the JS fiber pattern occur quite commonly in crystalline proteins and viruses, and may become much sharpened by denaturation. a G-tree. Thus, there is some little reason for drawing an analogy between the denatured state and the extended or 3 form, but there can be little immediate justification for supposing the A folding to bear any but the most general resemblance to the configuration of the corpuscular molecule. The supercontracted fibers have something of the amorphous quality to be expected of a collection of randomly coiled chains, and the circumstances under which supercontraction is observed are clearly such as would favor the thermal disorientation of all chains which under ordinary conditions are subject to powerful constraints. Concerning the manner in which this haphazard coiling can be replaced by the ordered convolutions of the corpuscular protein, there is no information whatsoever. The two processes seem at first sight antithetical. Perhaps a detailed study of the virus proteins will throw further light on the subject. Possibly, even a less naive interpretation of fiber pictures will perform this service. For the observation of axial spacings of several hundred angstrom units in collagen and other fibrous proteins suggests an architectural scheme more elaborate than that implied by the 3 structure in its elementary form. H chromosomes. The chromosomes, the most important of all natural fibers, are also the least accessible to direct study. Consequently, their possible resemblance to one of the types of fiber already discussed is a matter for speculation, insecurely based upon cytological observation. And held together, we may crudely represent the prophase chromosome, and perhaps also its precursor in the interkinetic nucleus, as an elongated body, perhaps 10A in length and 10 thick, although the latter dimension is open to question. The contracted metaphase chromosome may be 10 long, and 10 a thick glycoprotein protein or protamine and nucleic acid are present at all points along the length of the chromosomes, although their proportions may vary from point to point, showing a fact that partly underlies the banded teeth. Kasperson, Scandinav, Arch 73, CFLA 1936, CPA Emersky, and W. Polsky, Sir 6 190, 1942. Appearance of stained specimens. The observed double refraction of Clermosines is in accord with this result, and although often complicated, accompany changes in the hydration of chromatic material, is such as to suggest that the nucleic acid molecules are arranged lengthwise in the axial direction of trichromosome, but nothing is known concerning the oriented. Kion of the protein comma 1. The fibrous habits, stead by the linear dimensions of the chromosomes, is borne out abundantly by their behavior during cell division and by the results of intercrodissection. Their extreme flexibility is shown by the remarkable coiled-on figurations that they temporarily assume during meiosis and cell division, and their marked axial cleavage by the longitudinal splitting untergons during the same processes. At the same time, the formation of chiasmata. Apparently, in response to local torsional stresses involved in the diploid CNC resolution of the coiled 4-strand bivalent chi betokens a certain mechanical weakness that at once precludes an extremely long covalent chain as the basis of chromosome structure, and is equally at variance at first sight with the evidence of extreme extensibility, provided the linear elementions of the chromosomes are, of course, consistent with a fiber structure based upon polypeptide strands associated laterally with TLOY degree of overlap and disorder characteristic of most fibers. It has indeed been considered that such a structure has a certain prior probability in view of the linear structure of the protamides, but little more can be said at present. With 3.5A as the length of a peptide residue and perhaps 8L as an average lateral spacing, a chromonema 10x10A would be about 3.1 duoptide linkages in length, and a diameter would include about 120 chains. It has been suggested that such a polypeptide fiber structure could underlie the genetic linearity of the chromosomes, the specific character of each linear segment being established not only by the axial sequence of polypeptide residues and side chains within a single strand of the fiber, but also by the varying patterns of neighboring strands within the segment, and 363 J. Clement didoppelbreturate von Karyoplacina, Zytoplacina, und Metaplop. Fibers is tacitly considered to be in abeyance in Ibis case, so that the rock in coin one end of a chronozoin appears as a liwar SCGEans of height 2, li origi. Seed segreals outrops niora closely analogous to a particle of to mosaic, a virus than to a thread of mosaic. Aside from the lack of positicsy evidence in favor of such a hypothesis, it fails to assign a satisfactory rho to the nucleic acid component. There is no particular virtue in the fact that it straddles the gap between the two extreme possibilities of chromosome structure, the first of which is represented by the picture of the chronionema as a protein fiber playing the role of a mechanical carrier of specific substances, chromomeres, just as a clothesline carries a variety of and the second showing the genes as elaborately organized regions of unknown constitution, each of which adheres by some unknown nuance to two neighbors, like a row of dancers holding hands. It is idle to discuss these possibilities until the linear differentiation of the G-unit units shall have become more clearly defined and more closely correlated with the physical linearity of the chromosomes. General bibliography, Gapler 8 Lernbers are the ideal structure of protosome, as determined by microdistal ion and injection, incineral geology, ODK Audrey. University of Chicago, Purchase, Chicago, Huggins, M.E. L. X-ray studies of the structure of compounds of biochemical interest, and James R. W. X-ray oestellography, Methuen, Lomlon, 1980. Mark II. Physical Chemistry of High Polymeric Systems, Insentience, Meyer K.L. Recent Developments in SLAR H. Chemistry, Advances in Alloy Science, Ed Meyer, K.H. and H. Mark, Der Aufbau der Polymeren Naturstoffe, Akkad, Verlagskus, Picken, LFR, The Fine Structure of Biological Systems, Ryle, Reverend, 16, 188, 1940, Symposium on Liquid Cry, Styles, ZT, Sharps, Christ, 79, 1981. St. Georgiae, AIDN, Protoplastic Structure and Function, FM Zoology, 98. 1941, Waddington, Ill, An Introduction to Modern Ionetics, Allen and Elwin Nixwydon, 1989. Waddington, C. Ill, Ordani Sears and Ionizersi Press, M. Learage, 1941. Introduction to Subdivision, or the Enclosure of All Living Matter, E.T.T. Bronze, Septa, Pellihides, or Fluid Skins, is a fundamental fact of biology. Between the extremes of swirlural rigidity and the easy deformability of the euarimate I fluid sy leer, ye encounter all possible mechanical qualities, associated with a great diversity of form and function. It is natural to inquire into the behavior of matter in bulk when it is attenuated in the form of thin fluids, but this is not as a rule the most utralitable appeal to the proof. All matter becomes anisotropic at its surface, but it is statlum that cernidide mechanical attenuation can be carried so far to lie at tin anisotropy is not masked by the known properties of the material in bulk. This is not to deny the importance of such work as that of Lardy on Teuanism of lubrication, or the suggestive use of the rigid liu-ecomb structures that can be formed by soap bubbles. But the boundary stale is be sludged by starting with a single interface. FER here, the anisotropy, all the surface layer is as arly exhibited. Above all, in the phenomena of sear-phase tension, as it is by the layer of oil between two ground surfaces, by molecular films of soap. It is further possible to introduce other substances into SEU. An LT studied the change in properties brought about by their UV. ECC is probably the first stage in the genesis of all bounded membranes. And in the detailed study of interfacial films, it is perhaps possible to find the in vitro counterpart of some of the reactions which lead to the differentiation of protoplasmic boundaries, their specialization as silos of functional or metabolic activity as selectively or meiola barriers delimiting the organism from its environment, or as skeletal structins. Interfacial films, for example, readily become rigid or elastic under some circumstances. We need only appropriate localization, therefore, to introduce a new anisotropy into the surface of the primitive sphere and to cause spontaneous deformation. If such influences are sufficiently numerous and complex, it is clear that we can eventually get a great variety of cellular structures, although it is admittedly a far cry from see also liliography at end of chapter. W.B. Hardy collected Jappers, Ainridge Losh, references to separate papers on this subject, see Ref 327, p. 227. Our general theoretical statement to a knowledge of the processes leading to the beautiful spiral arrangement of cellulose fibers in the cell wall of Valuyi cheeks, or even to the simple discoidal structure of the mammalian in devoting our discussion. In this chapter, to the properties of oriented metafacial layers, we are attempting, as many others have done, to introduce into the idea of surface activity a new restriction, and therefore a new source of that specificity which is characteristic of vital reactions. Where the mere increase of interfacial area consequent upon subdivision might once have seemed sufficient to explain many of the differences between homogeneous and heterogeneous systems, it now is necessary to attribute an equal importance to the actual molecular configuration of the interface. 2 Gibbs equation, soluble molecular layers at an interface. Let us consider first the properties of the interface between 2 immiscible fluids. Its most elementary property is that work must be done in order to increase its area, because this involves the rupture of cohesive forces between molecules. The IU surface being composed of molecules which formerly were situated in a symmetrical field of attractive forces, and now are subject to a resultant pull in a direction normal to the interface. The work required to increase the area is thermally is wired, y, which may be defined as a surface tension of y dyne, over 1 centimeter. Substances present in aqueous solution introduce new intermolecular fields of force, either more or less intense than the forces operating in pure water. Their nature is reflected in the surface composition of the solution. Ions or polar molecules, by virtue of their powerful electrostatic interaction with water dipoles, tend to be pulled into the interior of the solution, leaving a surface layer of pure water which, insofar as it is influenced by the solute molecules in the interior, has a higher surface tension than that of pure water molecules containing nonpolar groups. Conversely, tend to displace water from the interface, causing a decrease in surface tension. In a homologous series, for instance, the surface tension varies in a regular manner with the length of the carbon chain. It is often possible to distinguish by measurement of surface tension between the opposing effects of increasing methods. Ref 270. E.A. Hauser in Advances in Colloid Science by E0 Kramer, Inner Science Pub Inc., New York, 1942-1, pages 891 to 415. Generally, the surface tension decreases continuously with concentration of a surface active solute, approaching a limiting value at high concentrations. Various irregularities have been reordered, which aptitude here, to be connected sometimes with a change in the nature of the solute with concentration, as in the case of the soap solution studied by Miclia, but more frequently with failure to attain a true equilibrium between surface and bulk phases. This may be a very sluggish process in systems containing asymmetric molecules and antagonistic grows. The basis for quantitative studies of interfacial equilibria is the isotherm derived thermodynamically by Gibbs, an approximate form of which may here A is the surface excess, or amount of adsorbed solute per unit area, and C is concentration of solute. In the bulk GISB quantity F has been introduced because it is often more convenient to use than 7. It is the surface pressure and may be defined by considering an imaginary movable barrier of legibly separating the surface of a solution from a surface of pure solvent. Since the surface tension 7 of the solution is lower than that of the pure solvergite 70, a force F dyne crew act on the barrier in such a direction that the surface of the solution will tend to expand at the expense of the solvent surface. If the Harrier is allowed to move a small distance, dxu work done will be 70 to 7 GY dx. This must also be phi dx. Thus, F is equivalent in physical terms to an osmotic pressure. It represents the two-dimensional pressure needed to prevent dilution of the surface phase by pure solvent. To return to Derby's equation, 21, we see that it represents a relationship between surface tension lowering, surface excess, and bulk concentration for ordinary, moderately soluble substances. The amount present in the surface layer can be varied by changing the concentration of the solution, and Gibbs' equation can be tested, at least in theory, by measuring the surface excess and the surface tensions for solutions of several concentrations. It seems to be agreed that the verification of Gibbs' equation may now be considered reasonably well established by measurements on such solutions. Accordingly, it is permissible to use the equation for calculating the surface excess from surface tension measurements. And certain interesting facts concerning the structure of the surface layer have been revealed by such data when used in conjunction with empirical surface tension equations. For very dilute solutions, for exact definition and derivation of Gibbs' equation, see Ref 370. Giving with the Gibbs CAN, where A is the area per molecule, if the mobile of solute in the bulk phase can be neglected by comparison with ERR equation 24, is simply the perfect gas law. For very dilute solutions of short-chain fatty acids, this has been confirmed. With increasing length of chain, the values of Fia are too small. This is probably due to lateral cohesion between the adsorbed molecules. With increasing concentration, on the other hand, the values become too large. Obeying in empirical excipiation in severe is a correction for the ion account. I by the molecules and is analogous to Ashton der Waals ray Sion forces. For all chain Nigerts, it is about 25A, or excipial roughly to the cross-section of molal chillness, the molecules evidently stand more HFS on end in the more concentrated adsorbed film. Apply a actual value of the constant B, equation 2pi varies regularly with the structure of the solute. This is merely another way of stating Trobe's rule. Trobe shows the value to increase geometrically from one member of an homologous series to the next. Thus we may write empirically, where n is the number of Earl AFN atoms in a given homolog, and k is a constant differentiating the series. It is arithmetical increase in B amounts to an arithmetical increase in the work of adsorption, which for V series small values of C can be shown thermodynamically to be where R is the thickness of the surface region. Thus, combining 26 and 27, we may write Langmuir's analysis of the data suggests that the term WXEO, which is negative, represents the effect of the hydrophilic groups of the molecule, and EN the effect of the CH2 chain. Values of the constant K and of XO for various groups have been calculated. From these and ECPHUA, it is thus possible to calculate X for higher members of homologous series, in which no experimental value can be assigned to C because of the infinitesimal solubility of the subshioka. Then, if necessary, equation 27 can be used to calculate B according to Thribb's equation. A value can always HV assign D to C for any pair of values F and R. The surface active substance may, however, be so extremely insoluble that F and L can be varied over a wide range without any measurable amount of material passing into solution. Such substances form insoluble lerins, which are studied by special methods, since the situation imagined in the definition of surface pressure can actually be realized. And Tly pressure of the film in contact with a Clige surface can be measured directly. There is an important intermediate region in which oddly soluble films decrease in area upon compression. For moderately insoluble substances of this type, the solubility is given by C of Gibbs equation and is a function of amount of solid substance present in the interface. Interesting preliminary calculations of the pressure solubilities of homologous polypeptides as a function of surface pressure and molecular Weigelt of CH and given by Lang and Watt. Can he determined from Nation 1 by introducing an empirical relation between surface tension and concentration C as that of Siskowski, where C and A are constants. Combining Whitley 2.9, we find where GA is the surface, when XS, when C is very large C, rest gen to the value for a closed pack F film. We then use Ilkay tenon integrate equation 21 obtaining, assuming arbitrarily that 1 mg of polypeptide covers 0.5 m. When close packed on a water surface, we find where m is molecular weight. To apply equation 31, we now only need to know, in addition, the value of $1. This can be calculated by using equation 28, modified to include terms for the side chain of the polypeptide, and then equation 27. Each peptide unit is assumed to have a residue weight, 120, the average value obtained for several proteins, and an effective number of carbon atoms estimated from the average number of TH2 groups and hydrophilic groups in the side chains. The XO term includes values for peptide co and NH groups when the appropriate substitutions are made. When the appropriate substitutions are made, equation 31 takes the final form calculation shows that with polypeptides of the average composition of a protein and molecular weight 2000, pressure solubility would account for so little of the material in the film and would occur so extremely slowly as to be undetectable. With a reasonably large volume of underlying solution and adequate mixing, measurable changes in area should occur upon compression. When M is 1200 to 1700, when W is greater than 10, it is found that the substance dissolves very rapidly. The proteins, if they existed as extended polypeptide chains of molecular weight 35.0, should be extremely insoluble. And the fact that they are actually very soluble lends further conviction to the evidence for their globular form and solution. The theory and technique of pressure solubility measurement I remise to become important in the estimation of the amounts and molecular weights of protein degradation products. 3. Insoluble monolayers in SABSEC. 2. We discussed the transition from the simple Gibbs adsorption of solutes to pressure-soluble films, and finally to films which to all intents and purposes are insoluble. The insolute blowout films are usually prepared by spreading over the liquid surface. Such spreading either occurs spontaneously or can be promoted by dissolving the substance in a volatile solvent, just as the formation of a Gibbs layer requires the presence of nonpolar groups in an otherwise soluble molecule. So the spreading of an insoluble substance requires the presence of polar groups in a predominantly nonpolar molecule. The long-chain aliphatic hydrocarbons will not spread. The corresponding monobasic acids spread readily, continuing the gradual change in surface properties exhibited by the short-chain acids discussed on page 190, from the observation that the polar group provides a spreading force, and the postulation that only short-range forces operating between molecules in contact should be responsible for adsorption. It follows that fatty acid films must be oriented with the carboxyl groups in contact with the water, and that the amount of the fatty acid that can be spread on a given water surface is limited by the number of molecules that can be packed into a single layer. Monolayers can be less solids, liquids, or gases. The phase relationships shown by a particular substance in the form of a monolayer are not in general those found in bulk, nor would this be expected, for the orientation imposed by the submergence of polar groups in the substrate may interfere with the mode of packing naturally assumed, under otherwise analogous conditions, in 3 dimensions. The state of a monolayer, by definition, must be considered in terms of the mechanical properties of the surface which it occupies. These properties can be determined by special methods. Compressibility is usually studied by measurement of surface pressure as a function of area per molecule. The apparatus used being some modification of Langmuir's surface balance, in which the force acting on a floating barrier separating the film from a clean surface is measured. Viscosity can be determined from the rate of flow through a narrow surface channel, or by observing the oscillation of a circular disc, or a vane. Measurements of rigidity can also be made with the latter method. Rigidity can be detected without special apparatus by observing the mobility of talcum powder placed on the surface. Heat disposition of polar groups in a film and its homogeneity can sometimes be deduced from surface potentials. Although the interpretation of these is still in doubt, they are generally measured as a difference in potential between a reversible T-electrode immersed in the solution and a second electrode coated with a source of ionizing radiation placed near the upper surface. The ties of behavior encountered in relatively simple monolayers can be described by reference to substances with long hydrocarbon chains terminated desired sequence of phase changes upon compression by suitable choice of temperature, chain length, or size and shape of the polar part of the molecule. See Ref 370, pages 33 to 35, where other methods also are described. 898. The possible transformations have been enumerated and discussed by A.D.G. Dervikian, J. Fies Rad, 7, 10-333, 1939, B.D. Dervikian and M.M. Jolie, Ihid, 375, 1939, C.D.G. Dervikian, J. Chemberl, Is, 7, 931, 1939, Dervikian's contentions concerning the analogies between the states of monolayers and of three-dimensional matter have been criticized on numerous grounds by D.A.E. Alexander. Faraday, Adelaide, Subte 37, Ford Arn, E. Boyd, and W.D. Harkins, Bull Am Phys, Soc 16, 1940. F. W.D. Harkins and E. Boyd, J. for many substances at very large areas. The film is gaseous and extremely dilute. On compression, sudden condensation occurs at constant pressure to a very incompressible film of area between 19 and a per molecule, with which we may compare the values of about 18.3A obtained from X-ray data for the hydrocarbon C29 LFEO and stearic acid at room temperature and about 19.5 and near the melting point. Since the melting point of monolayers on water is almost invariably lower is almost invariable than that of the crystal, it is probably reasonable to conclude that the hydrocarbon chains in the condensed monolayers are vertically oriented. The compressibility of Sogden's films is comparable to that of a long-chain paraffin and Beale. Cheat's layer state of aggregatine depends apparently upon the nature of the end groups and their interactions. The film may be a brittle solid, as a stearic acid under certain conditions, a plastic solid, or an extremely viscous fluid. TA long-chain alcohols, the value for shoemaker's wax, compression of the condensed film, leads to collapse of the film structure at an area around 19A. In other cases, condensation may become complete at arenas greater than 0A. The values show considerable variation, lying in general between Z and 30A, the condensed film being initially more compressible than in the case on Z or above, but Sony Edians approaching the same area and compressibility at high pressures. These copper fills are usually ligute. Their area may be determined primarily in many cases by the size of the polar head groups, in the particular stable configuration dictated by the positions of the centers of polarity with respect to the surface and to other parts of the molecule. His can often take up a more compact configuration on further compression, as in the case of the methyl ketones and esters. When this occurs, the packing approaches that characteristic of hydrocarbon chains. If the terminal group is a single polar radical, such as hydroxyl, the properties of the film must be determined approaching more closely than 4.5A larger groups may hinder compression, as we have said. They may also interact. Thus, the large areas and rigidity OT condensed films of compounds containing the CO-nil linkage have been attributed to hydrogen bond formation between neighboring end groups. Tuning A. Alexander, Procroy, Soki, 179A, 486, 1942. It has also been noted that polymorphs of the aliphatic acids are known. 1. Nebdebor, Nature, 11950, 1927. Ibid, 634, F. Francis H. Piper and T. Malkin in Rock Roy, Silky 128A, 214, 1930. In one of these, the chains are tilted at about 60 degrees to the basal plane. The effective cross-section of such tilted chains would be about 28 temperatures well below the melting point. At higher T, ambicratiurous gaseous films may condense at a certain pressure to a much more compressible liquid, the discontinuity repercuting let condensation, LPO carrying at progress. I.e. structure of such lipid expanded films has been discussed in a classical paper by Langmuir. IO shows the equation of state for the liquid film to be this. Would be expected if the film had a duplex structure, consisting of an upper layer of hydrocarbon chains disposed at random with a constant spread Ine coefficient, and a lower gaseous layer of polar groups in solution. The equation of state for Tlilat would be JF. The 10QX ratio is not above the critical temperature for solidification. Compression of the liquid film adds to a further sharp discontinuity, which signals the transformation to the condensed state. This is not a phase change in the synchyl sense, however, because a DTS not occur at constant pressure. The surface pressure rises gradually from the nearly horizontal portion, immediately following the break, merging imperceptibly into the curve for Tli condensed state. Above the critical temperature for liquefaction, the gaseous film can be commodoressed without discontinuity. It shows increasing dexiation from the perfect gas law and increasing resemblance to the liquid expanded films, until finally a condensed film may be formed by way of a discontinuity, similar to that observed on condensation of liquid expanded films. The foregoing outline of the properties of long-chain monolayers contains an indication of the kind of information that can be gained concerning the size, sliopy, flexibility, and fields-offery of the hydrophilic and hydrophobic parts of monolayers, and some have been studied in sufficient detail, as have, for instance, some of the sterols, including ergosterol and its irradiation products and various derivatives of oestrin, for useful deductions as to chemical constitution to be made. In numerous other cases, the data are at present mainly of descriptive value, and no attempt will be made to review the subject here, despite the existence of several references to substances of biological interest. Study of such films in connection with the problem of hydrogen bonding in proteins is discussed by A. E. Alexander and E. K. Rydell, Nature, 147, 541, 1941. We shall, however, devote some space to a description of protein monolayers in view of the fact that protein films are present at nearly all biological interfaces. For protein monolayers at an air-liquid interface, A. The spreading of proteins. It has long been known that proteins are slowly precipitated when their aqueous solutions are shaken. Viflent 1 degrees, the still surface of a protein solution also becomes coated spontaneously with a film, but the process ceases before bad. Visible coagulum is produced. The rates of diffusion of protein to the surface are such that there may appear to exist equilibrium surface concentrations of protein for different concentrations of solutions. This is illusory, for in the course of 24 hours, practically all the protein in a solution of concentration, 10 to millimeters, deep reaches the surface and stays there. The film shows almost perfect elasticity and complete insolubility, being reversibly compressible to 1/5 of its area, whereas it should pass back into solution if its presence in the surface represented a true equilibrium between dissolved heat and adsorbed protein. A similar irreversible change often occurs if a drop of protein solution or minute particle solid protein is applied to a clean water surface under suitable conditions. Most of the substance remains in the surface layer, and the film thus formed can be studied by the methods already described for soluble monolayers. The mechanism of spreading is not completely understood. It has been found that the area of the film produced when a given amount of protein is applied to the surface of a solution varies very greatly with the pH and the salt content of the solution. The force area curves are usually linear or nearly so, over an wide range of areas, and the area found by extrapolation to zero force, limiting area, gives a convenient measure of the film area per milligram of protein originally applied to the surface. At the isoelectric point, the limiting area is frequently about 1 in what has been considered a typical case. It falls off sharply on either side of this point, and may again increase at pH values near the stability limit of the protein. These variations are misleading. The very low areas obtained at some pH values sometimes increase gradually if the time interval between spreading and compression is extended. Moreover, formation of films of large limiting area is promoted by the presence of electrolytes. However, give very similar force area curves to those of low area. Does not expand when the underlying solution is brought to a pH at which films of high limiting area are formed, nor do films formed at the isoelectric point contract when the pH is changed to a value less favorable for spreading. It is probable that limiting areas resent only variations in the amount of protein which enters the surface, XSE, a certain fraction being lost by diffusion into the underlying solution, or entangled in the air surface of highly viscous film. Since it is very hard to determine how much protein is lost in this way, the numerous studies of limiting area as a function of pH and other variables tell us only about the mechanism of spreading, and very little about the real properties of protein monolayers. Probably the maximum of about 1 F-tier from the true value of the limiting area, but small variations with pH and other properties of the substrate would be very difficult to establish. 6. There area curves of proteins. We have referred to the high reversible compressibility of protein monolayers. This statement requires qualification before the shape of the force area curves can be discussed quantitatively. Firstly, the course of the curves depends upon the rate of compression having a smaller slope when compression is carried out slowly. For bibliography of paper S by Gorder and others on this subject, CHH. Neurath and E25, Methods for Promoting Rapid and Uniform Spreading. I, by adding surface active soluble substance to the protein solution. CA1G, Dervichayacher 144 629 1939. B.S. Stalberg, T.R.R. Faraday, Sock 36 14 16 1939. 2. By applying protein along the line instead of at a point in the surface. C1 Langmuir, Cold Spring Harbor, Simp 6 171 1938. DII Langmuir and D.F.Y. JAM Chem, SoCast 62 277 1940. Secondly, the curves always show some hysteresis upon expansion, and Soinolini, explication of Lou theory of pressure, solubility suggests that Ply's collages are associated with Telu displacement of substances of molecular weight. Between 1,000 seem to eliminate Telu possibility that the effect is due. Dilution of unspread F-protein, Teresa's Lou, can be obtained from film shearers provided the times of compression and expansion are not altered. At least 2 types of fork area curves have been obscured. Lie majority of proteins give curvates of Telu type slione in figure EA2 for ovalbumin. Whitley a well-marked linear region to it. Hanges at the low pressure end to a curve of gradually decreasing slow Dry low of a linear portion is a secondary tenofistimation point, at which Tulu corn resibility D and a DDF has a minimum value low pressure region, often has a fairly definite area of Zenschurfers implicating that the film is coherent. In other cases, particularly for films on acid amyalkaline substrates, it becomes asymptotic to the a-axis. Second, tie of curve is roughly hyperbolic, so that the transformation point is absent, and the UVX are a wide range of areas. Such curves, remembering that the true areas per molecule are uncertain, we must select ways of measuring and comparing Fonk's area. curves in terms of arbitrary units of VLC. IOJ or Archie curves marked as surface compressibility curves. Mark K for ovalbumin 1 and gliadin Z abscissa as II will zero AI is area of OI2 at a surface pressure of 1 cm. Surface pressure ordinate is in diex centimeters, and compressibility ordinate is in arbitrary units. Bottom, the ratio of 3:1 plottle against the content of relatively hydrophilic amino acids for several proteins, explanade. An obvious init liad is to express Tli areas. A, in terms of that at A, slain lard resier of, say, 1 I ignite, or in or age-dale analysis, Leoac Leolia, Yaranjan. He ends DW Chula special signify Lajajanwir and Wa have published first for a number of proteins. Isla areas Aja at 25 cm. Range from 0.06 and 0.14 for gelatin and gliadin, respectively, to 0.58 for insulin. JT is not certain that these curves are suitable for accurate quantitative comparisons. Protein films lend to L-econy more coin-eresible, the larger the relative area of free surface available for SEI reading, so that if varying amounts of protein are SJ read initially, OVIC the whole surface of the Langmuir trough, and then compress. Both Ajax and the minimum compressibility values vary with the actual area in centimeter of the film. At some standard Jewisher dip, there is little doubt that the structures of the films under these various conditions differ. And it is obviously necessary to standardize the conditions before hourly curves can be constructed for different proteins, or for the same protein on different substrates, roughly SDK. The minimum compressibility values for all proteins tend to converge when the area for spread ion is very restricted, while they approach individual limiting values, which vary in a highly characteristic manner with YIH. When infinite area is available, closely correlated with these changes is the coexistence of a coherent and an expanded phase at very large areas. The viscous films and the mobile hysteresis free of films of Jolly. According to the A films are gaseous at areas of about 100 mg/mg, with apparent molecular WCIs of 40.0, 27.0, and 12.0 for ovalbumin gliadin, and hemoglobin CCI ideally of the right order of magnitude for protein molecules. On the other end, it is possible that there is some relationship between the pressure-soluble materials found by Langmuir and Waugh in compressed films amid this mobile phase, although the latter, Kumjur, SC Sci certainly gives a characteristic protein curve. The whole question requires more detailed study. That considerable rearrangement of polar groups occurs at a certain stage of compression. Large changes occur also at acid and alkaline reactions. These are greatly reduced by the presence of salts in the substrate. Protein films exhibit remarkable changes of state during compression. The most elementary facts can be demonstrated by very simple observations. The behavior of dust particles, displaces the passage of film material through a surface channel 5 to 10 millimeters wide. Practically all protein monolayers become gelatinous and clastic when compressed. The pressure at which solidification occurs for isoelectric films, or films on pure water, vary wide limits for different proteins, and also depends to a considerable extent upon the history of the film. In many cases, the accompanying structural changes occur slowly, and gelation may take a few seconds or a few hours. It can usually be reversed by expansion or mechanical disturbance, the films being markedly lixitropic. albumin and pepsine are characteristically rigid at very low pressures, while insulin and gliadin remain fluid, when freshly spread up to 10 or 15 cm. These differences are not correlated in any obvious way with other properties. Gliadin, which forms liquid films, is very compressive as insulin, which also forms liquid films, is almost as incompressible as ovalbumin, which is solid. Aged gliadin films appear to solidify at a lower pressure than fresh films, and at a point coinciding with an inflection of ply force area curve, but no such coincidence can be noted in the case of other proteins. Films of ovalbumin on sodium tungstate may be extremely rigid at 0.19 centimeters, and yet show the usual inflection at higher pressures. On the other hand, the changes in compressibility which mark the transition from 13 to a films, as the area available for spreading is increased, are accompanied by an increase in the gelation pressure. According to July, the pure films compressed. Quantitative studies with the oscillating disk method in its several forms have given values for the absolute viscosities of films in the very limited low pressure region, which is free from anomalous effects, and apparent value at high amplitude oscillation in the plastic region. The enormous range of variation is illustrated by the following values obtained at a surface pressure of 6 Dienstein gliadin 0.00 cgs unit Zine 0. 2. Insulin 0.21, trypsin 0.12, pepsin at estin 233. Films on acid solutions at pressures below the gelation point are about 30 times less viscous than at the isoelectric point when first spread, and do not at once solidify at higher pressures. The acid reaction does not, however, necessarily abolish the ability to form a gel. It only prolongs the relaxation time from a few seconds to a few hours. The relation between the various elastic moduli has not been worked out fully. The rather elaborate experiments that might be needed would certainly yield useful information concerning the nature of the binding forces in protein monolayers. The oil expansion patterns show clearly enough that the compressed films are anisotropic, and it is possible that quantitative data could be obtained by a refinement of this technique. The insolubility of protein monolayers suggests at once that they have an open polypeptide chain structure. This possibility invites comparison with the molecular arrangement in fibers. If the chains had the I-keratin configuration, with the cytokines lying ill, the plane of the surface, the area per amino acid residue would be about 33 if the side chains were perpendicular to the surface and spaced, so as not to get in each other's way. The area would be 16 AG in an A-keratin configuration or something similar. With side chains perpendicular, the area would be about 6 AA. The corresponding values in M Verger, assuming an average residue weight of 125, would be about 1.6, 0.8, and 0.3 respectively. We have already referred to the difficulty of assigning absolute values to the experimental areas. But the range of areas found for gliadin films when apparently spread without loss of material is from 1.6 to 0.5 at first sight. This suggests a change in side chain orientation between 1.6 and 0.8 mg, and some sort of backbone folding at lower areas. As a general explanation, this is inadequate. The surface electric moment is constant between 1.6 and 1 mg, so that probably no change in configuration occurs in this range. This must mean that the side chains are tilted all the time, and it has been suggested that the compressibility at very large areas arises from the elimination of water of hydrogen. The disposition of the polar and nonpolar side chains presents some difficulty. In an extended polypeptide chain composed of ZA amino acids, neighboring side chains are on opposite sides of the main chain. In general, however, polar and nonpolar chains will not alternate in this regular manner, so that it will not be possible for all the hydrophilic groups to point downward and the hydrophobic groups up. If the chains are folded in the plane of the surface by rotation about single bonds, any desired arrangement of GT Philippi on the nature of proteins, Thesis, University of Leiden, NV, Nord, side chains can be obtained. BMT, the X-ray pattern of protein multilayers, seems to show the presence of parallel chains, while the oil expansion patterns prove that there are lines of weakness at right angles to the direction of compression. It is more probable that the folding occurs in a plane perpendicular to the surljack, so that segments of polypeptide chain tend to float up out of the surface if the side chain is hydrophobic, even if it is oriented downward, while the whole segment tends to be immersed if the side chain is hydrophilic. According to this idea, the chain molecules can be regarded to a first approximation as linear polymers capable of acting independently in segments subject to restraints Cn posed by the properties of neighboring segments. Langmuir and Waugh, applying the theory of Escher's solubility, have sought to explain the differences in compressibility of different proteins in terms of differences in the proportions of hydrophilic side chains. Divide the amino acid constituents of proteins into three groups according to the degree of hydrophilic of their side chains. They have shown that the change of area U on compression from 1 to 8 dynes is closely correlated with the content of acids of the most hydrophilic class, class R, while the contraction BC weight 1 in 25 dynes, is related to the ratio of the most hydrohobble, class 3, to the most hydrophilic acid contents. The first correlation they interpret as the result of reversible pressure displacement, solubility, of the last one acids. The R at 25 dynes is assumed to be a measure of the more strongly hydrophobic residues. It is significant that the correlation thus established involves the actual proportions of the various acids or their relative volumes, and not their molecular proportions. This must surely indicate that at low pressures, TGI area occupied by each polypeptide unit is a function of the volume of the cytokine attached to it. Although it does not necessarily mean that the side chains are coplanar with the JOI peptide chains, this seems rather improbable at areas less than 1 mng, where CT is the total fraction of the J-protein accounted for by amino acid analyses and CLL, and C as the proportions of acids of classes 1 and high. The use of COG instead involves the assumption that the acids unaccounted for in the analytical data are distributed in classes I, C, S, N, and the same proportions as those already found. This would be hard to justify. Accordingly, it seems illy at the remarkable exactness of ecpations, E5, and RL30 is largely fortuitous, and in presenting Langmuir and Havigili's data, EFI figure we IF preferred to use mean values of Chi and C as a better approximation to the true values of C2. When this is done with the inclusion of data for a few other proteins, the relationship, although still remarkable, lakes the form shown. Alias is easy to understand, because one would expect that if C3-YAS I residues occurred in several neighboring positions along a polypeptide clean, the pressure displacement would occur more readily than that of isolated residues. And miglet also tend to cause the simultaneous submergence of more hydrophobic residues. The weak point in the picture is that it leaves ply region of compression between 2 and F5 dyne syn unaccounted for. Clearly some process must occur here other than the displacement of class 2 AELs, since it is precisely in this region that the compressibility increases from its minimum value. This minimum value may signal the complete displacement of class I acids. The increase on the light pressure side is unaccounted for unless indeed one again invokes dehydration, as some authors have done already. 5. Properties of mixed films and membranes. We may readily imagine mixtures which, by virtue of isomorphism or of SAE-acidic interactions, remain of constant composition upon compression, others in which one component is pressure displaceable but not soluble. In O'Lears, we may expect true pressure solubility of one component with a Gibbs equilibrium modified by possible specific interactions between surface and bulk phases. There may also be adsorption of dissolved substances, and Doliish S-effect affinities may give the reaction an irreversible character. Within this wide range of geosabilities, we shall find important and suggestive analogies with the behavior of biological systems. In the mixed films of insoluble substances, we have, on the one hand, a mosaic structure of molecular dimensions. In the pressure displacement of one component into the substratum, we see the formation of a bimolecular layer reminiscent of the lipoprotein membranes that have been so widely discussed as a model for plasma membrane. And in the possible effects of surface active solutes WE4C influences, which must have a counterpart in the relationship between biological fluids, and the interface is WD dot, which they come into contact. 8. Mixed monolayers of insoluble substances, mixtures of saturated straight-chain compounds, show the comparatively simple behavior that would be expected. In general, a mixed film of substances giving liquid films is itself liquid, with a molecular area not greatly different from the mean area of the components. While a liquid expanded film tends to be condensed by a substance which forms a condensed film, this is W hat would be expected if the degree of condensation of a film depth, NZS upon the time average area of contact between neighboring chains. The evidence for head group interactions is slight in these cases, although an equimolecular mixture of sterile alcohol and stearic acid gives a solid film of unusually large area. While there is strong evidence for interaction between acids and amines, the condensation of expanded myristic acid films by tripalmitin and penerythritol tetrapalmitate falls into line with the above argument. There are auth-percentered condensing effects which seem to be more specific. Myristic acid is also condensed by cholesterol. P-nonylphenol is condensed by cholesterol, but not by tripalmitin. The determining factor here might be the smaller number of degrees of freedom of the cholesterol molecule. Mixed films containing unsaturated chains have also received some attention. Mixtures of oleic acid and trialine follow Harkin's law of averages, as one would expect. Oleic acid and trialine with hexadecyl alcohol give films of larger area than the average of the components. Upon compression, the oleic acid is squeezed out from the film. Lawrence and Harkins attribute this effect to the bending of the carbon chain in oleic acid at the double bond, this steric factor serving to lessen the energy of contact between the oleic acid molecule and its neighbors. In support of this contention, they cite experiments with the corresponding Fran-9 compound, elytic acid, which has a straighter chain than oleic acid. In the most striking case, they find that a mixture of calcium L-atate and sterilamine, which separately form expanded films, gives a highly condensed film, while the corresponding oleit-amine film was more expanded than a film of oleate alone. In the case of mixtures of oleic acid and tripalmitin, there is an effect of condensation. This may be due to favorable steric relationships conditioned by the fixed arrangement of carbon chains in the triglyceride molecule. Upon compression of this film, it is the tripalmitin and not the oleic acid which collapses. The sensitiveness of the surface method in detecting interactions which might otherwise pass unnoticed has been put to use in an investigation of mixtures of polycyclic hydrocarbons in sterols. These hydrocarbons do not, of course, form pure monolayers. Some, such as phenanthrene I, also do not form mixed films with sterols. Others, by virtue presumably of steric factors favoring close contact, are able to remain associated with the sterile monolayer at certain surface pressures, although they are ejected from the film at high pressures. It seems that two types of film may be formed. The components may be mutually soluble. The course of pressure displacement is then analogous to the variation of osmotic pressure with concentration. A typical case is that of 10-methyl-L2-benzanthracene, 2-O mixed with cholesterol 5E. In the second type, while illustrated by 3,4-benzpyrene and cholesterol, there is evidence that complexes are formed. This type of effect is especially pronounced in presence of stearic acid, and tends, on the other hand, to be abolished by high temperatures and by the presence of double bonds or of particular substituents in the sterile molecule. Both 10-methyl-L2-benzanthracene and 3,4-benzpyrene are carcinogenic. 10-butene-1,2-benzanthracene, which also forms mixed films of the solution type, is not. Thus, there is at first sight no correlation between surface behavior and carcinogenic activity. It has, however, been suggested that the solution type of interaction may be important as a mechanism of transport of polycyclic hydrocarbons from the point of administration to the site of action in the animal organism, while the association type may provide a mechanism for the binding of these substances in oriented biological structures. Reversible displacement of a component into the aqueous phase has been observed in compression of a mixed monolayer of gliadin and cholesterol. In this submersion of the protein fraction, One is reminded of the pressure displacement of residues in pure protein monolayers, but it must be assumed that in the present case, the protein remains as an adsorbed underfilm by virtue of its insolubility, and not necessarily because of any anchorage to the more hydrophobic component. The compressed films have the fluid character of pure cholesterol monolayers. In remarking upon the resemblance of the expanded film to a mosaic lipoprotein membrane, and of the compressed film to a stratified membrane, one is TP18T to suggest that the two theories of an embrase structure can perhaps be reconciled. Deadsorption and penetration Rojo surface tension of solutions of E-polarity active substances is determined by the Gibbs equation. In the absence of specific interactions, this remains trin when the surface of such a solution is covered by an insoluble monolayer. Thus, the minimum surface pressure of the monolayer is defined by the nature and concentrations of capillary active substances P present if this equilibrium pressure is low enough. The monolayer and the Gibbs layer will remain in equilibrium. Alternatively, injection of surface active material under a monolayer will result in penetration and dispersion of the latter and rise of J Rescher until the equilibrium value is attained. Compression of this mixed film will be characterized first by a decrease in area at constant pressure until the soluble portion has lu unquickly expelled D, and then by the usual compressibility curve of the homogeneous monolayer. This ρS will be reversible if the equilibrium pressure of the Gilbey's layer happens to be above the Alasi pressure of the monolayer. The latter will be completely and irreversibly displaced from the surface. Irreversible displacement of monolayers by soluble substances has been observed in numerous instances, of which we may mention the p-agnitration and displacement of protein and of triplemite monolayers by sodium oleate. It seems likely that this effect is nearly always masked by head group interaction, so that after expulsion of the hydrophobic chains that have penetrated the monolayer, the head groups remain adsorbed with the chains oriented downward. The adsorbed layer may prevent close packing of the monolayer and cause the compressibility curve to be of the excitanded type, or it may cause the formation of cross-linkages between head groups and thus decrease the area of an expanded film. This was observed by Askew in his study of films on Akia's butyl alcohol expansion of the condensed film has been found with short-chain capillary active solutes, such as benzoic acid and resorcinol and monolayers of hexadicylamide. Decarboxyl IC acids such as azelaic IO-7QE are also active. The adsorbed underlayer is best detected by its effect on the phase boundary potential, which may be considerable. Penetration occurs more readily as the hydrophobic portion of the penetrant is increased. In penetration by octyl alcohol, caprylic acid, and N2-iol it has been found that the increment for EKLI additional 112 Grange is greater than that given NHU's TLU caress on ANFRT, energy decrease being around 1,000 albinolpert. Instead of the value of 40 found at an air-water interfaces, this result may expires the influence of Van de Waals forces between the hydrophobic portions of penetrant and monolayer. Penetration is also favored by the presence of suitable polar groups capable of reacting with the polar groups, AGFE the monolayer. Rydels considers this to be an essential step in the process of penetration. The most striking cases of UCHL penetration are those in which there is considerable interaction, which may even amount to stoichiometric complex formation. X for yield semblant E to the behavior demanded by the dB's adsorption equation may be absent in these cases. Penetration continuing up to surface pressures far higher than those corresponding to Deb's adsorption of the penetrant in absence of a monolayer. Injection of a minute amount of sodium hexadecyl sulfate under a hexadecyl alcohol monolayer at a pressure of 16 dynes CU causes, in the course of 2 minutes, a rise of press short to 40 dynes and a large rise of phase boundary potential hex, adecyl alcohol, and sphingosine form a very stable rigid complex. from which the sodium oleate cannot be expelled by compression. Sterile films are penetrated by the hemolytic glucosides saponin, digitin, and psychosin in very small concentrations, and by bilirubin and capillary active porphyrins. Nearly all lipoid dietrants or substages capable of dispersing protein monolayers are hemolytic. A distinction has been inexigual between penetrants for protein and sterile monolayers, and some tentative conclusions have been drawn concerning the constitution of certain membranes on the basis of the lytic activity of these two groups of the substances. Other analogies suggest that a close study of penetration and adsorption in monolayers must lead to a more unified theory of pharmacology, and, in particular, to a more sophisticated use of the idea of lipoid solubility. The new molecular point of view should eliminate some of the early anomalies and offer some suggestions for the synthesis of new anesthetics, anticoagulants, and sensitizers. It may give us closer understanding of the mechanism of transport and operation of lipotropic and carcinogenic substances, and of vitamins or their precursors. At present, however, there are no sufficiently systematic investigations to show whether these hypotheses will be justified. Adsorption is not necessarily followed by penetration. There are numerous substances capable of being attached at the undersurface of a monolayer, ranging from simple metallic ions to the multilayers of protein, presumed by Hauser and Swearingen-Gento, be formed beneath the primary monolayer at the surface of an ovalbumin solution. All are capable of influencing profoundly the properties of the monolayer. Tartrazine, by combining with the free NH2 groups, enables ovalbumin to spread rapidly on acid solutions and causes liquefaction, and increased pressure solubility of the resultant monolayer spermidine promotes spreading of pepsin on alkaline solutions. By becoming attached to two or more barium atoms of a barium stearate monolayer or to two NH3 ions of hexadicylamine, the polymetaphosphate calgon causes a remarkable increase in the rigidity of these films' adsorption. Multibasic substance, tannic acid, at neutral reaction or of sodium tungstate at pH a thorough analysis of these effects, which show considerable variations among different proteins, should contribute to our knowledge of the geometrical distribution of polar groups in monolayers, at the same time presenting an analogy to the action of agglutinants, the adsorption of metallic ions, which in minute concentrations may profoundly affect the properties of monolayers of stearic acid and other substances containing carboxyl groups, has been studied by Langmuir and Schaefer. The di- and trivalent ions are able, in occupying two or more N groups, to confer considerable rigidity. Under suitable conditions, this effect can be antagonized by monovalent cations, an action which can be expressed in analytical terms by the use of a semi-empirical adsorption C, bimolecular films and membranes. Study of the liquid-liquid interface. Proteins spread very rapidly at a liquid-liquid interface to form insoluble monolayers of much the same area as those at the air-water interface. And with much the same mechanical properties, the force area curves resemble those of gliadin and are said to follow closely the behavior suggested by Langmuir's theory of the liquid expanded state. Interface takes on an opalescent appearance resulting from the formation of numerous ripples in the monolayer surface, a phenomenon that can also be observed by spreading a froth of egg white on a sheet of stretched rubber. Upon relaxation, the hexagonal cell walls are thrown into sinus folds. In the former case, it is probable that the folding occurs when the interfacial tension becomes zero. Oil drops covered with a folded film of this type can form a thermodynamically stable emulsion. Fly occurrence of such films also favors the preparation of protein membranes. The film can be folded double by lowering a wire loop vertically through the interface. Membranes made in this way from a film at a pure benzene surface soon break in T-vator, but much more stable ones are produced if the benzene contains a little lecithin. These consist probably of two layers of protein separated by one or two of lecithin. Danielelli, 2 years earlier, had described spherical shell oil films of the same type, obtained by allowing a heavy drop of a salt solution containing a little protein to fall through the interface between an oil and a dilute protein solution. The tension of these membranes has not been maintained. It is probably very low. The low surface tension of certain cells, such as the unfertilized Aracia egg, has been attributed to the effect of a protein component of the plasma membrane. And a similar effect has been demonstrated directly in the case of the oil droplet from a mackerel egg, which in its natural environment has an interfacial tension of only 0.6 dynes cm. In water, the value rises to 10 dynes cm, falling again to the original value on being placed in an aqueous egg extract. This implies that the protein component is adsorbed in soluble or elutable form. More work is needed to determine the conditions under which soluble films can be produced in vitro 6 chemical reactions of monolayers. It is somewhat difficult to make a valid quantitative comparison between reactions involving monolayers and the corresponding reactions as they occur in bulk. In a monolayer, the different parts of the molecule find themselves in widely different environments, and an approximate definition of the analogous conditions in bulk cannot be made unless the reaction mechanism is known in some detail. The tentative conclusion has been drawn from the study of a number of surfactant reactions, that the absolute velocity, reaction order, effect of 7dH, and activation energy are often nearly the same as for the reaction occurring in bulk. The most interesting difference lies in the possibility of controlling the steric factor in film reactions by making the reactive groups more or less accessible to reactants present in the subsolutine. The possibility also exists that, under the influence of surface forces or cross-linkages in the monolayer, reactive groups will be altered enough in their relative configurations for the activation energy to be significantly shifted. The most striking case of this occurs in protein monolayers, which seem to lose a good deal of their specific reactivity when spread. Thus, antipneumal, aqueous antibody monolayers will not react with the specific polysaccharide, while spur, aiding completely destroys the biological activity of the interstitial cell-stimulating hormone. Metacantrin dihydroxyurea are reactions which are said to occur only when one reactant is adsorbed. Horowitz, for example, finding that the Hernan-catalyzed oxidation of linoleic acid occurs oily at an oil-water interface, concluded that orientation and deformation of the unsaturated acid are necessary for the reaction. Despite the loss of their more acidic properties, J-rotein monolayers are still attacked by proteolytic enzymes. The kinetics of the interaction apparently agreeing closely with that observed in BNOC, if care is taken to avoid artifacts produced by penetrating fatty impurities in the enzyme. That the bulk reaction is also essentially heterogeneous, and that the first stage consists in the unfolding of the Y-RUT-CI molecule. Gorder found that the spreading of myosin is promoted by partial digestion with trypsin, and that of fibrinogen by trypsin or prothrombase. It is concluded from the time course of the change in phase boundary potential charge that the subsequent reaction in the process of digestion consists in the success side hydrolysis of terminal peptide links, the fragments passing into solution, and leaving a residual monolayer of progressively shorter polypeptide chains. This conclusion is based, however, upon a questionable interpretation of the changes in phase boundary potential. When the reaction rate depends greatly upon surface pressure, it is likely that steric factors are of importance. Liquid expanded films of unsaturated acids with a double bond halfway along the carbon-clean are rapidly oxidized at low pressures by acid permanganate, while removal of the double bonds from the surface by compression greatly decreases the rate of reaction. The rate of digestion of lecithin monolayers by snake venom is similarly extremely dependent upon surface pressure, presumably because the reaction involves attack of the double bond in the oleal group, which may be lifted by compression. The same thing occurs, however, in the hydrolysis of long-chain estrogene, where the active group remains in Te aqueous pliason compression. In the autooxidation of an unsaturated long-chain triglyceride, the maleic anhydride compound of PPE-elasterin, in which the double bond is still accessible to attack by oxygen. Even after compression has removed it from tinning lower interface, and in the plutochemical hydrolysis of stearic anilidate in the first case, the effect has been attributed to the pressure submergence of the ester group, which thus provides a protective hydrocarbon environment for the point of hydrolytic attack. But the data presented do not give very strong support to this view. In the oxidation reaction, although the case is complicated by the OC occurrence of a secondary surface polymerization, it seems certain from a study of the effects of PAHN of inhibitors that water is involved in the oxidation process. The pressure via variation of the photochemical reaction rate is attributed in part to the dichroism of stearic anilide, with consequent change in extinction, efficient as the molecules arc reoriented. These few examples show how hard it is to find clear-cut illustrations of the St. Rick effect in EGs. The effect exists under circumstances in which, at first sight, it would not be expected, and for case a different explanation is invoked. This is not to question the correctness, at least in part, of the exalinations offered, but only to emphasize the complexity of surface reactions and the difficulties of interpretation when direct analytical methods are precluded. This circumstance removes some of the advantages gained by the possibility of examining the reactions of a single layer of oriented molecules. Nevertheless, the study of chemical reactions in monolayers is likely to increase in iometritance and will contribute greatly to our knowledge of the reactions of polymeric substances. 7. Films transferred to solid surfaces. Although the amount of useful biological information derived from them has not hitherto been very great, the properties of films at solid surfaces are of some interest. These films may be obtained either in the form of monolayers or multilayers transferred to a solid surface from an air-water interface, or in the form of layers absorbed directly from solution. Studied with the aid of optical and other methods, they made JRO very useful in the quantitative examination of more or less specific interactions between biological substances available only in minute amounts. Preparation and structure of transferred multilayers. Monolayers of many substances can be transferred from the surface of a solution to a solid surface merely by dipping the plate vertically through the surface and raising it. The conditions under which this transfer occurs have been studied in especial detail by Blodgett. In the case of stearic acid and its salts, it has been found, for example, that a clean glass or polished chromium-plated slide rubbed vigorously with ferric stearate takes up part of a compressed monolayer of copper-bearer stearate, being dipped through the surface occupied by the monolayer, and the second portion of being raised. The decrease in area of the monolayer held at constant surface pressure during each part of this process is about equal to the measured area of the plate, notwithstanding the fact that the measured area is only a two-dimensional projection of the true area, which must be very much greater. The plate, therefore, acts merely as a grid upon which the monolayer supports itself at isolated points. A slide thus coated with a basal layer of ferric stearate and 2 layers of Baku stearate, if subjected repeatedly to the dipping procedure, can be coated with a multi-layer of any desired thickness, expressed in odd multiples of the monolayer thickness. As would be expected, these built-up films, removed from the influence of restraints operating at the water surface, tend to undergo rearrangement in the course of a few hours to the configuration characteristic of the crystal lattice. This change is comparatively slight for the stearates, but rather greater for unsaturated substances. The configuration of multilayers, and its relation to those occurring in the crystalline polymorphs, has been the subject of X-ray and electron diffraction studies. With somewhat divergent multilayers of sterols have been prepared with thickness per molecule about the same as that found for 8-dimensional crystals. Also can be obtained in this form studies of protein multilayers by X-ray. Diffraction appear to confirm the polypeptide chain structure of the monolayers from which they were built. Determination of film thickness by deposition of stepped multilayers. Of more immediate interest is TLI application, TGI's technique, pi to the preparation of stearate multilayers, suitable for the optical measurement of film thickness. Monochronialic light rays reflected from the chromium and the stearate surfaces of a multilayer will interfere with Cly optical path difference between Cly rays. Is XLXW wavelength? In practice, it is found that multilayers built in steps of 2 show up as a series of bands of different brightness when viewed at large angles of incidence in monochromatic light. If the angle of incidence is 73 Ki, the bands of 47 and 49 layers are about equally dark, and the bands on either side of these get progressively brighter. If the whole series of styles is now covered with a film of uniform thickness, the 47 and 49 bands are no longer east-patly dark, but can be made so by adjusting the angle of incidence to some new value. In this manner, the optical thickness of the new layer can be calculated to within a few A, and its true thickness can be determined if its enfractive index be known. In some cases, the refractive index can be determined independently by observing the disappearance of interference fringes formed weakly. The substance is deposited on glass slides of the same refractive index. In other cases, more or less plausible assumptions have to be made. Permanent reference blocks of etched lead glass have been described. Protein monolayers are somewhat thicker when transferred from a water surface at 30 dynes than at 15, but there is no certainty that their actual thickness does not change during transfer, nor that there is not some rearrangement during the process. Some evidence has been given that the outer surface of a protein film deposited on DEP1 film and the inner surface of that deposited when a plate is withdrawn. GB film are both hydrophilic as one would expect, while the opposite surfaces are hydrophobic. The differences are not, however, very clear-cut, perhaps because of the imperfect segregation of polar and non-unipolar groups, or perhaps because of stretching and reorientation during transfer. Such differences as are noticeable tend to become obliterated when the films are dried. The actual recorded values of the thickness of transferred protein monolayers show wide variation. From 9.5 A for oval Bowman spread at the isoelectric point 1 to 76 A for a B film of a complex protein fraction obtained from hemolytic streptocracy. That's some authors. Assuming that the thickness of a protein monolayer must be 5A at low pressures and 10A at high, tend to regard thicker films as imperfectly spread or inhomogeneous. Although some interest attack to the thinnest and most completely degraded films, peculiarly from the point of view of protein structure, a dogmatic refusal to regard the less degraded films as legitimate monolayers is unreasonable in our present state of ignorance. It is conceivable that the physical conditions at biological interfaces are such as to prevent complete spreading and to encourage the formation of viscous or plastic partially oriented films. In these may be embedded protein fragments which still retain some of the specific properties of the native substance and which influence in great degree the physical properties of the film. In presence of tissue fluids containing dissolved protein, such a film will also tend to be associated with an adsorbed layer of practically undenatured protein, the films mentioned above, which on deposition as a B layer had a thickness of 76A, gave an I layer only 24A and an AB layer 47 a thick. The former value can be due only to the elution of adsorbed soluble protein, while the slide was immersed C. Specific reactions of transferred monolayers. KSA related to the foregoing remarks is the question of the extent to which transferred protein monolayers retain their biologically specific character. Specific activity has certainly been observed in monolayers of enzymes or in substances associated with the monolayer's seg-albumin epigears to retain its ability to react with specific antisera after spreading. Show to various antigens. Proteins and nucleic acid protein complexes from hemolytic streptococci. Anti-pneumococcal antibody, on the other hand, is no longer able to react with specific polysaccharide after spreading. The relation of these observations to the completeness of spreading remains largely an open question, in one case tout, however. It appears certain that specific reactivity is retained even by the thinnest films of antigen, and probably that a certain difference in reactivity of the two surfaces of the antigen monolayer becomes apparent when spreading approaches completion. While there remains some doubt as to the survival of specificity in proteins unfolded at a liquid interface, it is very well known that at solid surfaces, adsorption is rarely accompanied by significant loss of activity. Dispersion of the active substance over a considerable area may even cause an apparent potentiation of infectivity of virus particles. Estel. Bacterial toxin or a hormone may be inactivated by adsorption at a chloroform-water interface, while it may remain active after attachment to collodion particles. The mechanisms of various sensitive agglutination reactions, doubtless depending for their occurrence upon adsorption, remain obscure. It would seem that more detailed information could be obtained, at the cost of some loss of diagnostic sensitivity, if the conditions for adsorption could be simulated at a multi-layer surface in the process followed by measuring thickness increment. Comparatively little has been done in this direction, but preliminary work shows what may be expected. Methods of conditioning surfaces for adsorption have been suggested by adsorption of egg albumin 50A increase in thickness. Tobacco mosaic virus 800A and diphtheria toxin 86A observed. The toxin so adsorbed reacts with antitoxin, giving a further 75A increment displayed by adsorbed layers of egg albumin, catalase, and new amokasana polysaccharide antibody. When XG respectively to anti-egg albumin, when XW used respectively to anti-egg albumin, anti-catalase antibodies, and to X pneumococcus capsular polysaccharide. Non-specific adsorption is atrit to obscure some of these regions. Quantitative study and interpretation of some of these effects is obscured by the ambiguity of any apparent increase in thickness, which may represent complete covering of a surface with a thin layer of material, or partial covering with a thick layer. Extremely thick layers, 100 to 500 A of SAML insulin and casein, are adsorbed from isoelectric solutions at the surface of conditioned plates. Isoelectric insulin, but not isoelectric casein, can also adhere to the layers of samine. On the other hand, samine causes insulin layers to detach themselves. There is some slight indication that 2,4-dinitro-cyclohexylphenol, which is known as a respiratory stimulant and inhibitor of cell division, may block the adsorption of insulin by protamine. Clayton W., The Theory of Emulsions and Emulsification, 2nd ed. D. Blakiston, Philadelphia, Dervishian, D.G., Changes of Phase and Transformations of Higher Order in Monolayers. Freundlich, Il, Kappel, Archime, 4th ed., Acat. Verlages, Leipzig, 1930. Rideal, E.K., Film Reactions as a New Approach to Biology. Nature, 144, 693, 1939. Chapter 4. Section 3. Introductory remarks concerning the architecture of protoplasm. Grateful acknowledgement is due to Dr. Eleanor Moore Irvin, to Dr. Margaret Sum Walt McCushie, and especially to Dr. Carl Solner for reading and commenting on the manuscripts of sections 3, 4, 5, and 8. My contributions to this work are dedicated to my wife, Dr. Josephine H. D.L. Ear. A renaissance of my previous book, and pass, to wait too early to see it come to life and, as one hoped, to usefulness. The objective of the last section was a survey and an analysis of molecular structure. The discussion began with atoms and their coordination to molecules and proceeded to aggregates, whose structural complexity surpassed the ordinarily accepted limits, up to which the units may be identified as discrete molecular entity. Jn. This regier die submicroscopical giant virus molecules, the aggregates of single thread-like myosin molecules, or the synthetic polymers, may be remembered. Investigation of these furnished guidance to the study of films, efflets, coservates, bundles of fibrils, and outlets. Entering now the realm of research upon living systems, which we are accustomed to regard as of unrivaled order of complexity. One may try to continue with the more hological approach to this material, as it was the preferred approach to the non-living material. In recent years, in an effort to secure a more direct attack upon the constitution of protoplasm. Various cells and tissues, liver, kidney, chick embryo, sea urchin, eggs, chloroplast, often as frozen, dried, and ground up material, have been extracted with dilute salt solutions, NaDKl. The residue has been dissolved in strong salt solution or in weak alkali, precipitated by dilution, acidification, or strong ammonium sulfate, ritlisol, and so forth. Through these procedures, submicrobial LLC aggregates are obtained, which, according to chemical as well as physical analyses, seem to display a still higher order of aggregation than the units discussed above. By chemical analysis, proteins, nucleoprotein, flavoprotein, fat, lecithin, sterols, cytochrome oxidase, and other substances have been identified. Optical tests have revealed a fibrous structure evidenced by X-ray diffraction diagrams with the precipitated material by intrinsic and flow birefringence with its solutions. But in order to identify these particles as preformed and discrete units, instead of more or less accidental protoplasmic fragments, their composition must be demonstrated to be below a certain degree of randomness, since probably the bonds bedding together the diverse chemical constituents are the relatively weak forces of residual valencies, among the conditions inducing the aggregation of the various compounds. There must be taken into account particularly protoplasmic movements of any kind, either flow or tension, in a certain direction, instrumental in orienting parallel to each other non-spherical units, like polypeptide chains, fibrinogen needles, or gelatin macella, to form strands. The submicroscopic R.R. Bensley and N.L. Hoare, N8 Rec 60, 251, 1934. A.E. Mirsky, Science, 84, 833, 1936. R. Bensley, N.A. Rec 72, 351, 1938. Science, 96, 389, 1942. Elbow, Bonga, and A. interstices of which may be occupied by both solvent and various solutes, lipids, carbohydrates, enzymes, and others. Such strands can be detected in the structureless hyaloplasm of normal cells, and is especially evident in streaming hyaloplasm. An interesting symptom of aggregation in protoplasm has been discovered by A.R. Moore. 2. The plasmodia of myxomycetes are able to grow through the pores of silk gauze or of hard filter paper, the average pore size of which is as small as 1 G. But if the plasmodium is pressed through the silk, it dies, whereas the remainder on the surface of the sieve continues to proliferate. Only when the pores of the sieve have G diameter greater than 0 G does the filtered material survive. Another pertinent evidence of a structural organization of protoplasm has been furnished by Harvey and Marsland in centrifuging Anebia duhia. When these animals are observed under the microscope during centrifugation, heavy particles, crystals, are seen in the cytoplasm to fall not continuously, but in jerks, even when moving through a visibly clear field. Mechanical insult to protoplasm, possibly involving disintegration of an internal architecture, is accompanied by alterations of many metabolic reactions. For instance, respiration of the sea urchin egg is reduced upon cytolysis to about 10% of the original, while the uptake of oxygen. Such effects can be considered as being due to the presence of interfaces in heterogeneous systems, which, nearly invariably by the way of adsorption, change the chemical equilibria and the reaction velocities, which otherwise would be consistent in the homogeneous fluid spaces enclosed in the vacuoles and channels of the intraplasmatic framework. Indeed, there are many ways to interpret as effects of adsorption not only the accelerations, but also the retardations. For instance, the reactivity of organic molecules with a nonpolar polar structure has been found to be sometimes reduced when the reacting group is attached to the nonpolar part by orientation at the interface in such a way that this part of the molecule is buried by adsorption in the interface, while the chemically inert polar half is turned toward the aqueous phase. More frequently, acceleration is encountered as a result of an increase of concentration of the reagents in the adsorption layer. But since the protoplasmatic structures can be assumed to be OPH, Zischer F. Elektrochemie, 86, composed of more than one adsorbent, the effective adsorption in such a polyphasic system would be extremely variable. However, in addition, it must be considered that the single structural units, instead of showing a differential adsorbing power, also can act as solvents, each of them distinguished by its own distribution, coefficient, see Sec 1 chap. 5. In phasic system, the effect will depend not only upon the variety, but also upon the mutual location of the differently acting units. The significance of a suitable arrangement of these is made evident, for instance, in the following experiments. First, a stream of hydrogen is passed through water containing a suspension of platinized asbestos. Methylene blue dissolved in the water will be hydrogenated by the activated hydrogen. But no hydrogenation occurs if the methylene blue is added after being adsorbed to filter paper, which has been thoroughly washed with water to free it from the unabsorbed surplus of dye. This is because hydrogenation is effected only the filter paper is gradually depleted. If a small amount of dye remains dissolved in the water, because the dissolved dye mediated as an electron carrier between the two surfaces, Sec 1, chap 4, CC 6 chap 30, Sec 8, of intracellular enzymes are attached to the structural colloids of the cells, but in such a pattern that a certain spatial succession secures a proper sequence of reactions, for example, the stepwise breakdown of large molecules, or that an immediate linkage provides the association. The latter case is illustrated by the following observation. In lactic acid formation in muscle, the two enzymes, muscle amylase and an esterifying enzyme, appear to be so closely concatenated and interdependent in their activity that they can be considered to form a single colloid aggregate, held together, however, so weakly that even by a short exposure to a moderately elevated temperature, the delicate complex is ruptured. Through many observations like these, the old idea of a chemical organization of the protoplasm, as complement to its structural or mechanical organization, has received new and more substantial support. Beyond that, it has stimulated the investigation of the linkage between cell work and cell chemistry. The numerous enzymes can be pictured as adhering to the cell structure and acting as catalysts, not only to accelerate the orderly sequence of the metabolic reactions, but, presumably, further to induce the immediate transfer of the liberated chemical energy to those structural components, which can be considered parts of the acting cell machinery. For unlike the prevailingly thermodynamic technical machines, the physiological machines are representative of the type of H.A.F. Hofmeister Naturwissen T500 chemodynamic machines which, in one way or another, transform chemical energy directly into mechanical, electrical, and radiant energy. Moreover, the cell machine excels other chemodynamic machines by the submicrobic dimensions of its elementary parts, spread to form a huge area for adsorption catalysis, thus providing an adequate means for prompt and reversible acceleration, or retardation, of metabolic nacta, and as the source of energy, j.e. giving increased consideration to the study of the microstructure of large molecules. The old and fundamental problem of how to conceive of the direct interaction between the structural and the chemical events seems to have been attacked with greater success before on the classical field, where for a long time one is searching to detect a device for coupling muscle work and muscle metabolism. Today, it is generally believed that the myosin molecules, which are folded polypeptide chains, are arranged to form long fibrillar nuclei Sec2 chap 8, which under various either chemical or physical influences are shortened by an increase or lengthened by a decrease of Tluer folding. These changes in length are reversible. Therefore, the myosin threads are believed to be the contractile machinery. Now, Engelhardt and J. Jubernovas have discovered that in a solid myosin, after adding adenosinophosphate, which is known as one of the essential components of the metabolic cycle in muscle, and as the chief contributor of free energy of contraction, CCC6, chap 30, liberating 1-phosphate from the triphosphate, that is, yielding adenosine diphosphate, spontaneously relax. Therefore, one may say that myosin behaves like an enzyme, like an adenosine-phosphate. And so, evidently, the coupling between mechanical and chemical action takes place in such a way that the machine itself, as a contractile enzyme, releases the chemical reaction by which it sets itself going continually on the background of this progress. It is inspiring to direct attention to other microstructures possibly suitable in their physicochemical properties to demonstrate the direct transformation of free energy of a chemical process into mechanical energy. In this resject, OG may refer to models which have beam-described membranes being essential parts of the surface and the interior of each cell, presumably are endowed with pores of various width and a variable electric charge of their walls. Interposed between AI-appropriate electrolyte solutions, for instance, the surface active narcotics can sever the contact between the enzymes and their substrates by covering the interior surfaces. See the adsorption theory of narcosis of different concentrations. Due to the selective ion permeability of the individual pores, such membranes can perform electroosmotic work by shifting water, cations, or anions against the concentration gradients until osmotic equilibrium is reached. Metabolic production of ions at the interfaces of the membranes may become effective for initiating or maintaining the electroosmotic work, not only by establishing concentration gradients, but also by altering the width or the charge of the chi-ores of the sieve membrane. Following these introductory remarks about some physicochemical aspects of protoplasm as basic substance in all living things, animals, and plants, cells and tissues, the subsequent chapters will deal with the surface of the protoplast, its properties and its architecture, WDF environmental influences on manifestations of cell life, WDF cell metabolism, and cell energetics. With excitability and contractility, with active transfer as superimposed to passive penetration. Frey Weisling, A. Subinakroskop. Morgi Iogi de Protoplasias. Rorntrex, Berlin. V. An outline of general physiology. N.D. Saunders, Philadelphia, 1948. Leobrun L.V. V. Deloyd, Highway of Protoplasm. Born-Traeger, Berlin, 1928. Cephras W. Protoplasm. Men. Irohill, New York, 1980. Cephras W. L. S. Moyer, O. L. S. Piesler, and 1 Bath 1A Marsland. In the structure of protoplasm, state Olegian breasts,